Hello everybody and welcome to Chapter 1 of Python for Everybody. I'm Charles Severance, I'm your instructor, and I welcome you to this class. The basic goal of this class is to teach everybody how to program, regardless of your background. You don't have to be a math whiz, you don't have to be a computer expert, no matter how old you are or what your background is, we want to teach you how to program. So welcome to the course, welcome to Chapter 1. So, the first thing to understand is that the purpose to learn to program is because computers want to do things for us. They are built and created and designed, and their hardware is set up so that they basically ask us, what do you want to do next? If you grab your phone sort of does nothing until you tell it what to do. It waits for you. And it's just waiting for you, and all the hardware, computer technology around you is generally waiting for you. And we can use this for useful things. We could play video games, we could have it help navigate for our cars. Someday we might even have self-driving cars. And it's really, in a sense, in my mind, silly if you spend your whole life not really understanding this technology. And I think it's important that we learn to tell these computers what to do rather than just let them increasingly control our lives. And so, as we'll see, computers aren't very smart on their own. We humans are the ones that imbue them with knowledge, but we need to learn to speak their language. It is much easier for us to learn to speak their language than it is for them to learn to speak our language. Although, with these cell phones, we're starting to see little bits where they can begin to understand, but you would be amazed at the 40 or 50 years that it has taken us to understand how to build programs to begin to understand. So I'm bringing you into something where you are going to learn the ways of programming and the ways of the computer, because it's easier to teach you how to program than it is to teach this how to work in your world, even though ultimately the goal is to get this to do work for you. So part of what I'm trying to do is move you from a user perspective where you just look at the computer as something that someone else has constructed and you are the user of, to the point where you construct new things. Now the first kinds of things that you're going to construct are actually things to solve your own problems. And it's very popular now to work on data, and Python is an excellent programming language for data mining and data analysis, and that's a lot of what we're going to do in this course, although really it's a gateway to all kinds of things like, artificial intelligence or gaming or navigation or mobile applications or entertainment, all kinds of things. But first we have to learn to program. We have to move from using the computer as a tool to using the tools within the computer that allow us to change how the computer sees the world. So there's a couple of reasons that you might want to be a programmer. Some of you are looking to improve your career, to be paid to work on programming. I've been a paid programmer most of my life, and I like it. It's a good job. You don't have to stand in the mud, you don't have to lift things, you have to use your brain. And I'll just say that it has been nice for my career to not be exposed to the elements, but to be able to work often wherever I want. But that's actually our secondary goal. Our first goal is to get you to write programs that solve problems that you have to solve. Maybe you have a job as an accountant or a lawyer or something else, and maybe you run across some data. Maybe there's some system that logs your time and it's not quite giving the report that you want to give, and so you say, could I just grab the log data myself and write a program to do some analysis to say, oh, what's the average this versus that, or the average of some other thing, right? And so that's the basic idea, that you'll initially use computers to serve your own ends. That makes it a lot easier to write programs because you don't have to worry about, a million users using your software. If it works for you, then we're happy. And so it takes a little more training to write software for other people or for thousands and thousands of other people. And so part of what I want to do is I want to change your perspective. You look at this from the outside and you see it from the outside and you click on things. I want to turn this around and I want you to be the person inside this looking out at the world. And as a programmer, we are making things inside these computers for the world. And so we want to pull you into being part of this. We want you inside this or thinking inside this. And what you learn is that if you're inside this computer and you are taking your instructions to build programs to be used by the human, oops, almost dropped that, the human outside the computer, you have things that you need to take advantage of. There's things like the central processing unit, the memory of this system, the network connection of this system, the disk drive or permanent storage on this system. And as a programmer, you are kind of mediating between all those internal resources that this has that are not very smart but highly powerful, and mediating with what that user wants, right? And so we take the end user and we programmers, we serve the end user, but the computer serves us. So together, between us and all the computer's resources, we can serve the needs of the end user. And we do this by writing code or programming, okay? And what is that? Well, programming is a sequence of instructions where we are giving instructions to the resources inside the computer in a way to accomplish the goals of the end user. And remember, sometimes we are our own end user. It's not just it's not just, you know, you're not always doing a startup, you're not always writing a mobile gaming system. Sometimes you're writing something for yourself, but that's okay. So sometimes you're writing something to solve a problem. You're like crafting, you're doing something that you could do by hand or manually, and you're making some clever little 25 or 100 line program, and you're putting that in. Other times, like when I work on the open source learning management system Sakai, it is my creativity. I've got an idea and I want to share it with 1 million users, and so I write my code for an external audience. And so code is that sequence of instructions that the computer itself doesn't know how to hand a roster out, but I can write code that will hand a roster out by looking at the data that's inside this computer, inside this application. And so if you think about programs, we have programs for computers and programs for humans. And a number of years ago, now sooner or later this will be me showing my age, this is an example of the Macarena. And the Macarena is a song that effectively is a sequence of instructions. You put your left hand out, you put your right hand out, you put it on the shoulder, you wiggle, 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 and you spin around and you do things. And this is a program for people. And so I want you to take a quick look at this and see if you can find anything wrong with this particular program. So look really closely. So I'll show you. It's got some typographical errors in it, and we as humans are really good at reading or hearing typographical errors and correcting them automatically and instantly. And but computers are not. Computers are extremely literal. If it saw this ham instead of hand, it would think, what's a ham? And why am I going to hit someone in the back of the head with a ham? And why would I take my left hand and hit somebody? That's, you know, these are all bad things. But the computer is going to take us very literally. And so we have to be really precise. And the computer just doesn't know the difference between what we mean and what we say. So we have to be very precise. And this is one of the great frustrations that people have when they first start using computers. And so we have to get this right. We have to get these little bits of text exactly the way they are. Computers will blow up with syntax errors, and they seem to make quite a fuss when you make the tiniest of errors. But you'll get used to that. I mean, that's not because you're bad or you're less than awesome. It just means the computers can't compensate when you make small mistakes. And so you got to get used to the fact that the computer is sort of intellectually not as strong as you, and so it gets confused really easy. Even though when it gets confused, it says seemingly mean things to you. So you'll get used to that. Okay, so the first thing I want to do is I want to throw up some text, and I want you to, while this text is up, I want you to count the number of each word in this text and tell me what the most common word is in this text. Okay, so here we go. Okay, so I kind of made that hard on you on purpose by moving it around and distracting you and confusing you. But even if it's not moving at all, it's a little bit, tricky to do. You probably stare at it a couple of times. Your brain is going back and forth and back and forth. And so text analysis is one of the great things that computers are very, very good at. And some of the things that, they can translate text, and that's because they've looked at a lot of information. So looking at text is actually something computers are really good at. And so if we take a look at the kind of programs that we're going to write to do this kind of thing, this is something that humans are not naturally good at, but computers are super good at. Now, I'm not going to have you look at this code. This code you will understand in a few weeks, but basically this is a set of instructions to open a file, read that file, read all the words in the file, create a histogram of all the words in the file, and then search through that histogram to find the most common word and tell us what the most common word is in the file. And in this clown file, the word "the" is the most common. It happens 7 times. And here's another large file called words.txt, and the word "to" is the most common thing. And our goal is to get to the point where you can write this on your own. So you can say, you know what, I got a problem to solve. That is, what's the most common word in this file? I know how to start, and then I know how to finish. I know how to do the stuff in the middle. And we have to learn this kind of weird language, but when we do, we can count millions of words as easily as you count 20 words. So that's the fun of all of this, is to teach you this language so that you can solve that problem so that you don't have to solve it. Because you could solve it, but it's not something that you're naturally good at, and it's hard work. So up next, we're going to talk a little bit about the hardware architecture that you're going to be experiencing as you write programs. Hello and welcome back to hardware architecture. Now you might ask, why do I tell you about hardware architecture? Probably you're not going to build any hardware, although it's fun stuff to do, and if you're going to become a computer scientist, which most of you won't want to be, it's a great thing to study, and those who build our hardware are amazingly talented individuals, and it's a really rewarding job. The reason I like talking to you about hardware is because I want to be able to use words at some point and say, oh, secondary storage, or central processing unit, or random access memory, or peripherals, input devices. And I want to be able to say those words, and I want you to be able to understand them. And so I'll start with a little piece of hardware called the Raspberry Pi. And the Raspberry Pi is a cute little single board computer. As we go forward, these things are smaller and smaller and smaller. And the interesting thing is that the architecture of these stays the same, but the number of components drops. So I'm going to start and give you a block diagram of sort of a generic computer and tell you the major parts of it. Now, I'm going to show you some really old hardware, some really new hardware, and then some hardware that is of medium age. And the medium age hardware is probably the easiest one to see. The architecture is the same, okay? And so the basic block diagram is that the brains, if there are brains in computers, which there really aren't, the software is the closest thing computers have to brains, but in hardware, the closest brain a computer has is this, called a microprocessing unit or a central processor unit. And this is designed 3 billion times a second to ask the question, what do you want me to do next? And these little pins on the back are our instructions, like 32 or 64 of these pins. 3 billion times a second, we send an instruction into these things. Now, we can't sit there and talk to it. We can't. And so the instructions we store in what's called the main memory. And this memory is really fast, and the memory sort of feeds this. And so every time the CPU needs a new instruction, it asks the memory where that instruction is. And so the memory feeds the instruction to the CPU does it, says give me another instruction, CPU does it, gives me another instruction, and that is the basic essence of programming. This asks what's next, and this is where your program is stored, or a program you purchased or came with your hardware, where that's all stored, and those are your places. And so you end up inside, your programs end up inside this memory. So then there's so in software you tend to program the CPU, and if you had bought a desktop computer a number of years back, it would have this thing called the motherboard. And the motherboard is called this because it kind of connects all the components together. And so if you buy memory by itself, it does nothing, but it has a place to plug into the motherboard. And if you buy a microprocessor, it has a place to plug into the motherboard. And if you buy a hard drive, this is a really old hard drive, it has a place to plug in on the motherboard, and so the motherboard sort of connects everything together. The hard drive is secondary storage. Now, the way how secondary storage is different than the main memory, which there it is. I got unpile this stuff. So this main memory is really fast, but as soon as you turn the power off of this memory, it sort of vanishes. And so to store files like word processing files or text files or whatever, you got to store it on something that lasts a little bit longer. And so that's the purpose of the secondary storage. It's permanent. When the power's off, it stores it. Now this one here is in such bad shape that isn't probably storing anything, but it's got these little heads, and it spins around and goes in and out. And we'll have a video later that shows you one of these things that's not quite in as bad a shape. If you look, this has 4 different platters that are all spinning around. And so this is just using magnetic material and electronics that sort of magnetize and demagnetize this stuff. And if you look at a disk, they're often rated, physical disks are rated in revolutions per minute, and that's how many times this thing spins around. And if you got an old desktop and you hear it spin up, this is the thing that's spinning. And it's the place that your operating system lives, your files live, your applications live, while they're stored and while the computer's turned off. And then they're loaded into this while they're running, and then this CPU takes the data from the main memory, and your program runs at 3 billion operations per second. So let's talk a little bit about something that this is probably from the 1960s or 70s. This actually has, if you're an electrical person, it has capacitors. Those little silver things are capacitors. These little colored things are resistors, and that's more capacitors. And then there's wires, and wires move everything. And so when you say like this has millions of transistors, oh wait, that isn't a capacitor, that's a transistor. That's a transistor. When you say that this here has etched, and if you look closely at this, go look at a picture of a microprocessor online, you will see that it has millions of these. And so the difference between 1960 and today is this circuitry of capacitors, resistors, and transistors has been microized and put onto this. It's using a photographic process, and they're tinier and tinier and putting more and more on. And if you think going from millions of these to one of these is crazy, the thing that's happening now, and the reason we have whole computers inside our pocket, is that everything, all of this whole thing, CPU, memory, everything, all of it connected, and the storage is being made smaller and smaller. And so this little single board computer called a Raspberry Pi has one thing in it, and it has the main memory, and it has the CPU, it has connections for things like peripherals like keyboards and stuff. Now it doesn't yet have secondary storage on it. The secondary storage gets plugged in right here via USB. And then if you take it one step farther to my phone, it's got the secondary storage built right in. And so, you know, this picture goes from the size of cabinets in the old days all the way down to really tiny. But at the end of the day, inside it is a highly sophisticated piece of circuitry that asks for instructions one at a time, and main memory that holds the instructions and feeds them. Okay? Central processor does the thinking. Let's take a look here. Central processor does the thinking. It runs the program. It's asking what's next. It's not really smart, but it's really fast. And so we compensate for the lack of intelligence of this thing by us writing really good software that runs really fast. And so voice recognition on things like phones is possible because computers have so much storage and they run so fast, and the algorithms that do voice recognition are finally starting to work. Input devices like keyboards and mice and pens and whatever, they come in. Output devices are like the screens that we see. The main memory is the fast part of the computer that stores all the programs, and the secondary memory is the permanent storage. Increasingly, secondary memory, do I have any USB sticks in here? I don't. Well, increasingly secondary memory is flash RAM or static RAM with no moving parts. And so you, in a few years, you'll not even be able to see secondary memory with moving parts. But that's okay. It's still secondary memory. It's still memory that lasts. And so you, and where your place is in here, is you live in the main memory. This is you. You are here. And so, in a sense, when the CPU asks the question, what next, it is your job to answer that. And you answer that by writing Python code. And so your Python code, you'll write a file in Python code, blah, 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 blah. And then that Python code sort of gets loaded into main memory. There's a magic translation process that happens. And then your code is actually answering this question 3 billion times a second. 3 billion times a second, you're sitting there. But this is you. You're really out here, but you then write a file, and the file's loaded in, and then the file runs. And that's how things are at. And that's your place in the world. Now, what's actually running is not Python code. There is, as I said, a translation process. You write a Python file, and then Python itself translates this into the actual language known by the microprocessor, which is a series of zeros and ones called machine language. Someday I would love to teach you a class on machine language, but for now we're going to teach you Python, and we're going to use Python as a crutch. We don't have to talk machine language, but you could, if you really wanted to, you could know how to write machine language. But I assure you, Python is far easier to learn than machine language. So Python acts as a translator, translates what you're doing into machine language, and then the machine language is what's sent back and forth. But still, even though it's translated to machine language, it's you. It is you answering those questions, and that's what a program is you pre-storing your response to the what next question over and over again. So here's a couple of videos that you can look at on YouTube about a CPU. These CPUs, and it looks very much like this CPU that I've got with me, these CPUs have extremely high heat. When you put this thing, or your computer, on your lap and it starts to heat up, that means it's thinking really, really hard. And so this is a small little old video from a long time ago that shows what happens when you take out the cooling capability of microprocessors and just how hot they can be. And the other video that I have is a hard disk, something like this hard disk that I have, except that it works and they turn the power on. Some of them last for a few seconds, some of them last for a few minutes. It's never I must be allergic to this hard drive. Or maybe it's because there's dust in this hard drive and I keep spinning it and I sneeze. But basically, some of them last for a few seconds, some of them last for a few minutes. It's not a good idea to open them up, but I'm glad somebody opened it up and then did what they did and then recorded it so we can all enjoy what it is that they're capable of doing. Okay? So that's a quick introduction to hardware, mostly so that I can use those words going forward. Now, what we're going to talk about next is communicating in the language Python. That is, writing code and putting it into the computer so that that can execute. Okay? And welcome to my video that shows how to get started and install Python on Microsoft Windows. Okay, so it's not too hard. We're going to both install Python 3 and we're going to install text editor. And so I'm just going to go into Google and I'm going to say install Python 3. And my top link is downloading Python. And there is my link for downloading Python 3.5.2. This version of my class uses Python 3. I have an earlier class that you may have seen that uses Python 2, but in this class we're going to do this. Now it might take you a while to download this. I've actually already downloaded it. Now the other thing we need is a programmer text editor. And you can really use any programmer text editor. We've used Notepad Plus in the past. We've used JEdit in the past. I like Atom, Atom.io, Tom.io, mostly because it works the same on Windows and Mac and Linux. But you can really use any text editor that you like. Just don't use Word or text edit that comes with the operating system. You need a programming editor that doesn't mess with weird characters or weird lines or strange formats. You must have a real programmer editor. So I've already downloaded this as well. And so I won't waste the time waiting to download it, but let's go ahead and do the installation. So these things ended up in my downloads file. So I'll go to downloads and I'll start installing Python 3.5.2. Now it's going to ask me some things. Add Python 3.5 to the path. Yeah, that's a good idea. Install the launcher for all users. I'm going to add that. Maybe you will, maybe you won't do that. It's going to tell me where it's going to install it. Install now. Of course, it's going to ask me for permission to do these things. And now it's running through the installation. Okay, so there we go. You could maybe click on this online tutorial and documentation, but we're just going to close this. And I'm going to start and run the Windows command line. Now, you may have all kinds of fancy ways to run Python, but I like running the command line, COMMAND. I like running the command line because after a while it's important to know what folder things are being run in. And so here's this command line, and I should be able to type Python here. And so now I'm in Python 3.2, and this is the chevron prompt here is the Python interpreter, where it's asking for Python commands, and I can say print hello world. Of course, this is what we tend to print all the time. I can make a mistake. I can say blah, blah, blah. Right? And it'll complain to me. Now to get out of this, I can either type Control-Z or quit. In this case, I'm going to type Control-Z, and I'm back to the prompt. A couple of things. I can do a dir to see what folders and files I have, and that is like my desktop. And then the cd command tells me where I'm at in the folder. That means I'm in the users directory, Dr. Chuck. Okay? So I have now installed Python. I ran the Python interpreter to verify it. I said print hello world. Okay, and so now what I'm going to do is I'm going to actually install Atom. I already had this downloaded, so let's go ahead and install Atom on my computer. Okay, so Atom is now installed and it's kind of telling us what to do. I'm going to actually just close all these windows, close this window, close everything, and I'm going to create a file. I'm going to say print, in this case, let's see if I can make this bigger. I can make it bigger. So I'm going to type print hello from a file. Okay, and I'm going to save this. I'm going to say File, Save As, and what I'm going to do is I'm going to go to my desktop, and I'm going to make a folder on the desktop. I'm going to call this folder PY4E. So I now have a folder on the desktop. Move this here. I'll move this here. Oops. And I'm going to go into PY4E, and then I'm going to name this file first.py. And you'll notice that when I save this, it syntax highlighted it. That's one of the nice things about a programmer editor. Okay, and so it says, oh, it's got a suffix of .py, so therefore it knows that it's supposed to look pretty with Python and make this one color, make this another color. The other thing that you'll notice is that I now have a folder called PY4E. And if I'm in this command line, let me just start that up again. I'll show you how to start the command line again. Command. Now, if I do a dir, I see the folders that I'm in, and one of the folders that you can see here is the desktop folder. So I'm going to say cd desktop, and then I'm going to type the dir command to see what folders are in the desktop. These folders are the same as these folders. These things are kind of virtual folders. PY4E is PY4E. Now I can type cd, which stands for change directory, PY4E, and I can do a dir, and now you see first.py, and that's the same as if I'm diving into this folder. Here's this file, first.py. Windows hides the suffix, which is somewhat annoying and frustrating, but that suffix is there, that file is there. And so for me, one of the things you got to figure out in Windows is how to make sure that you are in the same folder, users, Dr. Chuck, desktop, Py4E, and that's the name of this file, and here as well. And now I'm going to run this program. I'm going to type Python first.py. And you see that it ran the Python code. Okay? Another way you can do this is you can type first.py. And that's because this file association has happened in Windows. This doesn't work in Macintosh. This only works in Windows. That all files with .py are expected to be Python, and it knows the Python interpreter where to run it. Okay? And so I've got Python 3.0 installed, and that gets me started. And so I hope that this little introduction about getting things started and writing your first Python program has been helpful to you. We're going to actually download and install Python 3 from python.org on a Macintosh. If your Macintosh for years has wonderfully come with Python 2. So if I type Python ---- version, then if I type that, I see that I've got Python 2.0. What we want to do is, in addition, install Python 3. One of these days, Macintosh might upgrade their distributed version of Python 3, but there's so many things inside Mac that depend on Python 2. I'm going to expect that it will always be named Python 3, which is what we're going to call it in a second. So here I am at the python.org downloads, and I'm going to download Python 3. You click here, and I've actually got it sitting here in downloads already because I always do that. And so, I'm going to install this. There is the installer. I'm going to say continue, continue, continue. Of course I agree. I read all that really fast, and now I'm going to install it. Okay. So now that means if I run a terminal, so this of course is start run terminal. So Python 2 is still there, but Python 3 is also now there. So we should have Python 3 installed. So we installed Python 3.6, and so there we go. And that's all it takes to install Python 3 on the Macintosh. So let's write our first little Python program. I'm going to, I like Atom. And so I've got this Atom editor. It's atom.io. Right here, atom.io. Download and install the Atom editor. I like it because Atom works the same on both Windows, Mac, and Linux. And it has syntax highlighting, and so I really like things like that. So I'm going to make myself a simple Python program. Hello world, like we always do. Now you'll notice that it's not syntax highlighting yet, but I'm going to do a file, save, oopsie daisy, file, save as, and I'm going to go into my desktop and I'm going to make a folder called py4e. I'm just going to call this hello.py. Oh, crud. Got to rename it. Rename it. I ended up with 2 dots. Hello.py. There we are. And so now I'm here, and I'm in my home folder. I can go in my desktop, and I can go into that new folder I made, Python for Everybody, and I can see the files. Now, there are ways to run this, and I really want you to learn the terminal so that you really know what you're doing. And so here we are in the folder that has the Python, and then all we do to run it is we say python3 hello.py, and there we go. And of course, this is Python 3 because I'm using parentheses there. So instead of double quotes. But Python 2 is still there, and of course, if you just run python hello.py, it'll be a syntax error, or not. Must be they added something. Yeah, because Python is still version 2, but apparently they allowed print in the latest version of Python 2. So away we go. Okay, so again, thanks for watching. I hope this was helpful to you to get Python 3 installed on your Macintosh. Hello and welcome back to Python as a Language. You'll notice that I'm wearing a hat. Part of the story of the hat is that where I work here at the University of Michigan School of Information, my office is in this building called North Quad, and we call it Quadwarts sometimes because it's sort of got a square. It sort of imitates an Oxford quad. And so it seemed to me to evoke notions of Harry Potter. And when we first moved into the building, I joked in one of my classes that we should have a sorting ceremony for all the students as they come into North Quad for the first time. And so that was cool, and I thought that I would belong in Gryffindor, like everyone wants to be in Gryffindor, right? They're the good guys. And my students told me that I couldn't be in Gryffindor, that I had to be in Slytherin. So you'll see me drinking tea throughout the course out of this teacup. It's my Slytherin teacup. I picked that up from Harry Potter World. I went down to Florida and visited Harry Potter World. And the reason that I was sorted by my students into Slytherin is also because I teach Python. And Python is like a snake. And so if you think about the people from Slytherin, they are capable of talking to snakes. And the class that we were doing the sorting was a Python class, and so it sort of made perfect sense that you would have to be in Slytherin if you were the Python teacher. And of course, your name is Charles Severance, and then that sounds kind of like Severus Snape, and so I just accepted that I'm in Slytherin, okay? So you all can be in Gryffindor, but I can't. I'm in Slytherin. So I'm the bad guy, or the good guy, depends on how you look at it, right? And so what I'm going to do now is I'm going to, bring you into Slytherin as well, because I'm going to teach you the Python language. Python is the language that we Pythonistas talk. It was invented about over 20 years ago by a fellow named Guido van Rossum, and away we go. Now, even though I'm using this whole snake Slytherin thing, it turns out that Python was not at all named for Harry Potter, because Python was invented you know, almost 2 decades before Harry Potter was created, and it wasn't for the snake. It was actually Monty Python's Flying Circus was the inspiration for Python, the name Python, and because Guido van Rossum really wanted to create a programming language that, while it was powerful underneath it in its very nature, was a very powerful language, he wanted it to be a language that was fun. And he wanted it to be a language that was approachable. And so that's why Python recently has become so absolutely popular. It's easy to learn, but it's also powerful, and that's sort of the magic of Python, is the ease of learning it, the brevity of the programs, the shortness of the programs, and the power. And so we are going to become Pythonistas. Now, as you learn to be a software developer using the Python programming language, you are going to encounter syntax errors. And I remember when I used to get syntax errors, and I remember my first programming class, and I would type on cards. And I would upload those cards to the computer, and the computer would say, "You're not worthy." And I'm like, wait a sec, those are pretty good cards. How could you be so critical of me? You know, I'd say syntax error. And I really got sort of a really bad attitude that somehow this computer didn't like me, and that I would make cards, it would complain, and I would make changes to the cards and it would still complain, and I'd make changes and it would still complain. I'm like, how can I win in this situation? And you're going to feel the same thing. You're going to absolutely feel the same thing. You're going to be struggling. You're going to be like, how come this computer hates me? Let me assure you right now, the computer doesn't hate you. The computer actually loves you. It just is not very good at showing how it loves you, or telling you how or why it loves you. And so syntax errors are not so much Python telling you that you're bad, or that you're an inadequate programmer, or you should find something else to do. It's really Python's admission that it doesn't understand what you're trying to say. And so you got to get used to that. And it's frustrating, but you got to get used to the fact that syntax errors are your friend. Python is saying, hey, I got to line 7 and I was doing fine up to line 7, but boy, in line 7 there's some little thing. I don't know what the word else means in this context, or you didn't indent it, and so I'm kind of confused. What did you mean? Please, please, please help me. You know, and so it's so much easier for you to learn Python than it is for Python to figure out what you mean when you're writing code. So we have a number of different ways to sort of encode our instructions when we talk to Python. One is we just run Python interactively on our computer. Hopefully by now you've got it installed, and you just type Python at a command prompt. So either a Windows command prompt, or a Linux command prompt, or a Macintosh command prompt. And I got some examples of how to sort of get this all started, get Python installed, and away you go. Now you'll notice when you run the Python interpreter, the 3 chevron prompt, Python is asking you what next, right? This is you, it's saying, I want to talk to you, I want you to tell me some Python to do. If you know the Python language, you know what to say right here. Now if you know Python, you can type these languages. You can say, oh, x equals 1, which really means go find a little piece of memory, label it x, and stick 1 in it. Print x is like, go find that thing where you labeled it x and bring me back that number and tell me what I stored in there. Now why you want to do this, that's a different question. These are very simple things. It's going to take you a while to get the big picture of why we're doing this. So just trust me that you want to learn these statements, and then later we will successfully turn those into a program. So x equals x plus 1, the third line there. X equals x plus 1 is not, as it seems in math, it basically says, hey, go grab the old value of x, add 1 to it, and stick it back in x. That's what that means. So an equal sign really has kind of an arrow to it. And then we say, hey, go look up that x thing that we just did and print that out, and then we're going to say quit. So that's us talking to Python. Now, you can type just about any crazy stuff you want in here, and Python will be unhappy and talk to you. So what we're going to do next is we're going to start talking about the actual language of Python and what it is that we have to say to make Python happy when we're talking to it. So now we're going to start learning the actual Python language. So what do we say? You can think of this as almost like writing a story. We're going to start with a basic vocabulary. We're going to talk a little bit about lines or sentences, and then we're going to start talking about how to put those sentences together to make a coherent paragraph, as it were. And you just have to accept the fact that when I start teaching you this stuff, it's not going to make sense for about 6 or 7 more chapters. And so just sort of bear with me, except, I remember when I first learned, it went from me confused. Holy mackerel, this is awesome. And so I expect many of you will go through that same thing. So just learn the first parts, accept the fact that it doesn't necessarily make sense in a big picture, and just bear with us, okay? So we'll start with vocabulary, we'll start to make sentences, and then we'll have little short stories and paragraphs, okay? And so this is a short story about how to count the words in Python. It's got a couple of paragraphs, and we are going to look at all of this stuff eventually. So we start with a set of reserved words. And what are reserved words? Well, they're words that Python expects when you use these words that they're going to mean exactly what Python expects to mean. And what it really means is you're not allowed to use them for any other purpose than the purpose that Python wants. It's sort of part of the contract. It's like when you have a dog and you go, what did you think of that television program? And the dog has no idea what you're saying, and then you say, do you want to wait until Saturday to go to the veterinarian? And the dog still doesn't know what you say, and then you go like, how would you like to take a walk? And then the dog goes, walk. I know what that means, and then hits the door, right? And so the way the dog sees you is blah, 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 walk, blah, 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 food, blah, 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 treat, blah, 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 walk. That's kind of how Python looks at these reserved words. When you say class, it goes class. Oh, I know what that means. Now, if I say zap, it's like, oh, zap's something that you get to decide, or it's maybe a variable name. So reserved words are simply words that when you use these words in Python, and there's only a few of them, like and or del, or if maybe, pass maybe, in. A lot of these, you won't end up using them. It's just these are reserved for Python and part of the Python vocabulary. This is Python vocabulary. Now, when we move from words to sentences, you see that Python is a series of lines. A Python program is a series of statements. They have an order because the computer wants to know what next, what next, what next. So what next is start at the beginning. So I already talked about an assignment statement that basically says x equals 2. This is not a mathematical statement. This is a directive to say, take this variable 2, this value 2, this constant 2, and stick it in a location in your memory, and remember that I asked you to name it x. X is a variable, something you made up. You chose that. And so, but it's Python's job to remember it. So this says, go to whatever that x is, there's a 2 in there. Now pull that x back out, add 2 to it, which makes it 4, and stick it back in x. And so that makes this a 4. So x is a 4. And print x says, go look up that thing that was an x and print it out. And so these are like, each line has something to it. I'm using a reserved word. Well, actually, that's a function, but it's a reserved word too. And so there's reserved words and all these things, and you combine these. There are operators. Plus is an operator. Equals is an operator. These things do things, and we'll learn all this stuff in time. So the basic building blocks of lines of Python. Now, as we take these lines of Python and build them up, we end up making paragraphs, programming in paragraphs. And so one of the things that it's important is I showed you how to do interactive Python. So you just type Python and you type a statement and a statement and a statement. Those get really tiring after about 3 or 4 lines of Python because you start making mistakes and you have to start over. So the better thing to do is to, as your program gets a little larger, to write a script. Put your Python instructions in a file and then tell Python to read from the file and then run the script as it's entered in that file. We tend to name these files with .py, and I've got a series of videos that you can watch to figure out how this all works. Like I said, you can type interactively to Python, and it's a great way to experiment with Python, check to see if a statement does what you think it does, but script is the way, after we are past 1 or 2 lines of code, we write it in files and then run it separately. So there are a couple of basic patterns, and it's really important to understand each of these patterns, and like I said, we'll teach you these patterns separately, and then we'll combine them together. And when you combine them together is when you say, oh, that's what a program is. So you have to suspend disbelief. We have a couple of different patterns. One is a sequence of steps. Do this, then do this, then do this. Conditional is like skipping something. Repeated does it over and over and over again. Computers are really good at repeating stuff, much better than people. People get tired going over and over doing the same thing. And then we have store and repeated steps as well. And so if we take a look at this, and we take a look at a Python program, this is a piece of code, this is a little script. If you type this into the code, take this code, Python code, into a file and ran it, it starts at the beginning, and then it goes to the next line, and the next line, and the next line. And Python executes the scripts as you write them. So it says stick a variable to, find a place called in your memory called x, stick 2 into that, okay, then go to the next one, print that out. So the program is producing output. Now go read x and add 2 to it and stick it back in x, so x is 4, then print that. This side over here, this is called a flowchart. I'm not going to make you draw flowcharts. I'm only going to draw them a few times in ways that I think will help you. But you can think of it as Python, when it finishes something, it goes on to the next one, unless you tell it otherwise. Finishes this, goes on to the next one. Finishes this, goes on to the next one. Finishes this, and now the program is all done. And so that's sequential steps. You just type them in, Python runs it. They're important, but sort of uninteresting, because you can only get so far. And you can't really make them intelligent because it's always going to do the next one. So the next thing we do is what are called conditional steps. And this is where it starts to get intelligent. I mean, where you are able to encode your brain into the computer. Like, oh, wait a sec, let's only do this step if something is true. And the syntax that we tend to use here is the reserved word if. Okay? And so the if is like a fork in the road. You can go one way or you can go another way, and you're asking a question. So inside the if statement, right here, there is a question saying, is x less than 10? That resolves to a true or false. If it's less than 10, that's true. If it's greater than 10, it's false. And so then what we do is, if it's less than 10, we have this indented block of code. There's also this colon that tells us we're in the beginning of an indented block of code. And so what it basically says is, if this is true, run that code. If it's false, skip that code. So it can either run it or skip it, depending on this question that's being asked. Now, if you look at this code, it's pretty obvious what's going on. It comes down, x is 5. If x is less than 10, that's true. So it runs this code and prints out smaller. And then it comes back here, it de-indents the next basic sequential. This ends up being kind of a block. If x is greater than 20, if x is greater than 20, oh, come back. If x is greater than 20, this turns out to be false because x is 5, and so it skips this. So the bigger never comes out, and then it continues on and prints fini. Oops, that's a typographical error. Make that a lowercase print, and then prints fini. So it comes in, runs this, skips this, and then finishes. Okay? So here is the last one we'll talk about, the repeated steps. We'll get back to store and retrieve later, but for now we're just going to talk about 3 of the 4. This is another program, and the key is that we're going to use this same choice where we're going to go in, but then we're going to run for a while, and then we'll have an exit condition where we get out. So this is a repeated over and over and over and over again, and this is the essence of how we make computers do things that are seemingly difficult, well, that are more naturally difficult for people. Okay? And so how do we encode this notion that we want to do something not forever, but for a while? How do we encode that notion? And so we do it in this way. So we have our statement, sequentially go to this while. While is a keyword, and it's asking another question that's a true-false question. Is n greater than 0? I read this as long as n remains greater than 0, keep doing this indented block. And you have a colon at the end, and then you have 2 lines of code that's indented. So that tells us what the loop is, and then this is now de-indented. And so it comes in, and if this is true, if this is true, it runs these two lines. Prints out n is 5, and then it says n equals n minus 1, which makes n be 4, and it goes back up, and it goes up and it asks this question again. Is n greater than 0? If it is, continue on, and prints 4, and then subtracts it, and it does that. 4, 3, 2, and prints out 1. Then it comes up, and now after this, n is now 0, and n is no longer greater than 0, so it takes sort of the exit ramp and goes down here. So it takes the exit ramp and goes to here and runs the next line. Now, we're going to cover all this again. So I'm just trying to give you the big picture. Next couple of chapters, we're going to hit all these things again, and we're going to hit them in much more detail with a lot better information. This is now sort of like combining these. And again, I don't want you to really like know this stuff. You will know this in a couple of weeks. You will see this program again. But this shows you how we combine those patterns of repeated, sequential, and conditional together. And so this is a bit of sequential code. Comes in here, runs this, which happens to ask for a file name. Then it opens the file. It creates a data structure called a dictionary. This is all sequential. Now the for is another form of loops. So this is going to loop for a while. And then this is within a loop. We can even have 2 indents, and that's another loop. So these are like repeated. And then it goes down to the next sequential bit. Then it does this. Here's another loop that's going to run, and then here's a conditional it's going to run. And then when it's all done, we print out the last thing. And this is, of course, is the program that does it figures out the most common word and prints that most common word out. And so this is a Python short story. It reads some data. It reads the name of a file. It opens that file. It talks about how to make a histogram. And then it looks through for the most common word. So don't worry too much about this. Over the next couple weeks, we'll fill in the pieces so that you absolutely understand every single line of this code. So, this is a quick overview of Chapter 1. Stick with us. You realize it will be Chapter 7 before this makes too much sense. You really have to trust that you are learning important things and that it all makes sense when we bring it together like in Chapter 7 in a few weeks. Hello, and welcome to Chapter 2. Now we're going to continue to talk about the building blocks of Python: variables, constants, statements, expressions, etc. The first thing we have to talk about is constants. These are just things, we call them constants because they don't change. They're numbers, strings, etc. And we use them to sort of start calculations, or if something is greater than 40 hours, we're going to do something. And so 40 is the constant in that situation. So we have 123, we have 98.6, we have hello world, which is a string by enclosing it in quotes. We pass each of these things to the print function, and a side effect of the print function is that we see the output. So print 123, prints out 123, print 98.6, prints it out. So these are just really the syntax of constants, and without constants we can't write really much of anything. The other sort of foundational notion of any programming language are the reserved words. And like I said before, reserved words are these special words where Python is listening for them, and there are very special meanings. So when Python sees if, it's not just any other word, it means how Python implements conditional execution. Variables are the third building block, and that is a way that you can ask Python to allocate a piece of memory and then give it a name. And you can put stuff in that. Sometimes you just put one value. Later we'll see when we do collections in chapters 8 and 9, we will see that more than one value can be put into a variable. And the variable, how we control the variable is through the assignment statement. And as I said before, it's important to think of the assignment statement as having an arrow to it. So this is not saying x for all time is the same as 12.2. What it's saying is take 12.2, find a place, find some memory in your computer there, Mr. Python, give it a label x, we get to choose the x. That's the variable part. We chose it, right? And then stick 12 in it. And then the same is true for 14. Go find another spot, name it y, and then put a 14 in there. So think of this as an arrow every time you see that equality, the assignment in an assignment statement. Now, these variables hold one value. So now if we have these three statements, these two, and then the third one executes. It says put 100 into X, but that wipes out the old value of 12.2, and it rewrites it with 100. And so we can change the variables. That's another reason that we call them variable. There are some names, some rules for making variable names. You can start with a letter or an underscore. We tend not to, as normal programmers, use underscore. We tend to reserve those for variables that we use to communicate with Python itself. So when we're making up a variable, we tend not to use underscores as the first character. You can have letters and numbers and underscores after the first character, and they're case sensitive, but it's really a bad idea to use case as the only differentiator. So in this case, spam, eggs, spam23, and underscore speed are all totally legit. We would probably not use this one unless we were actually doing it because Python told us to use that variable. 23 spam starts with a number, pound sign starts, and dot is not a legitimate variable character. And spam, capital spam, and all cap spam are different, but this is not something that you want to sort of depend on too much. So that's just the rule names. We tend to start them with a letter and then use letters, numbers, and underscores. Underscores other than the first character are generally pretty common, and you'll see those used a lot. Now, when we're choosing variable names, one of the things about variables is we get to choose the name. We get to choose the name X, choose the name Y. And so sometimes we like them short, but sometimes we want them descriptive. And the notion that of making variables descriptive is often confusing to beginning students. Sometimes it's really helpful to, if you're going to have a line of text and you name the variable line, that's great because the next person reading your program says, oh, that must be the line of text. Whereas it also can become misleading that the name of a variable somehow has meaning. And so sometimes we'll have even singular variables and plural variables like friend and friends. And you're like, is plural? Does Python know about singular and plural? And the answer is no. So sometimes we pick variables that make no sense. Sometimes we pick variables that make a lot of sense. This is just something that you as a beginning programmer are going to have to understand, that we can pick anything we want. And so you'll see, I'll try to call attention to this in the first few lectures as we go through. So here's a bit of code with an assignment statement, two assignment statements, a multiplication, and a print statement. And you can say, what is this doing? Now, Python is perfectly happy with this code because it assigns it in there. You have said, please go give me this as a label. And then we assign two variables, and then we're carefully pulling these two variables back out, multiplying them together and sticking them into yet another variable, and then printing that variable out. That seems like, you know, we can figure out what it is. You just have to look really carefully. And a single character mistake, and Python is going to be, you know, pretty unhappy. Okay? So that's one way to write this program. It's hard though, because any of those characters are long variables and they're random stuff. It's not very friendly to anyone who might read your program. Now this looks a little friendlier. It's the same program because Python just wants a correspondence. You picked A, you picked B, and you picked C, and it's really much easier for us to see what's going on. And so this is, in a way, going from here to here is much friendlier, but we can be even friendlier if we pick mnemonic variable names. So this is not mnemonic, this is short and convenient, this is long and inconvenient. Python is happy with any of these. Here, on the other hand, is another version of the exact same program. And now you think to yourself, oh yeah, now I get it. 35 is the number of hours, $12.50 is the rate, and then we're going to multiply the hours and the rate and come up with the pay, and we're printing out the pay. Now whoever wrote this program is helping us greatly understand what's going on. And that's good. Choosing variable names. Python, again, all three of these are the same to Python. Choosing variable names in a way that help your reader understand what's going on is a great thing. The problem is, the danger is, if you read this and you think that somehow Python understands payroll, that if you name a variable hours, that Python knows what hours means. The answer is, Python really doesn't care what you name the variable as long as what you name it, you use it, right? And so you got to be careful. And so you'll see, when I write my code in these first few weeks, first few lectures, I will sometimes write it with gibberish. I'll sometimes write it with extremely short but meaningless variable names. And sometimes I'll use meaningful variable names. and I'll call your attention to it, and it will get you. You'll start, when you look at this third kind, it has meaningful variables or mnemonic variable names. You'll just instinctively want to give Python more intelligence than it sort of deserves. I guess that's probably the best way to say that. So we've talked about constants, we've talked about reserved words, we talked about variables. And so here we have a sentence, like we've already done some of these things, where we set x equals 2, we retrieve the old value of x and add 2 to it, so that becomes 4, and then we print 4 out. Print is a function that's built in, and we pass in whatever we want to print out. So this parentheses is part of a function call. Okay, so an assignment statement, you have to really get your head around the notion that it has this arrow nature, and that it evaluates this entire right-hand side before we change the left-hand side. And so you can think of this sort of as at time step 1 it does this, and then at time step 2 it does the copy. And that's how you can have something like x on both sides of an assignment statement. And so if, for example, we have x and x has 0.6 in it, what happens is that it sort of ignores this part right here and evaluates the expression. So it pulls the 0.6. Everywhere x appears, it pulls 0.6 out. Then it starts running these calculations, and then it has the new value. After all the calculations are done, then and only then is it going to put that back into x. And so it sort of takes that and puts it back into x, and then wipes out the old value. At this point, this has all been taken care of, and it's been reduced down to this 0.93, and so that is what's put in as the new value. So, up next, we'll talk a little bit more about making more complex expressions. So welcome back. We're now going to talk about expressions. Expressions are a little more complex calculations that we can sort of do on the right-hand side of an assignment statement. So one of the things about expressions is operators. And the operators in computer programming are often very much the same as the mathematical operators, but we don't have all the fancy characters that we have in mathematics, and so we have to choose what's on the keyboard. And then we really go back to the 1960s and 1970s, and we used what was on the keyboard in the 1960s and the 1970s to make these operators. So plus is addition, minus is subtraction. We don't have a times sign or a dot in the middle, so we use the asterisk as multiplication. Division, we can't put two things over top of each other, so we use slash for division. Raising to the power, because it didn't have little characters back then, is star star, which is raising to the power. And then remainder. Remainder is when you do integer division, it's also called the modulo operator. It's the remainder, not the quotient. And I've got a picture of that coming up. So here's a whole series of little examples of this. Right, so we've already seen, the plus, x equals x plus 1. Keep remembering that these assignments are arrows, basically. Arrow, arrow, they have a direction. Multiplication, 440 times 12. Dividing this by, that's division, over 1,000, 5.28. Here we're going to put 23 into JJ, and then we're going to do modulo. So that says, take 23, divide it by 5, and give me back the remainder and put it in KK. So this is the expression that evaluates like this. Take 23, divide 5 into 23, 4, remainder 3. The 3 is what comes back up here. Okay, and so that is the remainder. It's also called modulo operator. It turns out that for things like picking a random number and then taking the modulo of 52 is a way to pick a card randomly. So this modulo operator is actually, especially in games and other things, super useful. So that's the various operators. It's important to know which of these operators goes first. That's called operator precedence. Now normally we put parentheses in, like, so if I put the parentheses in here, I'd say this goes first, parenthesis, then this goes first. Oh, actually not that one. Whoops, got that one wrong. This happens first, this happens, then this happens. Okay, and so, but it's important for us to be able to know, if there were no parentheses, the order in which these things will happen. So the way things work in terms of operator precedence is parentheses are the most important thing, followed by raising to the power, all else being equal, multiplication and division are all both equal, and then addition, and then within it's adding left to right. So let's see an example of how this works. And so if we take 1 plus 2 to raised to the 3 power divided by 4 times 5, and we print out what comes out of this. So the way I did this when I was taking exams back many years ago when I was first in computer science is I'd write it all down and I'd look for the highest precedence thing. Now parentheses would make this easy, but exponentiation is the first one. So that means we're going to take this, and that's going to be 8. 2 to the 3rd power, 2 times 2 times 2, 2 cubed is 8. Then what I would do is I rewrite the whole thing with the 8 there, and now I look across and I'm looking for multiplications because the power's been done, the multiplication is what I'm looking for next. And then there is both multiplication and division. They're equal, they're at the same level. And so what happens is they're done left to right. 8 divided by 4 happens before 4 times 5. And so the fact that it's not 4 times 5, but instead 8 times 4 is because of the left to right rule. So then this gets rewritten to be 2, 1 plus 2 times 5, and this one, multiplication, is the top one, so that does this next. 2 times 5 becomes 10, I rewrite it again, and then 1 plus 10, addition, is the lowest thing, and that's how we end up with 11. And so that's how I would do these problems if I ever saw the problem on an exam. And it's a fun problem to put on exams because there is one and only one answer, and every programming class has usually at least one slide about this stuff. So like I said, the rules go top to bottom, parentheses, power, multiplication, addition, and then left to right within it. So we talked about variables and computing values to put inside variables, but the one thing you've kind of also, maybe you noticed it as we go by, is we have different kinds of data. We call it type. Is this of type integer? Is this of type floating point number? Is it of type string? What is going on here? And Python is pretty smart about various kinds of types of data. And so, you know, we're adding 1 plus 4 here, and Python knows as it looks at this that that's an integer and that's an integer, and we'll add it together and make it an integer. So that thing is an integer. We can also use this plus to concatenate two strings. This is hello blank plus there. And plus looks here, says, oh, that's a string and that's a string. So I know what to do with strings. I will concatenate those two things together so it becomes another string that gets assigned into EEE, and it's hello space there. The plus doesn't add the space. I added the space by putting it right there. And so these operators are kind of smart in that they kind of know what they're dealing with, and sometimes they will do one thing or another depending on the kinds of values, variables, or constants that they're working with. And so sometimes type can get us in trouble. So here we have EEE, which is hello there because we've concatenated these two strings together. And now we're adding 1. And the problem now is that it looks on one side and says that's a string and that's a number, and says I don't know how to do that. This is another one of those annoying errors that you think that somehow Python doesn't like you, but it just is confused. If you look at these things, traceback always means I quit. It means I stopped, I ran, I'm quitting now because I don't want to go any farther because I've become confused. So your program stops running and you say, here's where I stopped running. Because we're typing interactively, it's always line 1 here. Type it, but if you read carefully and you don't get too stuck on too much stuff, line 1, that tells us something. In module type error, can't convert int object to str implicitly. So that's an integer right there, and that's a string, and that's what it's complaining about, that little bit right there. If Python is so grumpy about types, then we should be able to ask it about types. So there turns out that there is, inside Python, a built-in function called type, T-Y-P-E. So we can pass into type. So the syntax is calling a built-in function named type, parenthesis is the parameter that we're passing to it. We're saying, hey, hello, tell me something about the type of the variable EEE. And so this is a function, the parentheses are part of the function call, and it says, oh, that would be of class string. And then we can pass in a constant and says, hey, what about hello? The string hello, it's like, oh, that's a string too. What about a 1? Well, that's an integer. And so we are asking Python through the type function what the type of either a variable or a constant is. And there are even several types of numbers, and we'll even see Booleans and others later. Like 1 with no decimal, that's an integer number. 98.6 with a decimal, that's a floating point number. And so, you know, constants and constants can be both integer and floating point. And I'm just asking over and over and over again, what is the type of what's in XXX, what's the type of what's in temp, and what's the type of the constant 1, and what's the type of 1.0. You can also use a set of built-in functions like float and int to convert from one to another. And so this basically says, I want to convert, oops, let's go back. I want to convert 99 to a floating point number. So this is a function and it's participating in this plus, but before it can finish the plus, it turns this into a 99.0. The difference between 99 as an integer and 99.0 is that it's a floating point number, and that actually turns this computation, as it looks to the left and looks to the right, it says, oh, I've got a floating point number on one side and integer on the other side, and so I'm going to make my calculation overall be a floating point calculation. I can also pass into the float function. I can say, take this variable I, which has a 42, also an integer, and then give me back a floating point. So that'll be 42.0. Pass that into f. We print it out, and it is indeed 42.0, and it's a float. And so it knows the type and value in any variable. This is an integer, a value 42. This is a float, a value 42.0. Integer division in Python 2 was kind of weird, and it was actually one of the big things that they changed between Python 2 and Python 3. This is a Python 3 course, so we're not worried about that too much. What's nice about integer division in Python 3 is it always produces a floating point result. And that means that Python 3's division is more predictable, and it works more like a calculator. So in this case, I mean, you can go back and look at my Python 2 lectures and see how crazy it was in Python 2. 10 divided by 2 is 5.0. And the weird thing here is these are both integers, but the division forces the result of the calculation to be a floating point number. And this, 10 over 2 could be 5, but 9 over 2 is 4.5. And so that is accurate. In old Python 2, that would give us back 4, which is completely unpredictable and weird. The same with 99 over 100. As you would expect, if this were a calculator, you get 0.99. Actually, what you get in Python 2 is 0, because it would round it down. It doesn't round at all, it truncates it. So 99 over 100 is 0.99, and then it truncates it to 0. That's Python 2. We're not talking about Python 2. There's a good reason we're not talking about Python 2. Welcome to Python 3. Of course, if there are a floating point on either side, the result is still a floating point, and the result is still a floating point. So integer division produces a floating result in Python 3.0, not in Python 2.0. That is an improvement in Python 3.0. And that's why we're recording these lectures. I have a whole great set of lectures about Python 2, and now I'm going to have a great set of lectures about Python 3. Welcome to Python 3. Okay, so we've been talking about converting from integer to floating point, but you can also convert from string to integer or string to floating point. And so here we start out with a little string value. Now it only works for strings that are made of digits. So quote 1, 2, 3 quote is not an integer. It is a 3-character string that has 1, 2, 3 as the characters in that string, which is very different than 123. We say, what is the type of this? It's a string. We say, let's add 1 to it. And it says can't convert into string, so that blows up, right? Because this is a string. It looks to both sides. String plus an integer, not good, okay? But we can convert this. We can call the int function, which is like the float function, and pass a string in. So it says, hey, take this and turn it into an integer. So take the input of sval, which is the string 1, 2, 3, and give me back an integer representation of that, which is going to be 123. So we say, what kind of thing do we get back? Well, we got back an integer. We can now add 1 to it and get 124. And so you have to manage the type of things, and you can convert from one type to another. Now, int is not magic. If you send something into it, a string that doesn't consist of digits, then you're going to end up with another error. Invalid literal for integer with base 10, blah, 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 blah. So it's really complaining. It says, I want these to be numbers here, and you just gave me letters, so that's going to cause this to fail. Another thing that we're going to do with variables is, just like the print function takes something, a list of things, in this case, a string, comma, a variable, and then prints some output in the program, the opposite of that is input. Actually, input generally happens before output. Input is a built-in function, and we pass to it a prompt, a string of text that's going to be printed out for the user, and then it stops and waits. So it says, who are you? And then right here it just sits, waiting for us to type something. So we type blah, 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 and then hit the enter key. Right? We hit the enter key, and then this text ends up in this variable. So this is an assignment statement that Chuck is the result of the input call, gets copied into the NAM variable. So let's do that again. It's evaluating assignment statement. Remember, it's kind of this way, or you can think of it as just do this right side first. It writes this out, writes that out, then it waits, wait, until we hit the enter, and takes this Chuck, and that becomes the result of this input, which is then assigned into NAM. Now then we go sequentially to the next line. It prints out welcome, comma, contents of the variable NAM. Now this one, this comma here, actually does put the space in here automatically. So it says welcome space Chuck. So it pulls there's no space in Chuck, just the CHUCK. And so print can take more than one thing separated by commas. As a matter of fact, print can have, you know, a whole bunch. Oops, come back. Print can have comma, 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 parentheses, as many as you like. Everything you've seen up to now is kind of one thing in the print, but that doesn't mean that print only can do one thing. So I've talked about variables, we talked about constants, we've talked about input, we've talked about output, and now it is time to write our first meaningful program. And so this program has to do with those of you who have traveled internationally. If you traveled to the United States and you traveled outside the United States, you notice that there is an elevator convention that is different inside the United States. In the United States, walk in the ground floor in the elevator, that's 1. And if you walk in the ground floor in Europe or many other places in the world, in the elevator is 0. So we have written a small app that we're going to put on the App Store and get wealthy with called Elevator Floor Conversion App. And it's going to ask us, we're in Europe and we're lost, and you say, well, what floor would this be if I was in the United States of America? And so we have to read the floor that we are in Europe, and then we're going to convert it to a US floor, and then we're going to print it out. This is very silly, but it is a pure essential program that has input, does some kind of task on that input, and then produces some output, which is useful for some value of useful, okay? So let's take a look at how we combine everything that we've learned in this lecture, input, processing, and output. It's a 3-line program, but it's sort of the beginning of something that programs do, okay? You're going to do lots of programs that do this. So here we go. Program starts, we do the input, side effect, it prints out this and then waits. We type in 0, that comes back here, and the 0, which is a string. Input gives you back a string. It doesn't give you back a number. It's a little different in Python 2, but in Python 3, input gives you a string. So quote 0 quote, which is what we typed here. We didn't type the quotes, it's a string, gets stored in the imp variable. Then we move to the next statement, and on this right-hand side, we convert that string variable to an integer, so that becomes the integer 0. We add 1 to it, and then that becomes 1, and then we assign that into USF. I've named this variable United States floor, right? So imp is the input and USF, that's mnemonic. It doesn't know anything about elevators, it's just I picked a variable that was quite friendly. And so at this point, USF has the United States floor that's equivalent to the European floor, and then I just fall down and I do a print statement. Print out US floor, comma, that's this space right here, and then whatever the contents of the US floor variable is. And you could see that I could write this on 4, and it would say 3. I could write this and say 7, and it would say 6. This is an amazing program. It converts floors in a European numbering scheme. Wait, actually no, I got that wrong. Hang on, let me clear this. I wasn't thinking clearly. I could type in 4 and it would give me back 5. I could type in 6 and it would give me back 7. See, I'm confused. Haven't been in Europe in a couple of months, and so I forgot all about the floors. But that's the idea. Now, this is a super simple program, not super useful, but you get the idea that we're going to pull some data in, we're going to do some intelligent thing. Soon this will be hundreds of lines of code instead of 1 line of code, and then we're going to present the results to our user. Now, another element of most any programming language is what's called a comment. A comment is a way for you to put in a program file some text that's to be ignored by Python or C or whatever language we happen to be using. In Python, comments start with a pound sign. So what you could do is put a pound sign anywhere in a line, and then after the pound sign, Python ignores everything after that pound sign. It can be the first character. So here's our recurring concept that we talk a lot about. We're not going to cover this. Remember what this does. This is counting how many letters. There's 16 thes, and there's in that file there was 6 2s or whatever it was. This is that code. We'll get back to this code. But what we've done here is I've added some comments that are really for human consumption. So this first paragraph is get the name of the file and open it. The second paragraph is count the word frequency. Maybe I should have said histogram here. Count the word frequency and assemble a histogram. And then here I'm putting this pound sign in, find the most common word, and then I'm all done. I print the stuff out, right? And so all I'm saying is comments are for people to read. Your next programmer or the person who's going to change your program after you're done with it. And they're nice, and you don't have to use any particularly weird syntax or variable naming conventions. You put a pound sign in and you can write anything you want from that point forward. Okay, so we've talked a little bit about variables and types and mnemonics and how we would choose variable names and how expressions work and the various operators, converting between different types, printing, input, output, and comments. So that just kind of gets us sentences. And coming up next, we'll talk about conditional execution, where we're really starting to move up to paragraphs. So see you in a bit. Hello and welcome to Chapter 3, Conditional Execution. In conditional execution, we meet the if statement. The if statement is where Python can go one way or another way, and it's the beginning of sort of our way of making Python make decisions for us. Sequential code, we just do some things. Sometimes that's useful, but now we can have our code check something and then make a decision based on that thing. So the conditional steps in Python are pretty straightforward. The keyword that we're going to use is the if statement. And so if is a reserved word, and the if statement has as part of it a question that it asks, and this is asking if x is less than 10. And the colon is the end of the if statement, and then we begin an indented block of text. And the way this works in this particular thing is this line is the conditional line. If the question is true, the line executes, and if the question is false, the line is skipped. And you can think of it the way this is, right? X is 5, ask a question, is it 10 or not? These questions do not harm the value of x. If it is, then we run this code, and then we sort of rejoin here, and then we test this next if, and if that's true, we do this code, and then we do there. But in this case, it's going to be false because x is not less than 20, and so it just continues down here. So if we look at how this works, it runs this line, then it sees this question, it skips that line. So this line does not run, and so smaller prints out and fini prints out. Okay? And so that's the basic idea of an if statement. And the indentation, when we are done with an if statement, we de-indent back, and there's this little block. This is one sort of if statement, and this is another if statement. And these are the two conditional lines that either run or they don't run, depending on the question, the answer to that question. So we have a number of different comparison operators that we can use to ask these true-false questions that say, is this true? So again, we're kind of limited to the keys that were on computer keyboards in 1940s and 1950s, less than or equal to. So we didn't have fancy math characters, so we just concatenated less than and equal to be less than or equal to. This double equals is the asking, is this equal to? And so that's a little tricky. The equal sign is that assignment operator. If I was building a language today from scratch, I would probably make assignment be arrow and the equals question to have an equals. Or I might say, somewhere I would say question equals. But I'm not building this language, so it's not up to me. So this is the question. Double equals is asking the question is equal to. Greater than or equal, greater than, and not equal. So this is the exclamation point is sort of like not equal. So that's sort of not equal. So that's how we do not equal. So if we take a look at some of these in some examples. All of these are going to be true because of the way x is set. If x is equal to 5, that's the question version. That's true or false. It'll execute that. If x is greater than 4, it's going to execute that. If x is greater than or equal to 5, it's going to execute that. Here's kind of a shorthand where if there's only one line in this block, you can kind of pull it up right on the same line after the equals. If x is less than 6, which it is, true, execute that. Then if x is less than or equal to 5, do that. And if x is not equal to 6, do that. Now, like I said, all these questions have been carefully constructed so that they're true, just to kind of show you the syntax of those comparison operators. Now, you don't just have to have a single line of text in the indented block, and this will be something you're going to get used to. So if we indent more than one line, then the conditional code is actually these 3 lines. So the idea is you have an if statement, you come in, you do an indent, and as long as you stay indented, you stay in that if block. If it's false, it just skips all of those. So the way this is going to execute, x is 5, we print before 5, is x equal 5? That's the question mark, and that's true. So it's going to run all these, and then come back, and then continue on in the de-indent. So all this stuff is running, right? And then it says x equals 6. Well, that was false, so that skips all of them. So none of these lines of code run. So these actually don't run, and it says afterward 6. So that's a mistake. Those don't run right there, okay, because x is not equal 6. Okay? So indentation is an essential part of Python. We use indentation in lots of programming languages, often to kind of demarcate blocks, to show where blocks start and stop. But in Python, it's syntactically correct. You can make an error if your indentation is wrong. After an if, you must indent. And you maintain the indent as long as you want to be in that same if block. And then when you're done with the if block, you reduce the indent. In this rule of indenting, comment lines and blank lines are completely ignored. So we're going to tend to like put 4 spaces. 4 spaces ends up being the normal thing that we do, and you'll see all the code that I write has 4 spaces for each indent. If I go in twice, I use 8 spaces. And we have this instinct of wanting to hit the tab key to move in 4 spaces. Now the problem is that it might look the same on your screen. A tab and 4 spaces might line up the same place depending on how tabs are set. But Python can get confused by that. So we tend to avoid using actual tabs in files. And so most programming text editors, like if you're using Notepad or Text Wrangler, there's a place to set the tabs, to say don't put tabs in this document, but every time you hit a tab, move over 4 spaces. And so you hit a tab, but it's like space, 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 space. Now the nice thing about Atom, and this is the text editor we tend to recommend in this class, because it works on Windows, Linux, and Mac, but also because it automatically sets this up. As soon as you save your file with a .py extension, you can sort of hit the tab key with impunity, and everything works perfectly. But the key thing here is that Python insists that you get this right, and if you don't get this right, you're going to get indentation errors, and they're just another syntax error. So if you're using something like Text Wrangler or Notepad, hunt around in the preferences and you'll find something about expanding tabs, or maybe how many spaces each tab stop is supposed to be. And so you check these, and what this really is doing is telling your text editor never put an actual tab in the document, but somehow simulate tab stops using spaces. And so here is a bit of code. It's got a nested block, but it gives you this sense that you have to be very explicit when you're reading Python code of whether the indent is the same, between 2 lines the same, increased or decreased. And so every time you increase it, you mean something, and every time you decrease it, you mean something, and literally if it stays the same, you mean something as well. And so if we take a look at this, here we have a line, and the next line has the same indent. This is an if with a colon at the end, so we have to increase the indent, and now we're maintaining it, okay? So these 2 lines are part of that if, but now we have de-indented. So whether you choose to de-indent this word or whatever, where you do this de-indent affects the scope of how far this if statement lasts, right? It lasts up to, but not including, the line that's de-indented to the same level as the if. Okay, so this is a de-indent. Now we have a blank line, which doesn't matter, and we maintain it. Now we have a for, which we'll learn about in the next chapter, which is a looping structure. Let's do a for runs this 5 times. It has a colon, and it also expects an indented block. Now we have what's called a nested block, where we have an if and a colon, and we go in some more. So this is like 2 indents, right? So these are 1 indent, and these are 2 indents. And so this is a block within a block. And then we de-indent, so that means this print is not part of the if statement, but is still part of the for statement. And then we de-indent again, and then that means this print is sort of on the same level as that for statement. So if you start thinking about this, you want to be able to start thinking that these blocks are the start of the block with the colon line up to but not including this line that's been de-indented. So the for goes this far, right? The for goes up to but not including the line that's de-indented. The if goes up to but not including the line that's de-indented. So as you do this, you'll sort of mentally start drawing these blocks, and pretty soon you will start constructing them as blocks. And it takes a while, but doesn't take forever. But in Python, unlike other languages, in Python, unlike other languages, you have this is very important, and it matters, and you can have syntax errors if you get it wrong, because you're really communicating the shape and structure of your code using these indents and de-indents. We already saw a nested indent. This is a nested if, so you can put an if within an if, and you can go as far deep as you want to go, like Russian dolls. And so here we have x equals 42. If it's 1, we indent 1, and then with this next thing we do, these are at the same level of indent, but now we see an if, and it has to indent further. So this is like 2 in, 8 spaces, and then we de-indent back. Actually, we de-indent back 2. And so if you watch this and you take a look at how this works, it runs to here. Oops. Back up. Comes in here. The answer is yes, x is greater than 1. Prints this. Is x less than 100? Well, it's 42, so the answer is yes. So it runs this, and then it kind of continues back to there. And you can also think of drawing boxes around this. This is one if box, and then within that if box there is another if box. And again, it's the indent block up to but not including where the de-indent happens. And this here is like 2 backwards de-indents. So it ends 2 blocks. So 2 blocks are ended by where we place this. We could move this in, or we could move this out. We could have it all the way into here, we could have it to here, or here. And where we put that line depends on how the ends of these blocks are going to work out. So one form of that's a 1-branch if that we just saw, but then you can also have what's called a 2-branch if. And the basic idea of a 2-branch if is that you're going to come in, you're going to ask a question, and you're going to go one direction if it's yes, and another direction if it's no. We call this an if then else. It's kind of like a fork in the road. And the way to think about it is, depending on the output of this question, we're going to pick 1 or 2 of these, but if we pick one, the other one's never going to happen. So it's like an either or. We're either going to go one way or we're going to go the other way, but there is no path where we somehow go boot through both of them. That doesn't happen. And the syntax that we use for this is what we call the if then else. And so the first part is a normal if with an indent, and then we de-indent, and then this is another reserved word, else, with a colon, and then we re-indent. And so this is really end up being part of a whole block here, and the else is the part, this is the part that runs if it's false, and this is the part that runs if it's true. The first branch of the if, the first indented block is what runs if it's true, and the second indented block is the one that runs if it's false. And so here we go, just if x is greater than 2, in this case it's yes, we're going to print bigger, and then we're going to be all done. And so we do 1, and so this one did run, and this one did not run. So basically with an if then else, one of the 2 branches is going to run, but there's no case in which both branches run. And again, you sort of draw these blocks around these things mentally, and in this one you sort of take from the if, not the else is really part of the block, up to but not including that print, which is back indented, de-indented back to the same level as the if statement. Okay? This Python is actually one of the more elegant languages, even though after a while this indenting and when you get too far in it gets a little bit complex, but this is a good way to visualize this with these indents. Coming up next, we're going to talk about some more complex conditional structures. So welcome back. Let's talk a little bit more about some more complex conditional statements that sort of build on this concept of if and if then else. The first thing we're going to look at is the multi-way branch. And so the idea is it's kind of like the if then else where you're going to pick one of two, but now we can pick one of three or one of four or one of five. And it introduces a new concept called the LF. The LF is another reserved word inside Python. And the way it works is it's probably best to look at this here where it checks the first one, and if it's a true, then it runs that, and then it's done. It doesn't check them all. It's not like it sees that there are two logical conditions. It actually checks them, the first one, and how you order these matters, as we'll see in a bit. And so if the first one is true, it runs. If the first one is false and the second one is true, it runs this one and it's done. And if the neither of them are true, it falls through, and there's an else clause that is otherwise, and it runs that. So basically, it's either going to run one and then skip the other two, or it is going to skip one, skip two, and then run this one. But it only runs in this case one of them. But the important thing is it checks these questions in order, and it doesn't check the second question until it finds that the first. It doesn't check the second question until it knows the first question is false. So if the first question is true, you're done. You're done, and you're done with this. You're done with the whole block at that point. So only one of these three is going to execute in that block. So here's sort of some examples of this. If we, for example, have x equals 0, it's going to come down here. X is less than true. That's true. So it runs this code, and then it skips down to that. And so it's like this. Runs that code and then skips to the end. Okay. On the other hand, if it's 5, then this is false, and it skips that, and it checks this. This is true. It runs this code, and then it's done, skips to the end. It goes like false, true, run, end. And then if x is like 20, for example, it runs, false, false, run the else clause, and you're done. So skip, else, run that code, and you're done. So in this case, we ran that, and we didn't run that, and we didn't run that. Again, one of them's going to run. They're checked in order. These questions are checked in order, not out of order. It doesn't look ahead. It just checks in the order that you wrote it. You're the one that wrote that order. And so there's a couple of variations on this multi-way. You can have no else. You can have no else, as in this case, and this just means that it might not run any of them. In this case, x is 5, so it's not less than 2, but then it runs this one. But if x was like 50, for example, if x was 50, then this would be false, then it would skip, and this would still be false, and it would skip, and neither of these two would run. So if you don't have an else, you're not guaranteed that one of them is going to run, because else is like the catch-all. If the other ones are all false, then the else is the one that runs. Similarly, you can have many LFs, but this is where it's really important for you to make sure you know what order they're being taken in. So I've got, this, if this is true, it runs, it goes all the way to the bottom. If, if it's false, 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 true, it runs this one and it's done. If, on the other hand, it looks at it as false, oops, go back. If it runs false, 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 they're all false, then it runs the else. Right? This one has an else, this one didn't have an else. They don't have to have them. The key is you can have more than one of these LFs. Okay? So I got a couple little things. I'll let you pause right now and look at, the question is, are there, looking at the 3 lines or 4 lines of code, x equals something. Are there lines of code that will never execute regardless of the value for x? And I'll let you pause and think about it, and then I'll explain it to you. Okay, Hopefully you paused and thought about it as long as you like, but so let me now explain it to you. So we come in here, and if x is less than or equal to 2, it's going to run this first thing, and if x is greater than or equal to 2, it's going to run this, and if neither of those are true, then it's going to run this. Well, the weird thing is, all numbers are either less than 2 or greater than or equal to 2. I carefully constructed this to the point where it would never run this line of code. It is either going to run this one or run that one, but it's not going to ever run this one. So that was kind of like a weird dysfunctional one that I constructed. This other one is a little different. If x is less than 2, we do this. If x is less than 20, we do that. If x is less than 10, we do that. And if none of those are true, we do that. Well, the problem here is between these two lines. The problem is if something's less than 10, like 6 for example, it's also less than 20. So even though there might be values for which this is true, those also are going to have this true. So for something like 6, it's going to run here, and it's not even going to look at this. That's the point. It doesn't even look at this. And so I could have made this more sensible if I'd have moved this little block of code up to there. So this is where the order in which you choose your questions, the way you put these LFs together matters, because it doesn't look at all of them. It only looks as long as it can. As long as it sees falses, then it keeps on going to the next one. But as soon as it doesn't see a false, it doesn't continue. So the last conditional structure we'll talk about is the try and except structure. And if you know any other languages like C++ or Java or JavaScript, you're like, whoa, that's kind of an advanced concept. But it turns out in Python, because of Python's propensity to throw tracebacks in situations where you kind of would like to recover, it turns out you kind of have to use it a little more and a little earlier in your programming skill. So the problem is what if there is a line of code and you absolutely know it's going to make a traceback, it's going to blow up, but you don't want to blow up. I mean, I don't want to have code blow up. If you're using my autograder and you see a traceback in my autograder, that's kind of like, I consider that a failure. I could put an error like, hey, you entered blank data, or you didn't enter a number, but a traceback, that just seems like I'm too lazy as a programmer. So we as programmers are supposed to anticipate parts of our code that are going to blow up potentially based on perhaps the user's input, and then do something about it. And that's what the try and except are for. It's you take this little dangerous piece of code that might break and might blow up, and you surround it with a try and says this might blow up, and if it fails, run this code down here. Okay, so that's the try, and if you get an exception, the except is kind of like if you get an exception. And the problem is if you are running code, here's a little bit of code, we put hello Bob in, and then we convert it to an integer, and we know from past experience that this blows up, right? You can't take hello Bob and convert it to an integer, it's just going to blow up. The problem is, and here we are, it says, oh, you blew up on line 2, that's great, and I'm not very happy with hello Bob, and whatever. But the important thing is your program stops. These other lines, they don't, oops, these other lines, they don't exist. Right? It doesn't go any further. Remember, the traceback is Python is really confused and I don't know what to do next. So Python is just going to be conservative and stop. So Python stops and your program stops. No matter how much error checking you put down here, it doesn't matter because it's gone. It's all gone. And like I said, we take this kind of personally because the code that you write is like you being put into the computer, giving it instructions. And if the code blows up, well, that sort of wipes you out. You're not in the game anymore. You're not able to do anything. So we want to be able to, especially in these situations where we can anticipate that an error that might happen in the normal course of your program's execution might be something that you want to compensate for. And that's what the try and except does. So here's a bit of code for the try and except. And we just have two little bits of straight line code. And so we put a string in here that's hello Bob, and then we're going to convert it to an integer. This is the dangerous code. This code, in this case, with hello Bob, is going to do a traceback. And so we say try, and then we indent the dangerous code, and then we add this little except bit. If it works, the except is ignored. If this blows up, it runs the except. So in this code, it's going to come in, it's going to try this. This is going to blow up. But instead of giving a traceback, it's going to say, oh, I've got an available except. I'm going to run this except code, and then I'm going to continue on. And so that prints out first -1. So because we set this variable Eyster to -1, like a little flag telling us that something went wrong. And then we keep on going, and now we have put in 1, 2, 3, the digits 123, the digits 1, 2, 3, and now it's going to work, but we still have it in a try block, and then this one works, it does not blow up, and then it ignores the except block. So the except block is only triggered when something goes wrong in the code. It is ignored if something doesn't go wrong. So it's like you bought an insurance policy on this line of code, and when things go wrong, your except block springs into action and does whatever it is that you want it to do in the case of an error. Okay, so that's a pretty useful thing. You got to be a little bit careful that you don't overuse it, because if you put more than one line inside the try part and one of the lines blows up, it doesn't come back to the try block. And so in this one here, we have kind of a simple, silly one where we set the string. We're worried about some stuff. Well, the print statement's never going to blow up, so it's a bad idea to put it in try except anyways. Then we do this conversion, and that's the dangerous part. And in this one, it's going to blow up. And so then it's going to go to the except block and then run the except block and then continue. What it doesn't do is somehow go back and finish this. So these lines are gone. So if you look at it like this works. The try starts. Hello. This blows up. It goes to the except. It runs the except and it continues on. Never runs that code. So it's not like you took out an insurance on the whole block. Any of those lines can blow up in the block, but whichever line blows up, that is the last line that's executing in that block. Okay? So you tend to want, in this particular example, you would probably, the print statement would go out there and this print statement would come down here, and you would only put in your try block the single line of code that you think might blow up, because you kind of know print statements aren't going to blow up. So this is an example that's a more common real-world example where the user is going to type some data. And it's users that get us in trouble. So our program starts by asking the user to enter a number, and we know that this could be dangerous. So we're going to do it. We're going to put the conversion from string to integer in a try block, and we're going to set -1 if that's a failure. And then if it's greater than 0, we'll say nice work, and if it's less than 0, well, not a number. So first time we run this program, out comes enter a number. We type in 42, which is a string. That 42 goes back into roster, runs in here. This runs. It's fine. That becomes a 42 number, so we skip the except block, and ival is greater than 0. We print out nice work, and we skip the else. Okay? So it says nice work. On the other hand, if we run it again, this time, the input says enter a number, and we're silly. We enter the word 42, but in words, 40, F-O-U-R-T-Y. So that's a string, and that goes into roster. And then the execution continues. We run in here, and now this is going to blow up. That's going to blow up. Normally, we would see a traceback right there. There'd be a traceback. But we're not going to, because we put this calculation in a try and except block. It's going to immediately run the except block, set ival to -1, continue on with the program. See, you are not blown up at this point. And if ival is greater than 0, well, it's -1, so we're going to hit the else clause and print out not a number. So we've done error detection. The user set something that caused a line of our code to kind of blow up, but we put that line in a try and except block, and so we caught it. And so we dealt with that fact. So in summary, in this, we talked about if statements, we talked about else, we talked about try and except, how important indentation is to mark blocks where they begin and the end, and an else if and try except. So up next, we're going to talk about loops and iteration. Hello and welcome to Chapter 4, Functions. This is the fourth of our basic patterns. We'll get to iterations next. Functions is the store and reuse. One of the things in programming is that we never like to repeat ourselves. We don't like to, if we have 4 or 5 lines of code and we're going to do the same thing later, we don't like to put the same 4 lines of code in, even if it has to do with reliability. If you find something wrong with those 4 lines of code and you got them 12 different places in your program, then you got to find all 12 places and fix them. So we're like, collect those to one place and then call them and reuse them. And that's the idea of store and reuse. So this is how functions work inside of Python. The first thing we notice is there is a new keyword def that stands for define function. And the def is like an if statement, or we'll see fors and whiles, that they end in a colon, and then they have an indented block, and then the indented block de-indents, and that's the end of the function. And so there's two statements make up this function. The key thing that you have to understand and get used to is this def part is actually not running any code whatsoever. It's actually remembering the code, and that's what I call the store phase. The def creates a bit of code and records it like a macro, although it's much more complex than a macro, and it names it whatever you chose. You gave it a name. We named this one thing. And so it, as a side effect of Python reading or parsing these 3 lines, it doesn't do anything, but it remembers. These 2 lines are what you would like to run when you invoke thing. So this is the definition of a function, and this is the invoking of the function. But so this doesn't do anything. So there's no output here from that stuff right there. But then what happens is you invoke it. And this thing looks like it's part of Python, but you in effect have extended Python with your def statement. And so when it sees thing, it goes up and runs your code, and so out comes hello fun, and then it comes back and goes to the next line, does print, so print comes out, and then it goes back and like, oh, this is the reuse part, but we get to reuse it. We define it once and we use it twice. Then it runs this code again, and then goes to the next line, and it's all done. So this little bit came out twice. And of course this is really simple so that I can fit it on a page, but you get the idea that I don't want to repeat. This might be, 15 to 100 lines of code, and I don't want to type those over and over again. So I say, hey, store these in a name that I choose, and then when I invoke them, bring them back and then run them again. Okay? So that's the basic idea. We actually have already been using functions from the beginning. The print is a function, right? Print is a function. Every time we see print, P-R-I-N-T, parenthesis, and then we have some stuff in here, we are calling the print function. This is the syntax with 2 little parentheses, is the syntax for functions. And so input's a function, type is a function, float's a function, int's a function. All these things are built-in functions that come with Python at the moment that we started. I mean, we installed Python and these came along. And then there's other functions that we define and use, and that's what the def is for. And in effect, we can create new reserved words of our own making that extend the Python language after we define the function. So it's just this bit of reusable code that takes some arguments. We haven't seen any with arguments. There's a little parenthesis, and we'll see how that works in a bit. We define using the def keyword, and then we invoke it. There's the defining phase, which actually doesn't run the code, it just remembers the code, and then there's the invoking phase. You define it once and then invoke it 1 or more times. Calling the function or invoking the function, we think of those 2 things as the same thing. Call, invoke, or just the terms we use. Most people just say call the function, but invoking it is a perhaps more descriptive way to think about it. So here's an example of a function. It is built into Python. It's called the max function, and we can pass some parameters into the max function. So we pass the hello world string. Now, like much of Python, max knows what kind of thing is being passed into it, and it knows that it's looking for the largest character, the lexicographically largest character, and in this case it scans this little, that's inside the max code, it scans through and finds the largest character. So apparently lowercase letters are higher than uppercase letters because in English we get back a W, and so this is what's called the return value. So this is an assignment statement. Let me clear this and start over. So this is an assignment statement, so it has to evaluate this right-hand side, and a function call is nothing more than like x plus 1. It's something to evaluate. It runs the function code, passes in this argument, and then this residual value, this is called return value, we'll look at this in more detail, becomes the result of this little bit in the expression, and there's nothing else. We could have, w plus 1 or something, and then the w is what's stored into big. Okay, so we print big, and big is a variable that has the letter W inside of it. And then we ask what is the smallest, and that finds the blank, and so we get a blank to see this. There's a min function and a max function. Both of these are built in. These are built-in functions. They're always there for us. Okay, so here is another example of the max function, and so we can think of this as invoking or calling this function as this right-hand side is being evaluated. We are passing this variable in, and there's some code in here, and it's going to do some stuff, yada, 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 and then it's going to give us back a bit of stuff, and that's its return value, and then that goes up into the big, right? And so that's how this works. And so this is actually built in or burnt in, I guess I can't draw. And so you can think of this as sometime a long time ago when Python was being first formed, somebody wrote some code. And it's got some stuff in it. It's got a little loop that reads through all the letters. It has to figure out if it's a string or a list, etc., etc., etc. But this is store, except you didn't do the storing because it's already built in, and then this is the reuse, store and reuse. So we build these things into Python. They're already pre-built, as if before the first line of your code executes, way up here, someone put all this code in for you into Python and created a thing called max for you. Now we've been using this already, built-in functions, we've got type conversions, we've got like the float that takes a integer and returns a floating point version of that. And again, this is kind of like an expression. So it's like I want to divide this by 100, but before I do that, I've got to convert it to a float. So it has to sort of do these function calls as it's evaluating the expression. Okay? Sometimes, like here, we just have a prints out the return value. That's what this is. This is the return value. If you just type a function in a parameter, it can be in a constant or it can be a variable. And as we'll see in a second, we'll give you many of these if you like. So you can either just run it or take the result of this. This passes an integer in, converts it to a float, and then puts the float into that. Type tells us what kind of thing that is, and you can use this inside of an expression. And so it's like, what am I going to do first? Oh, I've got to do 2 times this thing. Oh, wait a sec, pause just briefly for a moment, call out to some float code, pass a 3 into it, and then something comes back, the return value, the residual value comes back, and then that participates, in this case it's going to be 3.0, participates in this 2 times 3.0. Okay, and so 2 times 3.0 then ends up being 6.0, etc., etc. But you can see as it's like, oh, wait a sec, I got to figure out what this is, call the function, get the return value, and then continue processing this expression. We've also done this with string conversions, partly because, just as an example, the input always returns a string. The input function returns a string. And so, you know, here's this string, could be coming from input, but we'll just take 1, 2, 3. We know that that's a string, it's not the number 123, and if we try to add 1 to it, we get a trace back. Cannot concatenate string and integer. Trace back. But we can't convert that string to an integer, and so int can take like a floating point number or an integer or even a string, and it says, oh, I know what I'm supposed to do with a string. I'm supposed to look at this, interpret these as numbers, and, you know, multiply by 10 and figure out what the hundreds place is and all that stuff. There's a little bit of work to that, and it does it. But then it gives us back an integer, and we say, oh, what is that? That's now the 123, but it is of type int. And now we can add 1 to it and get 124. And as before from this example that we're kind of reusing from a previous chapter, you don't want to try to convert, oops, sad face, sad face. Sad face. Don't want to try to convert something that doesn't have digits using int, because it'll say, I don't know what to do, and then your program quits, right? You don't want your program to stop, tracebacks, and you can, of course, deal with that with try and accept, but that's like a previous lecture. Okay, so up next we're going to talk about building our own functions, not just using the predefined ones. So welcome back. We're going to continue and start talking about building our own functions. So again, we use the def keyword to define a function, and then later we're going to invoke this. And there's a bit to it. We are defining the name of the function. In effect, we're extending Python and creating new predefined things that we can use, except it's our code. It starts with a def keyword. Has some optional arguments, which we'll see in a bit. That's what the parenthesis is. And then the name. And the function names follow the same rules as variable names. And then you have an indented block whatever code you want to do, and then you have a de-indented block, and that sort of defines the essence. The key thing here is this is not calling. It's not invoking. It's not executing. It's remembering. It's storing. It's figuring things out. So here is the output of a program that defines a function but then doesn't use it. So this is a sort of broken function. So here we go. We start x equals 5, print. You don't have to def, you have all the defs at the beginning. The def runs whenever. So, you know, out comes hello. And then we define a function, and this says, oh, you want to make a new thing here. So I'll make a new thing. It's kind of like a variable in a sense. And then it copies this stuff, copies it up there, and says, later you probably are going to want to use this, so I'm going to remember it. So it doesn't do anything there. No output comes out. Then it says print yo, and out comes yo. And then it adds 2 to x, so x is now 7, and then it prints x, and there's no 7. There's 7. These print statements never ran. They never ran. Why? Because we did not invoke them down here. We defined them but didn't invoke them. So let's take a look at how you invoke a function, right? You define it and then you use it. Sometimes you define it once and use it once, but more commonly you define it once and use more than one time. Again, the store and reuse pattern. The def is the store and the invoking is the reuse. So here's just a slightly different version of that last program, and so now it's going to actually invoke it. So x equals 5, print hello, def, so out comes hello. This produces, the def produces no output, right? But because there's a de-indent here, that is the entire blob of the code that is part of print lyrics. So it prints out yo, and now we're going to invoke. This is the call. We're going to call the function. Now the function goes up. Let's clear this. So we're down to here. Now this like suspends at this place. It's like remember to come back to here when we're done. Go up, run this code, and then come back, and then continue on. So it like leaves like a breadcrumb of where it's supposed to come back to, and then it runs, and then the print lyrics, of course, produces the 2 lines of output, and yeah, that should probably not have. That they should be up there, and then x equals x plus 2, which makes it 7, and then prints out 7. Okay, so this is the invoke or call the function. Okay, you defined it and then later you called it. Now, in addition to just call and return and invoking, we can pass parameters in. And the example of the parameter is in the max function, we have to say, this is the thing I want you to find the maximum of, the largest thing. And part of it is in the whole store and reuse pattern, we have a few lines of code, but sometimes we want to do ever so slightly different things in the different invocations. And so we use the arguments to subtly adjust, like finding the maximum is a general thing, but what thing to find the maximum of, that makes a function that's much more useful and reusable in a lot more situations. So arguments are the thing we passed in, and we define for our functions that we're going to build, on the def statement, so we say def, greet, name a function, and then this is the arguments, the things that are coming in. Now this lang variable, in a sense, only exists during the life of the function, and it represents sort of a placeholder. It's not a real variable in the same sense. It's a placeholder that refers to how you touch that first parameter that's sitting in there. Okay, and so lang is our first parameter, whatever it is. We don't need to see this part down here right now. All we know is we're going to make a function, and we're going to take a parameter, and this lang is the placeholder that tells us what that parameter is. Okay, so within the function, we're going to check to see if the language is Spanish. If we are, print hello. Else, if the language is French, print bonjour. Otherwise, print hello. We have a very highly simplified language translation system here. So the def, of course, does nothing except remembers that and defines the concept greet. So that comes down, and now we're going to call it. And that says, go look up the thing that I defined called greet. If you don't put this in, greet is going to give you a traceback. But because you extended and named it greet, so it runs in, it starts, suspends the code here, starts up here, but then lang is now an alias to en. So now we can run if that is yes, else if, I'm getting it all wrong now. Right, so en comes in as lang, we're coming in the code. If it's not es, it's not fr, else it prints hello, and then it comes back to the next line. And then we call it again, and this time es is lang, and so it runs this code and prints hola, and then next time it calls with this, and then it prints bonjour. You get the idea. So this is a placeholder so that on the successive calls or invocation of the function, we can get at whatever the programmer put in as that first parameter. And so we are saying in this definition, we are ready to receive a first parameter. Please call us with a parameter, and then we will be able to do something slightly different for the different values. So this is a reusable bit of function that prints hello in 3 different languages, and then we tell it what language at the moment that we're actually invoking it. So that's putting stuff into the function. Now getting stuff back out is the concept of returning. In the return statement is an executable statement that does 2 basic things. The first thing that it does is it finishes. Now this is a one-line function, so that's kind of redundant, but when Python goes into the return statement, it doesn't continue on to the next line. It just returns. That is the end of the invocation of that particular function. But even more importantly, it takes as its parameter. You can say return without a parameter, and it will stop the execution of the function, kind of like a break does for a loop. It's kind of a break for a loop. Get out, we're done. Don't run that next line, get out. But it also allows the specification of what you want as the residual value in an expression. So we're doing a print, and then we're saying greet. And what's going to show up here is whatever this function does in its return statement. And so that prints hello. We call it again, and it prints hello again. Okay? And so basically the return statement is I call this the residual value. It's like what shows up here when the function is all done, and it's the string hello. We call the functions that return values fruitful because they produce something, and but you don't have to. You can just say return, or you don't even have to have a return statement. It goes to the last line of the function, and it does a return automatically at the last line of the function. So here's a little bit of a rewrite of our little language program. We are going to create a greeting program. We're going to take the language as the first parameter, and instead of just doing a print statement, which is what we did before, this is now more like a function because it takes some input and produces some output it as a return rather than just printing. It's a little tacky for a function to print. And so here we return hola, bonjour, and hello based on the right thing. So now we say print greet en, so it runs the code once, lang is en, and then it runs this code and the residual value is hello, so it says hello Glenn. And similarly, when it runs this code, it passes es in as lang, it runs through, and it runs this statement. It does, if there was more statements, it wouldn't run them. As soon as this return runs, that says that this bit right here is now HOLA. So hola Sally. And the same with French. Goes in, runs again, out comes the return statement, and then bonjour Michael. So you see how we can control as we're writing the application. We can control as we're writing the function what the residual value that we want to see in whatever expression is calling us. Sometimes we have returns and sometimes we don't have returns. So if you think of the max code that we talked about before, we can kind of see that somewhere inside that max code there's a return, and that's how it communicates the W back to us. So we pass in as argument hello world. It comes in as a parameter and it's going to loop through this imp somewhere. It's going to loop over and over into imp, and then at some point it's going to figure something out and tell us what it wants to send back to us is a return statement, and so the W comes back and gets assigned into big. You can have more than one parameter, and there's just an order. The first one and the second one, 3 and 5. So 3 becomes A and 5 becomes B. and away we go. So we just use this to add two numbers, and so 3 plus 5 is 8. So you get as many as you like, and the order matters. And if you do things like you tell it you want parameters and you don't give it to them, then that'll become a traceback, and it'll blow up. You can also talk about optional parameters later. So you don't have to have return values, and that means that you simply don't call a return with a value, and return is always implicitly happening as the last line of the function. So that's kind of the basics of how functions operate, but I don't want you to get too excited about writing functions. Some programming classes are like, gotta write a function, gotta write a function. Functions, to be clear, are a very powerful mechanism. And as we write programs, 150, 200,000, 200 lines of code, 1,000 lines of code, 10,000 lines of code, the concept of a function is really important. We would go crazy if we didn't have functions. But if you're only writing 20 lines of code, forcing yourself to write a function is kind of pointless. So don't worry about maybe the lack of urge to use this. We are calling lots of predefined functions, and we will for the next couple of lectures. There will be a time when you go like, oh, I'm sick and tired of repeating myself. Oh yeah, time to write a function. So that's why we don't push functions prematurely. We just want you to know what they are, use them, and at some moment you'll be like, oh, I want to define one. But don't worry about, it might take a while before you really want to define a function. So that kind of summarizes our lecture on functions, and up next we're going to do iterations. Hello and welcome to Chapter 5, Loops and Iteration. Now we're going to work on our fourth basic pattern of sequential, conditional, store and reuse, and loops and iteration. And this is the one where we teach the computer how to do things a lot. We can tell it to do something a million times. And so that's where we get the doggedness of computers, or the fact that they're so good at doing work for us because we can set them off to a task and they'll do it until it's done. So here's a very simple loop. Let's put the coffee over here. The keyword that we're going to start using is the while loop. We're also going to use the for later on. And the while loop functions very much like an if statement. The while starts it, and then this is just like an if statement. It's a question that leads to a true or a false answer. And then there's a colon, and then there's an indented block, and then we use the de-indent to determine how long the loop is, and so this print is de-indented, so that indicates the end of the loop. And so at some level, what's going to happen here is it's just going to run, and if this is true, it's going to run this code, and if it's false, it's going to skip the code. In that way, it functions like an if. The place that it doesn't function like an if is after it's run the code once, it goes up and then asks the question again. And so you can think of it going back up kind of to the top of the while loop and then re-asking the question, like, okay, is this going to run again? And then it's going to do that some number of times, and then it's going to finish. And so that's the loop, that's the iteration. And we're going to make a variable. We're going to construct very carefully a variable that we call the iteration variable, and that's n. And it's a variable that's going to change, and it's our way of running the loop, but not running the loop forever. So let's just run this. We come in, n is 5. Is n greater than 0? Yes, it is. So we're going to run this code. So we're going to run this code. We're going to print out 5, then we're going to subtract 1, and then we're going to go back up and ask the question, is n greater than 0? And the answer is, since it's 4, the answer is yes. So then it runs again. Then it prints out 4, subtracts it again, checks, prints 3, subtracts it again, prints 2, subtracts it again, prints 1, subtracts it again. Now n is 0, and so it comes back up. Is this question has now become false? So it's going to take the exit. So it's going to come down and run this line right here. Then it prints blast off, and we can kind of print out the residual value of n just to sort of prove to ourselves that it ran until n was no longer greater than 0, and then 0 was the final value for n. And we carefully constructed this n equals, oops, go back. We carefully constructed n. We set it to 5. Then we carefully subtracted 1 each time through the loop. And then we're using that to control when to exit the loop. And so you could think of this loop as, for now, running 5 times, true, 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 and then false finally. So this question was true for a while, and as long as it was true, the loop ran. And then when it turned false, the loop stopped. And so this variable that we construct to control the loop was called the iteration variable, because it tells how many times this loop is going to run over and over, or otherwise known as iterate. So this is a badly constructed loop with an iteration variable that we didn't do very well. And so if we take a look at this, we start it with n5, and then this is greater than 0, so it's true, so it runs it, and then it runs it again, and n is still greater than 0. So you can pretty much see, because we're not changing n, this is going to be true, 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 dot, 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 forever, true forever. And so this is an infinite loop. And it's just going to run until your computer runs out of battery or you hit the button. This is the kind of thing where you often see your computer spinning like a spinning beach ball, or some other indication that your computer's super busy. It's in some kind of a loop, really tight, and it's running something, and it's using up all of the processing resources of your computer. That's an infinite loop. And so the problem is we did nothing with the iteration variable. Now here's a different loop. And so this one demonstrates a different idea. So in this case, we start out with n is 0, and it comes in here, and is n greater than 0? Question mark, and the answer is false. So it skips it. It doesn't run these lines of code at all. And so this loop doesn't run at all, because it comes in, asks the question, and says no, and then it skips right around it. So never run, never run. And so this actually is, sometimes you write a while loop on purpose like this, not quite as simple as this one, but the idea is this emphasizes that these loops are what we call zero trip. They are not even guaranteed to run once. They're going to run maybe 0 times, and in this respect it functions exactly like an if statement, right? Meaning the first time through the loop, if it's not true, it's just going to skip right by it. So there's a couple of ways of getting out of loops. In this case, I'm constructing an infinite loop, because remember, the kind of definition of an infinite loop is if this is going to stay true. Well, true is the constant true. So this is going to run forever. And what it's going to do is it's going to prompt with a little arrow, and then let us type and read whatever we type into the variable line. And then if the line is done, we're going to break. Now break is an executable statement, and if you hit the break, it exits the innermost loop out to the place beyond the end of the loop. So when this runs the first time, and we say hello there, line is not done, so it prints it. So it prints out hello there, and then goes up, and then we type in again, we type finished, and so it's not done, so it prints it. So now comes that print statement. And then we type in done, and now this becomes true, and it comes out and runs the code beyond the end of the loop. The key is it doesn't go back. It's like once you've done a break, that loop is done. And so you look at basically, the block that is the loop. So here's kind of the loop block, and then the break goes to the line after the end of the loop block. And you can think of this as sort of like just a hyperspace jump. There is nothing really, this could be literally hundreds of lines with if statements, and you could be running and doing all kinds of stuff and running and doing all these things, and these things could run all kinds of ways, right? The point is as soon as you hit a break statement, however much stuff is down here, however much stuff is up here, it exits to whatever the next line is beyond the end of the loop. Continue is another loop control statement, but it works differently than break. So break says get out of this loop. Continue effectively says stop this iteration. We're done with this iteration. And so continue says go up back to the top of the loop. Oops. Yeah. Go up back to the top of the loop. And so here we read a line. If the first character is a pound sign, line sub 0, if that first character is pound sign, we're going to skip it. And this is a way for us to make like little comments in our typing. And then we print, if the line is done, we get out, and otherwise we print it. And so that's why there is no printout here, because it comes in, runs, oops. It comes in, this is true, and that goes back up. But it comes back and prints out the next one and does another thing. And so the loop continues, whereas the break ends the loop. And so again, the same kind of notion that you're sort of doing all kinds of complexity. Wherever you're at in this loop, you hit continue, and it doesn't go any further. It goes back up and runs the question mark. It asks the question mark. And so, I mean, ask the question, and it might exit the loop in that particular case. But this one here is this is an infinite loop that I've constructed. This is not an infinite loop because at some point the break gets us out of the loop. And so it's an infinite loop with break to escape it. And that's another common way to construct a loop. So these loops that we've been drawing so far, the ones that use while as their keyword, are what are called indefinite loops. And that's because they kind of go for a while, till a break hits or until some value becomes true. I mean, as long as that value remains true. So when all the ones we've done so far are easy to look at and know that they look pretty good and they're probably going to finish. But there are sometimes, if they're long and complex and their exit or termination conditions are a little more complex, it's not clear that they're really going to terminate. And so we can use while loops for a lot of things, but for most of our looping, we're going to use what are called definite loops, and that's what we're going to talk about next. So definite loops use the for keyword, and the idea of a definite loop is it's going to loop through some set of things. It might be a set of lines in a file, it might be a set of characters in a string, it might be a set of strings in a list of strings, but whatever it is, it's sort of going to run a finite number of times depending on the thing that it's looping through. And we like this, and it's an easier way to construct it, and we actually don't have to deal with the iteration variable. The for loop includes a mechanism to construct the iteration variable for us. So it's definite loops iterate through the members of a set. So here's a very simple for loop. And so you see the for keyword, and in is also a keyword. And the iteration variable is something we put right here. This I is declared. This I is like an assignment statement. And I is going to take on successive values. So I is going to be 5 the first time through the loop. Then I is going to be 4 the second time through the loop. 3, 2, 1. So I is going to be assigned 5 different times to 5 different values. And then the loop is going to run. It's going to run once with 5, once with 4, once with 3, once with 2, and once with 1. And so this block of code we have contracted, say, execute it 5 times with these values of I. I is that iteration variable. I is the thing changing through each iteration of the loop. Okay? And so that's why this prints out 5, 4, 3, 2, 1, and then when it's done, it finishes it. And so this is a much more direct syntax for looping 5 times and setting an iteration variable. You kind of all combine it into this one thing, right? All into one thing. So it's quite nice. So you don't have to be going through a list of numbers. There's all kinds of things that we can iterate through with for. And by the way, while I'm sitting here, I named my variable friends, because that's a list of strings, and friend, which is the iteration variable. I'm using singular and plural because it helps you read it. Python doesn't understand singular and plural. So just because you say friends doesn't mean Python knows it's a list. Python does know it's a list, but it doesn't know by the name of the variable I've chosen. That's your basic mnemonic variable warning. These are cool variable names, but I don't want you to be confused by them. So you can loop through a variable. So we're going to take this list of 3 strings and stick it in friends. And so friend is going to iterate through that. So the first time through, friend is going to be Joseph. Second time through, it's going to be Glenn. Third time through, it's going to be Sally. And so that just says run this code, the indented code, 3 times. Each time the variable friend takes on a successive version of a successive value that's in the friends array. So it says happy birthday Joseph, Glenn, Sally, and then we come out of the loop and we print done. So if we try to draw a picture of what this is really doing, the for loop is actually doing a whole bunch of stuff that we would have to do with maybe separate statements in the while loop. First, it decides how many times to run the loop, so it's answering the done question, which way do we go, and it is also then moving I ahead. It's managing the iteration variable. If you go back to it's initializing it too. If you go back to the while loop, we had n equals 0, while n greater than 0, n equals n minus 1. So we had like 3 lines to control the loop, to manage the iteration variable, but with a for loop, we don't have to do that. And so that's all taken care of. And so that basically says, you know, the for loop, by you using a for loop, are we done? No, we have 5 things to work. Well, set I to the first one, run it. We're not done because we got one more, set it to the second one, third one, fourth one, fifth one, and now we're done. And that is all handled in a single line of code that includes the iteration variable and the set of things through which we are going to iterate through. I really like the word in. It is mathematically, it reminds me of the set theory where you say this is a member of this set, or the for each. Math isn't important here, but if you do know math, the vertical bar means such that, right, is a member of this set, and that kind of stuff, member of this set. I'll erase the math stuff so we don't over math. But it's like, for each of the values in the set 5, 4, 3, 2, 1, run this loop setting the iteration variable I to the members of that set. So in reminds me, for those of us who are math oriented, in reminds me of a really nice concept in mathematics. Okay? Now, you could think of this as sort of this looping structure where the for loop, and this is pretty much how it actually runs inside the computer, right? Where it initializes it, it runs this thing 5 times, and then executes. That's one way to think about it, but you could also think about it in a somewhat more abstract way, and think of it as all we're really doing is we have a contract with Python that says we're supposed to run this code 5 times, and I is supposed to be 5, 4, 3, 2, and 1. So you could imagine this might be what's going on. The for loop sets I to 5, runs our code. The for loop sets I to 4, runs our code. The for loop sets I to 3, runs our code. The for loop sets I to 2, runs our code. For loop sets I to 1, and runs our code. All we know is our code was ran 5 times, and by contract, each successive time, we're get a different value for I, and the value for I is taken from this set. And so this is just one way to think about it, to say to yourself, oh yeah, this is one way to think about it as it's actually, and this is how it really works. But this is also kind of logically the contract that Python is making for us. So up next, we're going to talk about taking this notion of doing something to a lot of items, but accomplishing something with that, and I call these loop idioms. So now we're going to talk about loop idioms, and loop idioms are patterns that have to do with how we construct loops. We have the mechanics of fors and whiles, but ultimately we want to get something done. We want to solve a problem with a loop. And often what we have to do is, if we have a set of things, whether it's lines or strings or characters or numbers, we're looking for something like the largest or the smallest, or we want to add them up or something like that. And so we can't just say add them up. We have to say go through each one and do something to each one and somehow achieve adding them up. And the pattern that we're going to follow is we're going to have this loop that's going to do run once for each thing, right, in some chunk of data. And then, but we're going to set something at the beginning, and then we're going to do something to each one. And at the end, we're going to kind of get the payoff. We're going to get the result. So if we're doing sort of summing things, we're going to have a running total. And so this will be like t equals 0. And then this will be t equals t plus the thing value. And then, but this is not the real total. It's the running total during the loop. But at the end, it is the real total. And so we're gonna look at what you do at before the loop starts, during the loop, and then what you get after the loop and how you can use that. So we're going to use this loop. It's just going to loop through a set of 6 numbers over and over and over again. right? So we're going to do something before the loop, we're going to do something after the loop, and then we're going to run the loop some number of times. And in this case, thing is our iteration variable because I'm using unmnemonic variables now. So this is going to run 9, 41, 12, 3, 74, and 15. So it's going to run and print these things out. So it runs this loop 6 times, and away we go. Now this loop does nothing except print stuff out. Of course, I like to do that first, is always print things out to make sure that sort of my brain is functioning. So to kind of understand how these loops work, I'm going to ask you to function as a program. And I'm going to show you some numbers in succession, and I want you to mentally figure out what the largest number is, but more importantly, think about how your brain is solving this problem of what is the largest number, given that I'm only going to show them to you one at a time for a little while, and your brain has to do something. And imagine I was going to show you thousands of numbers. I'm not, but imagine I was. How would you organize yourself in a way so that for like an hour and a half, you could sit here as I showed you numbers and you keep track of the largest number that you've seen of all the numbers? Okay, so here we go. Here's your first number. Second number, third number, fourth number, fifth number, sixth and last number. What was the largest number? What was it? Well, it wasn't too hard. It was 74. But that's not the question. How did your brain arrive at 74? So here's all the numbers. If I'd shown you all the numbers and asked you what's the largest number, your eyes would have sort of gone, and then you got to 74. And you wouldn't do it in any particular order. Your eyes would just like see the 74 and it would just throw smaller numbers away, and it would move really quickly to what the answer is. Even if there was several hundred numbers on the screen, your mind would sort of move fluidly wherever it felt like moving and then arrive at it. And probably what it would do is it would do something like, kind of move like this, find this, and then sort of check to make sure that it's okay, and then say like, okay, I got 74, I'm done. That's not how computers do it. That is not how computers do it. They do not move fluidly. But they are highly dedicated. They're going to do something, 74. But how would you construct a loop to achieve this? So let's take a look. You could create a variable called largest so far. And this is the largest variable, the value that you've seen in the list so far. Now, I haven't shown you any numbers yet, so we'll just set this to -1 to get us started. So now we see 3. And we're like, oh, that's better than -1. It's our first number, so it's probably the largest we've seen so far, right? Great. 41. Oh, that's bigger than the largest we've seen so far, so we'll keep it. 12 is not bigger than 41, so we're not going to keep it. Notice this keeping thing. 9 is not bigger than 41, so there's no point to keeping it. 74 is bigger than 41, so we'll keep it. Is this the largest number? We don't know. We don't know until we're done. 15, not better than 74. So now we're all done, and hooray, 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 we have the largest number. And we had this variable that we kept the largest number that we'd seen up to this point. And then when we know that we're done at the end, then that becomes the largest. So if you look at all the numbers, keeping track of the largest so far, at the end of all the numbers, the largest so far and the largest are the same thing. And so that's how you get this idea of something you're doing during the loop is not really the answer, but by the time the loop is done, you will have the answer. And so here's a bit of code that does this. Use it with our numbers, right? So let's take a look. So I have this variable called largest so far. I set it to -1. Before the loop, remember there's a loop before and a loop after and a loop in the middle. Before it's -1. So now the num, remember underscores are okay, that's my iteration variable. If 9 is greater than largest so far, well, largest so far is -1, so that's true, so this code's going to run. So we're going to remember the new number. So this is 9, and so 9 ends up in largest so far, and then we print it out. And so largest so far is 9 after we saw the number 9. Then we do it again. So now 41 comes in. And is 41 greater than 9? The answer is yes, it is. So we're going to run this code, copy 41 into 41 into largest so far, and then print it out, and largest so far is 41 after we saw the number 41. Now we're going to run the loop again with 12, okay, and you get the idea, I hope. Is 12 greater than 41, which is the largest we've seen so far? And the answer is no, it is not, so we skip. So the largest so far stays 41 even though we saw 12, meaning we're sort of like ratcheting up, but we never ratchet back down. So we run it again with 3 and 41, and we skip this, and then the largest so far is 41 even though we just saw 3. And now we see 74. Is 74 greater than 41? See, we never are looking at all the numbers. We're only looking at the window on the numbers of the current number that we're looking at. So is 74 greater than 41? The answer is yes. So we run this code and then we capture the 74. So we just saw 74 and it is the largest so far. And then we run it again with 15, but 74 is our largest so far, and so it skips. So 74 remains largest so far after 15, and now we're finished because we just ran the last thing. The for loop takes care of everything and jumps to this print statement and says afterwards, largest so far is 74. But at this point, it's also the largest, right? So largest so far became largest when our loop finished. So that sort of gives you this notion of how we construct, you know, something at the beginning, some kind of thing that we're going to do over and over and over again, and then something at the end. And we put some print statements in just so we can watch it and see what's going on. So coming up next, we're going to talk about some more loop patterns, some counting, totaling, averaging, and finding the smallest number. So now we're going to look at some more patterns of the different things we can do at the top of the loop, in the middle of the loop, and at the bottom of the loop. And the first one we're going to do is counting. Now we're going to take a look at the number of something, the number of things in our list. Now we could just inspect it and see 6, but you will have for loops like you're reading through a file or, you know, scanning through some data. And so the notion of counting, you have to assume that you don't really know, you know, that there's going to be a lot more than just 6. But for now, we're just going to do 6, and we're going to count how many things that we see in this loop. And the pattern is simple. You set a variable, Zork, to 0 at the beginning. We often call this variable count in mnemonic. And now we're going to run this loop 6 times. 1, 2, 3, 4, 5, 6. And each time through, we're just going to add 1 to Zork. So Zork starts at 0, then it goes 1, 2, 3, 4, 5, 6. And we're going to print it out. So, you know, we see the 9 and Zork is 1. See 41, Zork is 2. And Zork is 16 when we see the 15. 4 stops. And we print out afterwards, and this then is 6 is then the ultimate count that we got. So that's very, very simple. The pattern is that set it to 0 at the beginning, add 1 to it, and if you run that enough times, then this is how many times that happened. And in a sense, it's how many times this line ran, right? Sometimes you put this in an if statement, etc., etc., etc. Okay? Oops. Now, we can do the same thing to get a total. And the way the total works is you compute a running total of the number of the items that you've seen so far, and at the end the running total in effect becomes the total. A better variable name for this would be like sum or total or something, but Zork, I'll use Zork again. So you set Zork to 0, and it starts out the total we've seen so far is indeed 0. And then we're going to run this 1, 2, 3, 4, 5, 6 times, and thing is going to be the iteration variable. It's going to take on the successive values, and each time through we're just going to take our running total and add to it the thing we've seen. So we see 9 and the running total is 9. We see 41 and the running total becomes 50. We see 12, the running total becomes 62. We get a 3, it becomes 65, we get 74, running total is 139. How many more are we going to see? We don't know. Could be a million. Could be 1. Oh, it's only 1. We get a 15. Our running total is 154. And what's true at any moment here is the running total is right of what we've seen so far. Now, when we're done, the for loop quits for us, and afterwards, 154 is indeed the total. So the running total while we're in the loop, at the end of the loop, after the end of the loop, we have the actual total. So it's not very difficult to convert this to the average, because we've calculated the count and we've calculated the running total, and now we're going to have the average by simply dividing those. Okay, so now this time I've used mnemonic variables. Don't get confused by this. Mnemonic variables are just friendly names I chose for you to read the code easier. I am not communicating to Python in any way by naming this count and sum, but count and sum is nice. Okay, so I set count to 0 and sum to 0. Oh, go back up. I set count to 0 and sum to 0 at the beginning, and the count is 0 and the sum is 0. And then I'm going to run this loop 6 times. 1, 2, 3, 4, 5, 6. And each time value is the iteration variable. I count every time I run the loop. I count equals count plus 1, sum equals sum plus value. So I have a running count and a running total, and they show up here 1, 2, 3, 4, 5, 6, and then the running total. And then at some point the for loop, we do the last one, and the for loop jumps out and it divides 6. 154 is the count and running total, and then it divides the average sum over count. Okay, so that's just again a pattern of something in the beginning, something in the middle, something in the end. Another kind of thing we tend to do in loops is we look for things, we hunt for things. And so this is where we have an if statement inside of a loop. And of course I've created a silly simple thing. In this code I am looking for large values that are greater than 20. And again, don't think of this as just 6 numbers, but I'm looking for all the values and I'm going to print them out. So, it says before, it's going to run this 9. Well, if 9 is greater than 20, it's false, so it goes back up. 41, true, so it prints out 41, then goes back up. 12, false, goes back up. 3, false, goes back up. 74, true, so it runs this, so out comes that little print statement. Goes back up, and then 15 is the last one, and that's false. It goes back up, and the 4 says, we're done, and then we do afterwards. And so this is just the notion of having an if statement inside of a for loop, where we're sort of picking or choosing or selecting or looking for something in a large set of things that we're looping through. We can also say, I want to know if a particular value is there. And so we're going to use a Boolean variable. And we've talked about integer variables like 1, 42, and then floating point variables like 98.6, and then string variables like hello world that have quotes in them. This is a fourth type, a kind of variable. It's called a Boolean variable, and it only has 2 values. It has true and false. Matter of fact, these if statements, they return Boolean values. Value equal 3, that is returning a true or a false based on the value of value. There's a mnemonic confusion there, right? But I'm using it. So I'm going to make a variable called found, and that's a decent name for a variable, so don't get hung up on that. And I'm going to initially say found is going to indicate to me whether or not I found a 3 in my list. And I'm going to start before the loop starts, say false, because we haven't found anything yet. So found equals false. And so at the beginning of the loop, found is false. Before the loop starts, found is false. And now we're going to run this loop a bunch of times. 9, is that true? No, skip. 41, is that true? Skip. 12, skip. Right, so 9, 41, 12. And found has remained false because we haven't done anything to it. But now in comes a 3. And this becomes true. So it runs this code. So found becomes true. And then we print it. And you'll notice that when we see a 3, we get true. And then it runs again. We get 74. It's still false. 15. It's still false. Run, quit. And the residual afterwards is true. And in fact, if you didn't know any of this and you don't print that out, all you know is that afterwards we loop through all those things and we know that there was a 3 in there. That's what we're doing. So we searched all of them, we checked for 3s when we found a 3, and you can see basically that, the found remains false until it flips to true, but then there's nothing to set it back to false. There's nothing in this loop that's going to set it back to false. So once it sort of catches the 3, then it remains true for the rest of the loop, and then it just finds its way out. Now, if you want to think about it for a moment, ask yourself, how might we make this loop more efficient by putting a statement right in here? Think about a way to, once you found it, and it's true, there is sort of no reason to keep on going. So what would you put there to perhaps make this loop to look for 3's, just to tell you whether or not there was at least one 3 in there, how to make that more efficient. Just think about that. Okay, so now let's look back at the largest value that we started out with, right? And so if you think about this, let's kind of give it a sort of a rough look here. Largest so far is our kind of like a running total, but it's our hypothesis is the best large number. And we have this if statement that says if the number we just see right now is greater than the largest so far, then capture it, right? Take whatever number we saw and capture it. So when we see 9, it's better, we capture it. We see a 41, it's better, we capture it. We don't capture this, we don't capture this, but we capture the 74, and we don't capture the 15, and that's how we do it. So you could think of this as better. When the number we're looking at is greater than our working hypothesis of the largest, we grab it because it's better. So this line right here is the grab line. Grab it. Okay? So then the question is, how would you modify this code to teach it to find the smallest value in this list of numbers? Think of it as you have a starting number, you have a sort of what's better in this grabbing notion. How could you do that? Take a look. Okay, so let's take a look. So let's do a couple things. Like if you look at this if statement that's better, well, it's better now if the number is less than. So but then we should probably change this to be smallest so far, 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 right? Matter of fact, that's what this is. We've changed the word largest so far to smallest so far, and we've changed the greater than to a less than. Is that going to fix it? I'll give you a second to look at it. Pause if you need. Is that going to fix it? Is that going to find our smallest number? The answer is, of course, no, it's not. So if we run this code, so we set the smallest so far to -1, and it starts out -1. We run it, and it's 9. Is 9 less than -1? No, it's not. So after we see a 9, the smallest so far is -1. Now we're going to run 41. Is 41 less than -1? No, it is not. So the smallest so far is still -1. As a matter of fact, it isn't the smallest so far anymore. Just because we named it smallest so far doesn't mean it is the smallest so far. It didn't work out so well. And so you see that none of these, because they're never less than -1, do anything. And we claim that afterwards the smallest we've seen so far is -1. And that is because, of course, -1 is smaller than any of the numbers that we saw. So how could we fix this? Well, if we started the smallest so far with some like arbitrary big number, then it'd be better. So if we made this 100, whoops, come back. If we made this be like 100, that'd be good, because the first time through, the 9 would be less than 100, so we would capture the 9, and then the rest of the loop would work just fine. But then what if we didn't know how big these numbers were? As a matter of fact, the largest so far wouldn't have worked if all the numbers were negative. Think about that. We just assumed they were positive, and so we kind of wrote lazy code that assumed all numbers were positive. That might not be a good assumption depending on the numbers that you're dealing with, right? So maybe 100 is a good number to start with, or maybe like 1,000 or 10,000, or like some number with lots of zeros in it. How big should we make this? And the answer is we're kind of solving this problem the wrong way. And the thing we really want to do to solve the problem is to just accept the fact that if we're looking for the smallest number so far, that the right hypothesis is the first number. And if we just knew what that first number was, the 9, because it's the first number, we know that it's both the largest so far and the smallest so far as soon as you see the first number. But we don't know here before the loop starts what that first number is. I mean, you can look at it, but assume this is just data that's coming from somewhere else, and we don't know it until we start reading it. So we have to construct a loop that deals with the fact that we want to capture the first value as our hypothesis for smallest so far. So how do we do that? Let's take a look. So what we do is we use yet another type. So we have integer, floating point, string, Boolean, and now we have a thing called the none type. None type is a special marker in that it only has one value. Boolean has true and false. You know, floating point has an infinite number of values and integer has an infinite number of values, but none type has one value, none. None is a constant. Capital none is a constant. The difference is we can check to see if we have stored none. None is often used to indicate emptiness, not non-existence, because smallest doesn't exist until we assign it, but we're going to assign it to like a mark, a flag, a marker, some way to say, oh, this is not even a number, it's nothing. And so we're going to, and you can do this. So that's like makes a variable called smallest, and in it puts none. It sticks it right in. It's not a string none, it's like a special type. Okay? So that actually captures the notion that before the loop starts, the smallest number that we've seen so far is none. We haven't seen any numbers. Okay? So then we come in and we have an if statement. And we have a new operator called is. Is stronger than equal sign. And so if smallest is none, that becomes true, it runs this case. And so then what it does is it copies this first value, which is 9, into smallest. And so we see a 9, and the smallest so far is 9, which is the first value. And again, we're assuming we don't know what the first value is before the loop starts, so we use the first iteration through the loop as the moment where we capture that. Okay? So, smallest is the value, and then we print it, and we go back up, and now it runs again with 41. 41 is not none. None is, there's only one thing that's none, so it is not equal to none. Smallest is not equal to none, or is not none. So this is false, so it skips over here. Then it asks the question, is the value we're looking at, 41, less than smallest? Well, smallest is 9 in this case, and this is 41, so that's false, so it skips that and goes on. So we see 41, we don't take it, and then you can see that this will never become true again. This is pretty much false for the rest of the iterations of the loop. That's false for the rest of the iterations for the loop. So it just is going to run down here and ask this question. And at some point we see a 3, and we run this code, we capture it. We see 74, we don't capture it. We see 15, we don't capture it. So then the for loop skips out, and at the end we have the smallest. And actually this would be a good technique for the largest as well, because it really is just a technique to put a marker in this variable so that we snag that first number or first whatever as we read and parse through them. So the is and is not operators are very useful in Python. You can think of them as like the double equal sign. They're asking a question, and they're asking a question, and they return a true or, you know, blank is blank returns a true or a false. It is stronger. Double equal says, are these things equal in type and value? So just as an example, if I were to say, is 0 equal to 0.0, it would say, yeah, that's true. But then if I says 0 is 0.0, that would be false. So that's because these two are the same value-wise, and these two are not the same type-wise. So is stronger than equals, meaning that it demands equality in both the type of the variable and the value of the variable, and no conversion is done. And so that's just a very strong. Don't overuse is. If you're dealing with numbers or even strings, use double equals, don't use is, because sometimes it gets a little confusing. So use is sparingly. I tend to only use is on Booleans and on none types. I don't use is on integers, and I don't use is on floats, and I don't use is on strings. Just none or true false. And also is not is also an operator. So you just say blah 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 is not none, or blah 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 is not false. Okay, so we've been looping around and doing loops and loops of loops. We looked at the indefinite loops, the while loops that kind of run for a while. The definite loop, and we looked at break and continue as a way to either escape completely from the loop or go back up and discard the current iteration of the loop. We looked at none. We looked at Boolean variables with for loops, definite loops, where you've got some kind of a set or a list or some kind of sequence that you're looping through. And then the concept of loop idioms, where you do something at the top, something to each item, and then you sort of get a benefit at the bottom. And so that gets us through iterations. Hello and welcome to Chapter 6. In this chapter we're going to talk about strings. And Chapter 7 is the payoff chapter, so we, up to this point we're still learning sort of basic building blocks, and actually we're going to write a real program in Chapter 7. So just learn this, and the payoff's in Chapter 7. So we actually been using strings from the very first lecture, because if you print hello world, well, that's a string. And so we've been doing things. This slide here is all review. We use plus to concatenate strings. We use print to print them out. Print's just a function that takes as a parameter something, strings, integers, etc. We can put digits in strings, but we can't add to them. By now you figured this out, but you can use things like ints to convert the strings to integers and then print things out. So, we've been doing this for a while. We've been talking about strings all along. Now today, what we're going to do is going to just get into strings in more detail. We input data with the input function. Input returns us a string. And if we want to input a number, we have to run some kind of conversion, like we have to do on int before we take this data that we read from input, And so there's things that we've got to do, and we've been doing all these things in programs so far. But if we look in a little more detail inside strings, we can index within strings each character. So each character has a separate position and a separate index, and they basically, the letters have positions, and the positions start at 0, and the best way I explain this to remember this is it's the elevators, as we used in one of our examples a long time ago. Elevators in Europe start at 0, and so strings start at 0 as well. Turns out in the old days there's some efficiency with the notion of lists of things starting with 0. These days the efficiency isn't the issue, but there's a certain elegance starting at 0, even though intellectually you might think 1 would be the first character in the string. Might make most sense to be sub 1, but it's not, it's sub 0. But just remember that. And so we have this operator called the index operator, and it's square brackets. So, fruit is a variable that contains the string banana, and then fruit sub 1 is the character that's in position 1. Now that actually is the second character. I'll keep reminding you until I get tired of reminding you. And so that assigns A, the letter A, into the letter A into the variable letter. Of course, that's a badly chosen. It's either a well-chosen variable name or a badly chosen variable name. And the thing that goes inside this can either be a constant or it can be an expression. So this is x equals 3, and then fruit sub x minus 1, well, that means 2, which is position 2, which is an n, and so that gives us an n. So the index is an operator, and you can add this bracket syntax to the end of a string variable. You can't index beyond the length of the string, so if I say zot sub 5, well, there's only 3 characters, which means 0, 1, 2, but sub 5 doesn't work, and of course we get a happy little trace back. So you have to be careful when you're starting to pull stuff out of strings. Although some of the things allow it, some of them don't, and then you'll kind of get used to that. We can ask how long a string is. And so we use the len function. We pass the string variable, and we pass it into len as parameter, and len gives us back the length of the string, not the position. So it's 0 through len minus 1. So it's 0 through length minus 1. So length is just another function that we've been doing functions now for a while. You pass in a parameter, and then len does some work, and out comes 6, and that goes back into x because the function has a residual value. It just happens to be a built-in function. And so somewhere deep inside Python there is code that takes this and somebody wrote a loop or looked something up and then returned a return value and sent back a 6 to go into our x variable. And so a function is there, and like I said, we've been using this for a while. Another thing we tend to do is to look through strings and look at strings and dig data out of strings. Python is excellent for doing sort of these kinds of lookups. And so we can write a simple loop. We can write a for loop that creates some kind of a iteration variable like index. And given that we know that these positions are 0 through 5, we can set this to be 0. And then write a while loop while the iteration variable is less than the length of fruit. And remember, this is 6, so it's going to be 0 through 5. 0 through 5 are the values we want to generate. And then we can look up one at a time, pull out fruit sub index, so fruit sub 0, fruit sub 1, 2, 3, 4, 5, and then print out the position and the letter index, and then add 1 to index, and it runs. This will run 6 times, 0 through 5, and out we go to produce this output right here. And so that's one way of looping through strings. That is a basic indeterminate loop, but we construct carefully an iteration value, and work our way through that loop data. The other way is to use a determinate loop, a for loop. And generally when we are able to use a while loop or a for loop, all else being equal, we generally prefer a for loop. And so here we have the for keyword and fruit, and it's an in. And so for letter in fruit, well, that just says letter is our iteration variable, and it's going to take on the successive values of each of the characters. So this loop is going to run 6 times, and letter is going to be B-A-N-A-N-A, banana. I'm always terrified when I make these slides that I'm going to misspell banana, because somehow I always think that there are 2 N's somewhere. I don't know. It's not one of my favorite words to spell. I actually didn't choose banana as the constant. The author who I borrowed the textbook from, Alan Downey and Jeff Elkner, they used banana, and so I'm still using banana. So some of the jokes in the book aren't my jokes. They are the jokes of Jeff and Alan. So here are just 2 equivalent, so you can have the while loop. They sort of both do the same thing. They both just print the letters out one time through. Each of these loops runs 5 times. But you can see how the determinate loop, the for loop, is a prettier loop, unless you truly somehow need to know this number as you're going through the loop. But if all you're doing is going through and you want to touch in order each of the characters of the string, you then simply write a for loop, because it's more elegant. The less code you write, the less chance there is for you to make a mistake. And so the fact that these are equivalent, this is 2 lines of a loop, and this is 4 lines of a loop. That's twice as many places as you could make a mistake, because you might, misspell index or something. I mean, why even make an iteration variable if you don't need to make an iteration variable? And so we can do things that harken back to our iterations and loops chapter, where anything that you can do in those things, like look for the largest letter, look for the smallest letter, search to see if a letter exists, or say count the number of A's in the word banana. And so that's what this is doing. And so we we have a counter. So again, we do something at the top of the loop, we're going to do something in the middle loop, and then we're going to print it out at the bottom. So we start our counter at 0, we're going to loop through all the letters, and then if the letter is A, then count equals count plus 1. This is kind of a pattern in a loop where we're noticing something, and instead of like we did it earlier where we said found equals true, well, we're going to count them this time. So if we have 1, we'll get 1. If we have 0, we get 0. And how many ever there are, but there should be 3 because it's going to run 3 times, and there's 3 A's in banana. And so this is a conditional within count. We've seen counts, we've seen conditionals in loop in prior chapters. And so again, I love the in keyword in Python. It again reminds me of set notation in algebra. If you're a math whiz, if you're not, don't worry about it. Or maybe you will be a math whiz and you'll say, whoa, this set notation reminds me a lot of the in keyword in Python. So again, it's for iteration variable letter, again, don't get stuck with letter, I just happen to be using it here, in banana. And that is for each character in the string banana. Run this loop once, changing the variable letter to be the particular character that we're pointing at. And so it's taking care, for is taking care of a lot for us, right? And so this is sort of this really smart for loop. The for loop is, you know, both deciding how many times to run the loop, in this case 6, and it's advancing the letter. So advance, print. Decide whether you're done, 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 advance, print. Decide whether you're done. I am now done because we're done with that particular string. And so you can think of the for as, magically doing all of this for you, of both deciding how long to run the loop, when you're done or not, and moving down through all the successive letters in the loop. So up next we'll talk a little bit about additional things that we can do with strings. So now we're going to dig into strings a bit, and we've already looked at how you can pull out a single character in a string, and now we're going to look at what we call slicing, and that is pulling chunks of a string out. And again, we're going to use the square bracket operator. And so S, and the way I say it is sub, S sub 0 through 4. That's how I read this. S sub 0 through 4. So I look at the colon as through, I look at the brackets as sub. And so S sub 0 through 4 says start at position 0 and then go up through, but not including 4, right? So we don't include 4. So that's probably the hardest part of this, up to but not including, up to but not including. This seems counterintuitive, kind of like starting at 0 seems counterintuitive, but after a while you get used to it, and there'll be situations where you're writing code like, oh, that's why that works better. But just for now, remember it, up to but not including. It's just kind of a little thing. We'll come back to when that is useful for us. 6 through 7, well, that ends up being starting at 6, up to, but not including 7. So that's why we only get the P out. Now, one thing that Python is pretty nice about is it's not going to give you a traceback. We might expect that 6 through 20, well, there's no 20 characters, but it's like, that's okay. We'll just let you stop at the end, and we'll start at 6 and go all the way to the end. Oh, no traceback. It's almost disappointing sometimes when Python doesn't trace back, when you think, if you're so obsessed about everything, I would have traced back in that situation. But hey, I guess if you're allowed, you're allowed. And so there we go. Now you can eliminate or omit the first or last. If you eliminate the first, it assumes the beginning of string. If you eliminate the second, it assumes the end of the string. And why you would do this, I don't know, but that's from beginning to end, so it's the whole string. So whole string, 8 through the end is thon, and up to but not including 2 is mo. All right, so you get that. So that's pretty simple. Once you've got the rest of slicing and the rest of string indexing, the notion of eliminating the first or the last of the colon expression, the first or second of the colon expression, I think is actually pretty intuitive, pretty nice. We've already been concatenating strings together. We overload the plus operator, and there is no space added. Remember, when you're doing print, x comma y, this comma does turn into a space, but that's not what's happening here. There is no automatic space being added, and so we see hello in there, and it just is hello there with no space. And so if we want, we just have to concatenate the space explicitly if we want to put spaces into strings. The problem is you might think it's more convenient to add a space with a concatenation, but then you have to think, well, what about if I want to concatenate things and not put the space in? Then I'd need a different operator. So that's kind of why it works that way. We can use in differently as a logical operator, so we're using it as an iteration structure in for loops, but we can also use it as a logical operator in if statements. So it's kind of like the double equals or not equals or less than or equals or something like that. It's like those guys, and so and it returns a true or a false, is N in fruit? So that's a question, and the answer is true. Is M in fruit? No, that's the answer to a question. Is Nan in fruit? Doesn't have to be a single character, can be more than one character, and the answer is true. And then you say something like, you know, if A in fruit. And so this is the logical value that returns a true or a false. And yes, we found it. So that becomes true in this particular case. So it runs the little indented bit. So in is an operator in this particular situation. In a for loop, in means something different. And we'll use in for other things as operators, as logical operators coming up in a bit. You can compare strings, and this has to do with the character set of your computer, the character set that Python is, but in general, you know, it is lexicographically less than and lexicographically greater than. Uppercase and lowercase are a little weird. I think when we used the max function earlier, the way my computer was set up, uppercase was less than lowercase, but in general, uppercase is less than lowercase. But in general, it's bad to assume case, but there is a deterministic way to sort strings. You can, you know, have something equal to or less than or greater than, and all those operations work naturally. The less than and greater than, you have to kind of be aware of uppercase, lowercase, things like where you know, punctuation sorts less than or greater than letters. That's kind of unpredictable and depends on the character set of your computer, and something you just play with and figure out. If you're doing sorting stuff by first name and last name, as long as the case is kind of the same, you know, if you were sorting Chuck with an uppercase and Glenn, the fact that these uppercases, they'd sort right and these lowercases would sort right, but if you were to subdue instead lowercase Chuck and uppercase Glenn, then that would sort weird. As a matter of fact, the G would come before that. And so case can mess this up, but in general, other than case and special characters and other things, it technically works. It's just hard to kind of predict it. A lot of what we do is use the string library, and so the strings are objects, and we'll talk later about what that really means. And objects have these things we call methods. So a string object has some built-in capabilities, and one of the built-in capabilities that the string object has is, here is a string object, and because greet is a string object, if we said type, we'd see that it was an str. Dot lower says, hey, dear string, make a lowercase version of yourself. It's like calling this function lower and passing greet into it, and then give that back to me. Now it doesn't actually change greet, it gives me a lowercase copy. So here I have hello Bob with an H and a B uppercase, and what I get back in Zap is hello Bob all lowercase. And note that greet is unchanged, so hello Bob is still there. And you can even call these methods on constants. So this is a string object, quote, hi there, quote, dot lower, that says call lower on this bit of string and give me back a lowercase version of it. And so it prints out as the residual return value. This is like a function call. A method call is a kind of special form of a function call. It's a function call where you say the thing dot the function name rather than function name passed in as a parameter. Like len, for example, is non-object oriented. You know, len of x, that's non-object oriented. Object oriented would be x dot something, parenthesis. But so constants are objects as well, and taking the lower gives us back lowercase hi there. And so that's just one of the things that you can do in the string library. These are built into string variables and constants. They're just always there. As soon as you make a string, they're part of it. And when you do type and it says it's class str, we'll get to object oriented. Don't worry, we'll get to object oriented. Okay, and so you can do things like use the type. If you're just look, this used to say type stir, but it's class stir. Kind of, this is more of an the word class is an object oriented concept, but it is a string, and you can use the dir, and of course there's extra stuff up here, and this is showing all the different methods or capabilities, things we can do to strings. So, you know, x dot something, parenthesis. Well, what can we do there? This is all of those things that we can do to X's that are built in and come with X's, come with strings when we build them. And Python, of course, has great documentation online for all of these string methods and what they do and how they work and why they work the way they do. And so here's some of that Python documentation. We'll look at a few of these, but don't hesitate to say Python string uppercase, and then we're like, oh yeah, that is upper, right? And so here's a few things that we can do and use. Some of the ones I use a lot, and we'll look at each one of these things. So the find operation says find me a substring within a string. Right, find me a substring within a string, so find me the first NA and give me back the position. So that gives me back 2. And then I can say, go find a Z in there. Well, there's no Z, and so it returns me -1. So that's what the find does. So we're going to use this kind of stuff a lot, and we do a lot of looking in strings. Converting things to upper or lower case, there is an upper method and a lower method. So greet.upper. And that means the uppercase NNN is hello Bob. Greet.lower, that means that www is the lowercase hello world. And greet is unchanged. Greet is still hello Bob with upper and lower, because each of these methods basically say, I'm going to give you back a uppercase copy or a lowercase copy of the original thing without changing the original thing. Search and replace is super useful, super duper useful. And it's pretty clean. Here we have a string, and we use the replace method. In this case, we're passing in the old and the new. Bob, replace all Bobs with Janes. And so that takes this hello Bob and turns it to hello Jane. Again, greet is unchanged. Greet is unchanged. And it does more than one thing. So this says go find, well, let's clear that. This says go find all the O's and replace all the O's with X's. And so it goes and finds 2 of them, and then out come 2 X's. And so that really is replace is not just replace the first one, but replace all of them. White space, as we'll see, is a big deal. And white space is not just blanks, although the most common thing, but it's also sort of non-printing characters like tabs and new lines and other kinds of things. And so we have a number of different ways to strip white space. So here we've got some spaces at the beginning and spaces at the end. And we do an L strip, and that throws away the spaces at the beginning. That's the left, so that's a left strip. It all takes any, if there's nothing there, it doesn't harm it. R strip means throw away all the blanks on the far end. And then strip says go take both sides for strip, and so that pulls out all the spaces on both sides. This will be useful because sometimes when you're tearing stuff apart, you'll find yourself getting extra spaces, sometimes at the beginning, sometimes at the end. And it can be tab or new line. It's sort of white space that is kind of not visible, clear. That's what white space is. It's like if you were on a piece of paper, it's the white space. It's like X. Well, that's not white space, but right here, oh, that's white space. It's any character that doesn't cause printing to happen, if that makes any sense. It's any character where nothing would be printed. And there are characters like that. There's like even bell characters, but we don't use them very much. We can ask very conveniently, we can say, hey, does this line start with a particular string? And so, line, does this is a question, going to return a true or a false. Does this line start with please? And the answer is true, it does start with please. Does this line start with a lowercase p? No, it does not. And so again, you'll use this in the context of if something, colon, some block of text, some block of code. So we can combine these things to tear stuff out. And so let's assume that what we want to do in this case is we want to take a from line. This is from an email format from a mailbox. And this has got the from with a space and the person's email and then @ in the school they're from. and a space, and then the rest of the stuff like when this mail was sent. And this is a real mail message from this guy Stephen from the University of Cape Town in South Africa. And it's really Stephen, and this really is the first line of a file that you'll get to know pretty well by the rest of this course. Hi Stephen, we like you. You are the example in my class and have been for a long time. People actually who know Stephen have taken this class and they're like, Stephen, I saw your picture in the class. So if you're ever in Cape Town at the University of Cape Town, say hi to Stephen and tell him that you saw him in the class. But okay, that's neither here nor there. What I really want to do is I want to extract his school from this email line. Okay, so now eventually we will do things like the data will come from files, but this is still chapter 6. So this is the data we're going to search through. And so we can say, hey, let's go find the @ sign. Search up to this position and find the @ sign. So data.find @ sign. And give me back where that's at. That's in position 21. This is position 0. Then what we're going to do is we're going to look for the next space after the @ sign. So we're going to start at the @ sign and tell find to start here and look forward until it finds a space. So data.find, look for a space starting at the position of the @ sign, and then that'll be in position 31. So 31 is what we get in the space position. So now what we have is we have in two variables, we have position, the position of the @ sign and the position of the space after the @ sign. Now what we really want is this bit right here. So we have to go one beyond the @ sign, and we don't want the space. So we say, we're going to use slicing here, data sub at position +1 up to but not including the space. Oh, smiley face, because we didn't have to say space -1 because that is up to but not including. And so we get that little bit right there. So we don't have to say -1 there because this is not actually included. The thing that's at the position of the space is not included. So that's already a little benefit for the up to but not including. And so when we print this variable out, host, we get exactly just the school that Stephen works at and probably went to, as a matter of fact. I don't know if you went there or not. So this is just kind of a note. For non-Latin character sets, all programming languages from the 60s on tended to work in what we call the Latin character set, which is United States and England and Europe, and lots of places use this ABC character set and the special characters. But it's really common to want to use different characters. And so if you're going from Python 2 to Python 3, and we'll talk about this a little later when it matters more, luckily we're in Python 3, and so Python 3, one of the big things about Python 3 is that all the internal strings are Unicode. In Python 2, there was sort of some confusion as you went between strings, and this is just a little bit of code, and so I'm putting in here, some Asian characters. This is Korean actually. Asian characters into X, and then I say what kind of a thing this is, and that is a string. And then there's this Unicode, and this comes from Python 2. If it's a Unicode operation, it's still a string. Whereas in Python 2, if you put international characters into X, then it was a string, and then there was a separate kind of a constant called a Unicode constant, and it was a different type. And there was ways that you had to mess with these Unicode variables as you did things like read them from files and put them back into files and did other things. So it was much more difficult in Python 2, but we're doing in Python 3, and in Python 3 it natively understands non-Latin character sets, international Asian character sets, Spanish, French character sets. And so this is a good thing for Python 3, and this is one of the real benefits of using Python 3. And as we start doing stuff where we're exchanging data with the outside world, this will come into play, and I'll have to show you how to use it. There was weird things that you had to do. It just makes a lot more sense in Python 3. Okay? So we've talked about strings. We learned about the string. We're converting it. We've done a whole bunch of stuff, and this is again, we're not yet doing anything super useful. We're learning sort of how to like slice and dice, even though we're sort of not making the meal yet. Up next, we're going to talk about files, we're going to read some data, and we're going to slice and dice and use all the things in the next chapter that we've learned up to this point. So see you in a bit. Hello and welcome to Chapter 7. This is the chapter where it all really starts to pay off. We have been learning bits and pieces and doing little 2 lines, 3 lines, 4 lines of code to learn the basic building blocks of Python and learn some of the syntax and define lots of terms. But now we're actually going to start doing something. So if you look at what we've been doing so far, you know, we're inside this little computer, and you type up, the Python says what next, and you give it its command and it does something, and you do something else and does something, and you do this 3 or 4 times, unless you write a loop, and then it goes like, 10, 20 times, and that's it. And then maybe we write a thing that reads something from our keyboard, gives us something back, and then we write something that prints something out, print a few things out, and so we've been pretty much using the keyboard, the screen, the CPU, and the memory. That's kind of where we've been living. And while it's important to talk to the keyboard and the screen, the real world is things like databases that live out here, files that live on our systems, and connecting to the network and reading data from the network. And so that's what we're starting to do right now, is we're starting to be able to work outside kind of our code and create things that are permanent. And so we're going to be talking, initially we're going to work on files. We'll later talk to databases and the network and other stuff, but for now we are talking about files. And so really we're stepping out a little bit and reading things that are permanent and creating things that are permanent. The kinds of files that we're going to talk about mostly are text files, and you can think of these as a sequence of lines in a file that are easily read by Python. You've been making text files all along. Your hello.py, that file's a text file too. You're using a text editor to create that file. You put your Python commands in a file, you run those files, and that's what it is. And so a file can be thought of as a bunch of lines, 1, 2, 3, 4, 5, 6, 7, a blank line here. That's possible. And But the reality is that these are actually just lines, and we have a special character called the new line that we'll talk about in a second. So to read a file, you have to call the open function. And open returns what we call a file handle. Open doesn't actually read the file. Open makes it possible so that you can read the file. So the parameters to open are, it takes one parameter that's required, which is the name of the file, another parameter that's optional, whether or not to read it or write it. If we're reading the file, it doesn't harm it. You can read it over and over. If you write it, if there's already data in that file, it truncates it and writes something. And we're not going to really write files, we're mostly going to read them. And so open you pass it in a file, it gives you back this file handle, and then you have a variable in which you store it. I often call it fhand to be mnemonic. You'll see my code, I use fhand all the time to indicate that that is a file handle. And so if we were to run this in interactive mode, we'll open mbox.txt, and that is a function built into Python, and then it gives us back a handle. It does not give the data. And you can kind of see this when we print out the file handle using the print statement. It doesn't print the lines that are in the file. The lines that are in the file are sort of out there. There could be like 10 million lines for all we know, lines in the file. The handle's like a little opening outside of your program, and you can talk to the file by opening it, then you can read stuff, if you're writing the file, you can write stuff, and then you close the file to shut the handle down. But handle is a thing that allows you to get to the file. It is not the file itself, and it's not the data in the file. It's just a wrapper that kind of allows you. So this, if you print it out, it's like that's the file we opened, we're reading it, and encoding has to do with the different kinds of character sets, which we talked about at the end of the last lecture, that Unicode character set, etc. UTF-8 is a great character set. It's probably the most typical character set that you will run into, although you can have different character sets of files, but most of them are UTF-8. So, of course, this is Python. If you make a mistake and there's a file that doesn't exist, we get a traceback, and it blows up. We'll show you in a second how to deal with that. Now, The new line character is an important part of file reading. And in strings, we can put the new line character in by this \n character. And the \n is the character that indicates that we're supposed to go to another line. Go to a new line. Go to a new line. And so we have, what is this? Well, that's a \n. That's a \n. And so if we print it out, we print it this way, we see that the \n is in there. This is how we type it. We actually type \n to Python to indicate that we're supposed to put that there. But if we do a print statement, it actually interprets the \n, and so the \n causes kind of this movement to the beginning. Now the print actually, at the end of this, adds another \n. So the \n that we put in by putting it into this string is that one, and then print always puts a \n at the end. There's actually a way to override that \n behavior by putting something on the print statement, which we'll talk about later. Now, it's important to note that the \n is one character, right? And so even though this x\ny prints this, and then print adds another new line to go down to here, if you ask how many characters, what is the length of this? Well, it's only 3. That's because that's a character, the \n is a character, and the y is a character. So it's a 3-character string. So the \n is a character like all the rest of the characters, but it's only, we encode it by typing \n. It's called an escape, where the \ is the escape, \n is a way to say new line, because we can't see it. It's a way for us to encode in a string this non-printable character, this invisible character. The white space, it's part of white space. So as we're reading through the file, we can think of it as a sequence of lines, and we can read these a line at a time. We can also read them a character at a time if we want. And so, but it's more common to say read this line, read the next line, read the line after that, etc., etc., etc. But the way to best think about this, it doesn't really matter. You can think about it as lines, and we will in most of the programs that we write. But realize that the way when we see this, when we see it like this, it comes back to the beginning, it comes back to the beginning. There's a character in the file at each of these points to say go back to the beginning. It's like hitting the enter key on your computer. And that is a new line. So you have to think that in the file, in order for your text editor and Python and everybody to know where the lines end, you put new lines in the file. And that's another character. So, you know, this looks like an empty line. This line here looks like an empty line, but really it has a single character, and the character is a new line. And it turns out that in a bit we're going to need to keep track of the fact that every line is ended by a new line. So up next, I'm going to talk a little bit about how to read files in Python. So we're going to find that there's a number of different ways that we can read through the file, but the most common way that we're going to read through the file is to treat it as a sequence of lines, and we're going to use the determinant loop, the for loop, to do this. And so what happens here is we get back this handle that opens the file and gives us back the handle. That handle x file is the variable I just named it x file. That's not the data, but it is a sequence. It is that file handle represents to Python a sequence that we can potentially walk through and then get all the lines. And it's the simplest, most beautiful, elegant way to read all the lines in a file. We use the for loop, and we have an iteration variable. This is going to take, when we talk about the file, cheese is going to be the first line, then the second line, then the third line, then the fourth line. So it's like going through a string, but you're going through a file now, and you're getting it line by line. So that's each line. I just picked a variable named cheese so you didn't get confused. Later I'll call this line, but Python doesn't know anything special by naming that variable line. Okay, and so this is, it's the for and the in, and so I read this as for each line in the file the file handle x file. So run this loop one time for every line and then print it out. So it's actually really quite simple. Okay, other languages like C or C++ or other languages, they have to write while loops with end of file conditions and all kinds of things that make this very difficult. But this is one of the prettiest things that Python has. It's a very, very pretty thing. Okay, so let's talk about what we might do. And we're going kind of back to iterations now. What if we wanted to count the number of lines in a file? Well, this is a basic loop counting pattern. So we open the file, and then like in all these loops, we do something to sort of prime the loop to get it started, set a variable count to 0, and I'm going to use the variable line that's going to go through each of the lines in the file, for line in fhand, down the file, and it's going to run this loop once for each line in the file, and the variable line is going to change. But all I'm going to do is add count equals count plus 1, and so that's just, like from counters, that's just how you detect. So every time we see a line, we're just going to add 1 to the counter. We're not printing the line, we're not even looking at its data at this point. And then when the line is done, however many times it has to go, out it comes, and we print out line count equals count. And so if we open inbox.txt, this is going to do all this work and then print this line out and say line count is 132,045. So this is a little 5-line program that shows you how to count the lines in a text file using Python. Again, simple and elegant and not too much syntax for you to have to learn. Now it's also possible to read the file as a series of characters, all in one go. Read the whole file in. Now you got to be careful depending on the size of the file. This is going to lead to a string variable with a lot of data in it. Now if it's 100,000 characters, that's actually kind of a small thing. But if it was 10 million lines, that would probably not be good. You'd want to read it one line at a time and process each line and then do something. But mboxshort.txt is a small little file. So we open it and we get back a file object, file handle object, and we call the read method, and that says go through and read all the text and give it back in one big blob, one big string, and I'll put it in IMP. And so that's where you have a line, a new line, a line, a new line, a line, a new line. It's not really lines, it's just a sequence of characters with new lines in there to punctuate them. And now you can split that, later we'll see how to split that into separate lines if you want. Now I picked a file that was short, and so this imp variable now has a string in it, and I can use the len function, pass a string into the len function. It says, 94,626 characters. That's kind of a small little file, and perfectly okay to read it all in one go. And so now I say just print the first 20 characters. That's beginning to up to but not including 20, and so it shows the first 20 characters of that little file is a from line, because this is a mailbox file. Now, let's say we're going to do a searching, and we did this loop where you're looking for something. And so we're going to search for lines that have a prefix of from. Okay, that's what we're going to do, and we're going to print those lines out. So there's lots of lines in this file. Line, 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 from. Line, 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 from. Right? On and on and on. And we only want to show these lines, the ones that match, right? That's what we want to do. And so we are going to write an open statement, and then we're going to loop through, and we're going to ask the question, if the line starts with from, print it. So sometimes it's going to skip, 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 and then it's going to run it, and then skip, 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 and it's going to run it, skip, 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 and then it's going to run it. Okay? So that's the basic idea, and then it'll finish when it's all said and done. And so this is like a criteria. This is like a search. We're looking for lines that match the string, that have the string from as their prefix. Now, when we look at the output of this, it's kind of weird. We see kind of these little blank lines that show up. Blank, 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 blank. What's going on here? What's going on? So let's take a quick look. The problem is new lines. Well, I mentioned that the file has new lines in them. And so when you do the for loop, it doesn't throw the new lines away. As you might expect, it would be kind of nice if it did, but it doesn't. It actually shows you when you read, it reads that first line up to and including the new line and gives you that back as the variable. So that is the first new line, so that means it's going to go down. And then the print statement actually adds another new line. So that's the second line of the file has a new line at the end of it, and the print statement adds another new line. So if we take a look at the code, there is a new line. Oops, come back. If we take a look at the code, this variable line has a new line in it. Oops, where am I at? I'm in the wrong slide. There we go. Yeah, this is the one I want to do. If we look at the code, there's a new line in here, and then the print adds another new line. So the print adds a separate new line. And that's how we get two new lines. The print statement's new line and the new line from the file. here's how we fix it. And you're going to write this code a lot because when you're reading text files, you end up with a new line, and often you don't want the new line. But thankfully, as we saw in the previous chapter, there is a nice little function in Python for strings called strip that allows you to throw away white space. And to review, remember, white space is anything that doesn't print. And this new line is not a non-printing character. So rstrip gets rid of it. So it's a way to get rid of white space. And rstrip does it from the right end. So it's the right end of the string. And so if we just are going to loop through all the lines in the file, we say line equals line rstrip, and then this variable no longer has the new line at the end of it. We have our little if statement, and if we print it, then this line, the data has no thing, and then the data has a no new line in it, so the print only goes down one. And so now we have single spaced output. And so you're going to be doing that a lot. It's really common to read through a file and then just strip the new line or any trailing space off the end of that. Now, there's a couple of ways to do a loop like this, and let's just think of this as we're looking for a file with lots of different lines in it, and we want to ignore all the lines except some, say, good lines, and we want to do something with those good lines, or the lines we're looking for. Needle in a haystack. This is like searching for a needle in the haystack. So if you look at this code at a high level, we're going to loop through everything, and then we're sort of picking which lines are, and these are the good lines down here. Now often we have a bunch more code that we want to do, and we're not just printing them, but we're going to do a lot of code. So sometimes you actually structure the loop a little bit differently. And so the way to do it, and this is going to do the exact same thing, it's just a little different way of thinking about this loop. So the top part is the same, we're stripping it, and what we're doing here is everything's the same here except we add this not. If the line does not start with from, that's the translation of that. If the line does not start with from, continue. So basically we have a skipping pattern. So the lines we're not interested in, we skip. So we come down, we skip a lot of lines. And then we find a line that's good, and then we fall through. So this is the good code, and then we have all the other good code that we want to do to that line. We have that showing up down here. And so there's just two patterns, two ways to do the exact same thing. So another way to select the lines that we're interested in is to use the in operator. So we talked before about the in operator and how that works. So we're basically going to use the continue skipping method. So we're going to read all the lines, these first few lines. If uct.ac.za is not in the line, skip it. And so this is going to print out all the lines that have the string uct.ac.za in them. And so you see this is the output of the program, ... Sometimes you'll have programs that want to read different files. Often I give assignments where I say, show me how this program runs on the short file, and then show me again how it runs on the long file, just like this. And so the way we do that, to input the file name, instead of making the file name be a constant to the open call, we make the file name be a input. So we just run an input statement, which gives us a prompt, and then we type mbox.txt, and then that shows up in this variable f name. It's of course a string all the time, and we pass that into open, and then we open it, and then we do the count operation. So if we enter mbox.txt, it counts 1797 subject lines in mbox, and if we give it mbox short, it says there are 27 subject lines in mbox. And again, this is another one of those ifs, and it's just counting, but only counting lines that match a particular pattern. Okay, so now the user can also type bad file names, and we need to be able to deal with that as well. And so we're taking a small change to the code. The dangerous code is this line right here. This line right here is going to trace back if that file doesn't exist. So what do? Well, we're going to just expand that. The rest of this program is exactly the same. The only thing's different is we've got this line. We took out insurance on it, and we know that it might blow up, and so we have it in a try and except block. So here's how the code runs. So, the input runs, we type in a good file name, it comes in here. This works, and so it skips the except, and so it runs the code and prints out the count. So that's the good pattern. The bad pattern is here, where we type in a bad file name, it comes in the try except, this file name is nanaboo, and it's going to blow up. So this line blows up, so it jumps down into the accept code, prints out, file cannot be opened. So it prints this out. Now this quit is really important, because if we don't put this quit in here, it's going to continue down here, and that's going to blow up here because file handle is not defined properly at this point. And so what we have is we have this quit. Quit is a special function where it comes in and never returns. So this is a way to terminate the entire Python program silently with no traceback. All right, so we put in our own error message, so we look like we're professional, say, could not open this file, and then we stop. If you don't, it's going to come down here and it's going to trace back right there. It's going to blow up. So the quit is useful when you want to stop executing because you've detected some kind of an error. So that's a quick zoom through opening and reading through files and doing some patterns. Most of the rest of the programs in this course are going to say open for rstrip, look for, and then do something interesting. That's going to be our loop that we're going to do over and over and over again. And now we see how this looping and if and iteration and variables are starting to come together, and you can actually sort of do a program that does something useful. But before we get to too many more programs, we got to switch a little bit, switch gears, and talk up next about data structures, and that is the shape of data and how we can use more intricate and complex variables to help solve our problems. Hello and welcome to Chapter 8. We're going to talk about lists in this chapter. Up to now we've been talking about algorithms. Algorithms are the concept in computer science of using the programming language to express the steps that you want the computer to go through to solve the problem. Read some data, convert it to a floating point number, check to see if it's greater than 40, do one thing if it's greater than 40, do another thing if it's not, then print out the result. Or open a file, read everything. If the first line starts with something, do something. If not, skip it, and then add all the things up. Those are steps. Those are a series of steps, and hopefully by now you're getting to the point where you have a good understanding of steps. But there's a whole other side of computer programming, and we call it data structures. And data structures is not the steps, but instead clever ways that you lay out the data and clever ways that you make sure that the data does what you want it to do. And so that's what we're going to start talking about now. Lists are the first and the simplest data structure. Strings are kind of like data structures, but lists are probably our first real data structure that we're going to think about and design and make use of effectively. But before we talk about what is a collection, we should talk about what is not a collection. So we're familiar with what a variable is. We know that a variable is a little piece of memory that's got a label on it, and then an assignment statement, you know, sticks a 2 into X, and then and then 2 is in this little cupboard, and then it goes to the next line, and then 4 goes into X, and so the 2 goes away and the 4 is there. Now, a key thing is you can't have more than one variable at any given moment, right? And more than one value in a variable. So when we move to collections, collections are more like suitcases. We can put lots of things in them. We have ways of organizing them, and as we go through lists and dictionaries and tuples, we'll see how there are different ways to organize them. And as a matter of fact, we've been talking about lists for a while. Every time we use one of these square bracket syntaxes in earlier programs, we've been working with lists. And so this is technically a 3-item list with 3 strings, got commas here. Joseph is one string, Glenn and Sally are another string. And here's another one that is another thing. And the list is basically, it's a list constant and it's being assigned into a variable. So this friends variable has 3 things in it. So that's different than what we've been talking about before. So these bracket structures with square brackets are those lists. And so the print is just a print with parentheses to get the print to work. But 12476 is a 3-item integer list. Red, yellow, and blue is a 3-item string list. But it doesn't all have to be integers or strings. Python can handle different things and different kinds of data in different positions in the list. So red, 2498.6, a 3-item list with a string, an integer, and a floating point number. And while we're not going to use this too much for now, this outer list is a 3-item list, and the second item is another list. So this is kind of alluding toward what we'll do when we start talking about data structures. And that is, we have a structure and then we have another structure inside of it. And sometimes this can get quite complex. And we're doing this for a reason. This here has no reason, just to show you that it's possible that lists can be made up of lots of things, including other lists. And of course, there is also the notion of the empty list. And like I said, I have had to be able to tell you about lists all along. We use them in for loops. We can put lots of things here. We can put file handle here, we can go through the file, we can put a string there, we can go through the characters in the string, and in a list. And the iteration variable then goes through the successive elements of the list, and that's why this prints off y4, 3, 2, 1, and then the loop is done and it prints out blast off. So we've been using them, and we've been actually iterating through lists with for statements all along. So the the for statement, has been something we use with lists, and when you just need to go iterate through the list and go through every item in order, the for is a great way to do that. So friend is our iteration variable, friends is our list variable, and so that says friend is going to successfully take on the value Joseph, Glenn, and Sally and print out, Happy New Year, Joseph, Glenn, and Sally. It runs 3 times, once for each of the values, and the iteration variable advances. Now, I do want to make it really clear that the choice of friends and friend singular and plural is arbitrary and capricious. It happens to be convenient and intuitive that the iteration variable is 1 and the list variable is more than 1. But Python has no idea about singular and plural. As a matter of fact, Python would care. It would be totally equivalent for Python to do the same thing, to have the list variable be z and the iteration variable be x. X will take on the successive values of these 3 things. Now, am I being nice to you by calling this list friends and this iteration variable friend? I am, but I also don't want it to confuse you if you're just a beginning developer. So, just like strings, we can sort of look within lists. Part of the thing is when you put more than one thing in a data structure, you need to get them out. And so lists have positions, they maintain order, and so the first thing in the list is the sub-0 position, sub-1, sub-2. Just like strings, they're zero-based, just like European elevators, they're zero-based. So if we take a look and we say, oh, friend sub-1, that's how I read that, the little square brackets, when you take a variable here and you say friend sub-1. Remember, singular and plural don't matter. Friend sub-1 means Glenn, because this is the 0 and that's the 1, and then Sally's the sub-2, and so that's what prints Glenn out in this particular thing. Now, lists are mutable. Mutable is another word for changeable. They can be changed, meaning that a list has 3 things. You can change this thing right in the middle if you want. To take a look at what's not mutable, strings are not mutable. So if I take a look at assigning banana into fruit, well, fruit sub-0 is a capital letter B. Could we imagine for the moment that we could change fruit sub-0 to lowercase b? Well, the syntax would be how you would do it if you could do it, but it turns out that strings are not mutable, meaning they're not changeable once you create them. And that's why when we do things like lowercase or uppercase, we take a look at the fruit and we say, give me a lowercase copy of that, and then we take the return value from this and we store that in x, and that's how x becomes a lowercase banana. But fruit is still the original one, so fruit has not changed. Compare and contrast that with a list though. Here we have a 5-item list, 2, 14, 26, 41, and we're going to do the sub-2 position, and the sub-2 is 0, 1, 2, so that's that one right there, and we're going to assign a 28 into it. So that 28 is going in here, going to wipe that out and put 28 in. So we can do item assignment in lists by putting a bracket syntax on the left-hand side to say, don't just put it in the variable, put it in this position within the variable. So that's what that's doing, and when you print that out, the 28. Everything else is unchanged, meaning the whole list is there. There could be 1,000 items in the list, and then you're changing the second one. We have a function called len. We've been using this len function all along to take a look at how long strings are. It counts the number of characters in the string, so that's a 9-character string. If we have items in a list, len tells us how many items there are. It's not like how many characters there are, it's the number of things. And each thing doesn't have to be a number. It could be a number, a string, or even another list. And len is the way to say, hey, how many things are in there? There's a function that returns a list of numbers, and we use it as we'll see in a second, to construct specialized loops to go through lists. So let's take a look at this range function just for a minute. So range takes as its parameter the number of numbers that you want returned. So I'd like a 4-item list with the numbers 0 up to but not including 4. And so it just turns out that that is really useful for constructing for loops that are counted for loops that go to 0 to the 1 to the 2, as compared to the the definite loops that go each way, go through each one. And so it's a common thing to say, okay, we know how many things are in this list. There are 3 friends, and if I combine range and len, so I take len friends, which is 3, and then I take range sub 3, I get 0, 1, and 2. And so the interesting thing is this 0 corresponds to the first one, 1 corresponds to the second one, and 2 corresponds to the third one. Okay? And so we'll use this to construct loops, especially when we need to go through an array and remember what position we're at. And so here's just an example of 2 different loops. This is a for loop that's just going to go through whatever's in this list. So friend is just going to take on the successive values, and so it's going to print out these 3 things just as you would expect. And if you don't need to, while you're going through the loop, know the position, your relative position from the top in the loop, that's okay. But sometimes you want a little more sophisticated loop, and instead you want to be able to loop through where you know the position. And so what we do instead is, instead of looping through the list itself, we do range len friends, which gives us 0, 1, 2, and then I takes on the successive values 0, 1, and then 2. So this loop is going to run 4 times, and I is 0 the first time. And we might even just look up the value inside that sub-0 value, so we get Joseph the first time, so prints out Happy New Year Joseph, goes, and I becomes 1 now, and so it gives us Glenn, and that prints out, and away you go. So if you look at these 2 loops, they really do the exact same thing. The only difference is this we allowed the 4 to find its way with the iteration variable through, and here we created our own I variable that went through the positions, and they're dense, there's no gaps in here, so it's 0 through 2 that it goes through. So these 2 are equivalent. There will be times when you'll want to use one in the other. I tend to prefer the first one because it's prettier as long as it works for me. So that gets us started with loops. We'll be back in just a bit. Okay, so we've taken a look at loops, and now we're going to just take a bit of a look at some of the operations that you can do with loops. Python has this, as we'll soon learn, object-oriented approach to its operators, and the plus can add strings and it can add numbers. It can add floating point numbers, integer numbers, strings, etc. And so the plus similarly works this way with lists. The plus looks to its left and looks to its right and says, what am I adding? And in the case that I'm adding the list 1, 2, 3 and the list 4, 5, 6, it concatenates them together. In this way, it sort of functions like a string, and so we get 1, 2, 3, 4, 5, 6. It's just concatenate this list to another list. And it doesn't change A or B, just like in any kind of assignment statement. Calculations on the right side don't change the variables, and they produce a new variable and then assign that into C. You can also use list slicing, and it's easy to remember. If you remember how strings work, list works exactly the same way. So it's, of course it's a little tricky. The first number is the starting position. They start at 0. So 1 is right there. So it's the 0 position, the 1 position. Start at 1, right? But go up to, but not including 3. There's 1, 2, 3. So this goes up to, but not including 3. And that's why we get 4112 out of that. So up to, but not including. I'll just say that over and over and over again. If we do, you can leave the first part out. You can leave the first part out here, and you can say, oh, up to, but not including 4. So that starts at the beginning, goes up to, but not including 4. And so that's how we get that piece right there. We can say, start at the position 3, 0, 1, 2, 3. Start at position 3 and go to the end. Now the fact that the number 3 is in here is sort of irrelevant. 3 to the end is those 3 numbers. And then you can do the whole list with slicing as well. Again, these pretty much are the exact same examples I used when I was doing strings. They're pretty much the same. There's a number of different methods, and you can look up all the documentation in list. I often just use the dir command to remind myself of them. Append will look at. Count looks for certain values in the list. Extend adds things to the end of the list. Index looks things up in the list. Insert allows the list to sort of be expanded in the middle. Pop pulls things off the top. Remove removes an item in the middle. Reverse flips the order of them, and sort puts them sorted order based on the values. So let's look at a couple of these. So if we build a list from scratch, we have a way to ask for an empty list. There are a couple of different ways to ask for an empty list. We could use just two square brackets next to each other, but this is a form we call the constructor form, where we say, hey Python, make a list. In this case, the word list is like a reserved word to Python. It's really a reserved class, but say list parentheses says make me an empty list, and then assign that list into stuff. So stuff is now it's a list object, it's of type list, but it has nothing in it. And then we can call the append method, stuff.append, and stick book in. And then we say, oh, and that knows how long, the stuff knows how long it is, where the end is, and how to add something to it, and then add a 99 to it, and we print it out, and we got book and 99. Reminding ourselves that lists, while they're often the same types of variables, same types of values in the various positions in the list, it doesn't always have to be that way. Then we say, oh, we'll stuff that append cookie. You can keep on going, and then we end up with three things and the cookie. We have an in operator. It works pretty much like the in operator in a string. Is 9 in my list? And that's pretty simple, and the answer, of course, is yes, 9 is in my list. Is 15 in my list? Looking through, no, it's not. 15 is not in my list. And then there's the not in operator. You can think of that as kind of like one operator. Is 20 not in the list? And the answer, since it's not there, is true. And so that's a way to just, it's kind of like starts with or in for strings, same kind of stuff. Lists are in order, and they're sortable, and so this is something that we take good advantage of. A lot of what computers want to do is sort stuff. Look all these things up, append them, and then get them sorted. And so there is this method inside of list that's just the sort method. So here we put three values in 0, 1, 2 position, 0, 1, and 2, Joseph, Glenn, and Sally, and then we tell the list to sort itself, and then we print it out. Now this is actually sorted the list in place, which is different than upper and lower, because if you remember, strings are not mutable, but lists are mutable, and so you say, hey, just sort yourself. Okay, and so just sort yourself, and then it sorts it, and then it's in alphabetical order, Glenn, Joseph, and Sally. I happen to be clever. I only put strings in there, and I put my uppercase and lowercase in a very consistent pattern, but the list is changed. And if I look at list sub 1, that is the second item, which is Joseph, that prints out right down there. There's a whole bunch of built-in functions to help manipulate lists. The other things I was showing was sort is a method that's part of lists, but there are other functions that take lists as their arguments. We already talked about the len function, tells you how many items there are. There is, pretty obvious, max, it says go through and find the largest. Min, go through and find the smallest. Sum goes through, adds them all up. And we can say let's do average by taking the sum of all of them and dividing it by the length. And you might think to yourself, oh wow, I wish we'd have known this a few chapters back when we were having to write all those loops to do max, min, sum, largest, smallest, etc. You can kind of think in your mind that inside each one of these functions is a loop that does pretty much what you did in those chapters. And part of the reason we did that back then, even though these things were here, was they're kind of easy loops to understand. And so those are there. And basically there allows two different ways of building loops to do the maximum minimum. Now it's not necessarily all that much easier to to do something using these, because you either can do them the old way, or you can make a list and then use these functions. So let's take a look, and I'll just say that these two bits of code are doing the exact same thing. And what they are is they're implementing a program that's going to repeatedly ask for numbers until we type the word done, and then it's going to compute the average and tell us what they are. And so using sort of the stuff from the loop chapter, we start with a total variable and a count variable, set them to 0, and then we read a number, we check for done to break out, but then we convert it to a floating point value. And then we say total equals total plus value and count equals count plus 1. And so this is going to run over and over and over again, however many times we're going to do this. And then it's going to pop out, and when it's done, it's going to have this value of total. The running total will become the overall total divided by count, and it'll print the average out. Okay? And so that's kind of how we would have done this before we knew how to do this with lists. Now, let's take a look at the other one. In the other one, we say, let's make an empty list. Remember, this is that constructor syntax that says to Python, make me an empty list and assign the empty list. It has nothing in it, right? But it is a list, has nothing in it, into the variable num list. Now we're going to write another loop. This part here is the same, these 3 lines. Read the number, if it's done, quit, and convert it to value. But instead of doing the actual calculation right now, what we're going to do is just append it to the list. So the list will start out empty, then the 3 will be in the list, then the 9 will be in the list, then the 5 will be in the list. So we're appending, each time through the loop, we're appending into the list. So we're just growing the list every time I read a value, instead of actually computing something with the value that we've got. So in either case we get value, and in one case we append it to the list. And then finally it finishes, the break happens, and then we just say, oh, hey, Python, sum up everything in the list, add these 3 numbers together, and then divide it by the length of all those things, and you'll have the average. And so these 2 things give us exactly the same output. Now there is one difference. If there was like 1 million or 1 billion numbers, they actually have to all be stored in the memory simultaneously. Whereas here it's actually doing the calculation of the billion numbers and not using up so much memory. For most of the things that you're going to be doing, the difference in memory, there is a difference in memory. This one here uses more memory, but I can't draw very well. More memory. It uses more memory, but it doesn't really matter by the time it's all said and done. And so for you, the difference between these things is not all that significant, but it's important to understand that they're just 2 techniques to accomplish the same thing with lists. So now we're going to wrap up and talk a little bit about how strings and lists are related. They're sort of related in that they both have zero-based things, and we use the square bracket operator to do various things. But there's a lot of situations where we're looking at our data and we're combining the use of lists and strings. So let me show you the first thing, probably the coolest thing. We're going to use it a lot the rest of the class, and that is the split function. So let's take a string. We've got ABC here. It's with 3 words. What we're interested in, the fact, is that there's spaces in this word. And what split does is says, you know, I'm going to look through this thing, I'm going to find this, and I'm going to break this into pieces, and I'm going to return you a list of the separate individual pieces. So look for blanks and break it in pieces and give me back the pieces. So I'll print these out, and now you see that it's a list with 3 items, with 3 words. The spaces are gone, but it's given it to us. So it's like, split this into words, please, and give me the individual words, and give me a list of individual words rather than a big long string with spaces in the middle of it. And that is a quick way to go from a line, and it's really common. A lot of things we're going like, go get the second thing or the third thing or whatever. So the split's really nice because then you can just grab stuff. And so you say, oh, how many things did I get? Well, I got 3. The len function tells us that. And I can print the first word I got, which is with the sub-0, and that'll be like with, will be the first word because that's the sub-0 position. So I read something, I split it, I can say there's 3 things, and I can look at stuff, the first word basically, without really knowing much. Now if you remember earlier, and we'll see this, we used find and slicing to do a similar kind of thing, but people tend to prefer the split. And you can, you know, oops, go back. You can also then loop through them. So you can split these things into stuff as a word and then go through with W, and then it's going to go through, W is going to take the successive with 3 words. And so you can make a loop by reading some data, splitting it, then writing a for loop, and then it's effectively going through the words in that line of data. And so that's a really powerful concept that we'll use in a lot of the programs that we're going to write. Just a couple of bits about this and how it works. Split with no parameters here, it looks for spaces, but it also treats a bunch of spaces as a single space. And so it's pretty smart about that. And so even though this has a lot of spaces between lot and of, you only see lot of, all the spaces are gone. It does something special about spaces. It's really white space. So tabs or new lines or other characters would also qualify in split, basically. Now, you don't always have to split based on spaces, and a lot of data that you're going to run into, you're going to want to split on something else. And so here's some data that looks like we're using colons to separate the first, second, and third piece. Now if you just call split, split's looking for spaces. And so split gives you back a list of the things broken apart with spaces, but there's not a single space in that line. And so we get a list, see it's a list, but there's only one item, and the semicolons are sitting there. Split doesn't go like, whoa, this looks like it should be semicolons. You know, split's job is to use spaces and split the string based on spaces, okay? But given that this is something we like to do, you can tell split what character you'd actually like to split on. Now, it's not quite as clever when splitting on something other than spaces. It doesn't understand that, you know, if there's a bunch of semicolons in a row, it still thinks of those as splitting points to split. But in this particular case, where there's no spaces, you know, and it's going to split that. So it says split this based on the semicolon, based instead of being based on the space. And so if you take a look at what comes out of this, we split on semicolon. Now we have a 3-item list, and we get first, second, and third. And a lot of your data comes out of some logging system or some router status updates. Who knows what you're looking at? But the delimiter is often something other than space, and you can do that with split. So this is a useful thing when parsing things like our email address, right? We wanted to get things like the email address, this second piece, off of the line. And so we can use split to take advantage of this. And so here's a little loop that's just going to print out not the email addresses, but instead the day of the week. We're going to print the day of the week out for all these things. How do we do that? Well, we can observe really quickly that if we split based on spaces, it's the 0, 1, 2. It's the 2 position. So we can quickly write a bit of code that, you know, opens the file, then loops through the lines. We do this all the time now. Strip takes off the end of the new lines. We can check to see if it starts with from space, right? From space is our key, so we're ignoring all of the lines that don't start with from space. But then we find a line that starts with from space, and we split it, and then we just print out the second word. And so we get the second word of the lines that start with from, and that's how this thing works. Now, sometimes we want to dig into it deeper, and we will take something, split it, and then split another piece of it again with a different delimiter. And so let's just say that the thing that we want to achieve is getting the part after the @ sign for email addresses. And we did this with, again, find and pose and stuff like that, but you can use split to do this as well. So the first thing we're going to do is we're going to take this line, we're going to split it based on spaces, right? Chop, 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 chop. And the fact that there's an extra space there doesn't matter. Split happily just like zooms through that. And then words sub 1, 0, 1, 2. Word sub 1 is this email address. So we'll put that in a variable called email. And so email will be a string that's just this. So in 2 lines, we've pulled out this second address into a variable. Then what we're going to do is we're going to re-split that. We're going to take this string we've got and split it based on @ sign because we know it's an email address. So we get a new set of pieces. The first part is the person's name, and the second part is the host name that their email is hosted on. And then what we can do then is we just happen to know that this is the 0 item and this is the 1 item, so we can get at that. So the interesting thing of going here, if you think back to how we did this before with find and pose and all that stuff, it's really a lot cleaner. And we don't, for me, I can look at this after you understand it, and it's easy for me to understand that it's correct. Whereas that pose stuff, you got to add one and start the second find after. Just remember that. And this is a lot cleaner way. And this is a more typical way of pulling this kind of information out of a line. So in this chapter we've talked about lists, we've talked about the concept of collections. That's our first data structure. We're not just doing algorithms, we kind of know algorithms now. But now we're going to do data structures. And this chapter and the next 2 chapters are our foundational data structures. And then we'll, like everything, we'll make more complex data structures by composing those data structures together. We've looked at how strings and lists connect together and how split works. And these are all really powerful tools that we're going to use going forward. Now we're going to take a look at how we would write some code to do some parsing, read some data. As a matter of fact, we're going to read through our famous mailbox data, look for lines that begin with from space, and extract the third word. As a matter of fact, we already have some of this code already written. We're going to debug it. We're going to look at code and we're going to debug it. And so here we go. Here we have it, and it's a pretty basic program. It opens a file, loops through the file, throws away the white space, splits it into words, and checks to see if the 0th word, the first word, is from, and if it's not, we skip and read the next line. And otherwise, if we find a line that starts with from space, then we print the third word, which is word sub 2. Okay, so this is what we've got, and we carefully saved this file into the same folder that we've got, ex08. And so let's go ahead, cd desktop Python for everybody, ex_08. And so this is some files. We got our day of the week Python and our inbox short, so that's sitting there, okay? And so let's run this program. This is the program that we've got right here, Python 3 dow.py, and it doesn't work. Now, by now you've seen a few tracebacks, and there you go. So, you know, when you look at a traceback, you think to yourself, well, I made a mistake, and you've gotten pretty good at looking at that line. So there you are. You're like, this is the line. There must be something wrong on this line, and you want to change it. But that line's not actually the problem in this particular thing, and so you got to be careful sometimes. And one of the things that you didn't notice in this one right away is that it actually worked. It printed the first line out. So if we take a look at our data set, it found the line started with from space, it split it, and printed out the third word. And it blew up later. And so part of the problem is that we don't know what it was doing when it blew up. And so the first thing I'd like to do in this kind of a situation is find the line and make sure there's a print statement right before it. And so I'm going to print words, colon, and then comma WDS. I want to print right before the line that blows up so that I know really when this finally does blow up what was going on in that line. So I'm going to run it again. And oop, did I forget to save it? No, I forgot to save it. Look at that. See the little blue dot? Forgot to save it. So now we see a whole bunch of output, and we see that it's actually doing a whole lot of work before it's blowing up. And so you see that it prints the words out from that first line and prints out Saturday, which is exactly what we expect. It's the third word in the line, and then reads a whole bunch of stuff. And it's actually, what it's doing now is ignoring. Let me just put something here. I'm going to say print ignore, so I can keep track of when these lines are being ignored. So let's run it again and have the word ignore pop up, right? And so it's doing a lot of ignoring. It finds these words, prints out Saturday, reads this line and ignores it, reads this line and ignores it, reads this line and ignores it. So a lot of stuff's going on here that you might not realize. And so we have to take a look at what the problem is. And so it is now blowing up word sub 0, and now we can scroll down and we can look at exactly what happened right before the traceback. So we really now know exactly what happened before the traceback. And the interesting thing is that there is an empty string. I mean empty array. There's an array with 0 items. So I'm going to print the line out too. Print line colon. Now I haven't changed my program at all. I'm just trying to figure out what's going on here. So I'll save that and I'm going to run it. And we've got a lot of stuff and it's still working. It reads a line.
It reads a line, splits it into words, and then prints out Saturday, which is the third word on the line. Now here it reads a line, and this line is a blank line. And it has, because it's a blank line, the split returns no words, and that's what blows up. And the problem now is, oh wait a sec, list index out of range. So word sub 0 is not valid, which is the first word, when there are no words. So this is a statement that works most of the time. Now you might think, oh, I want to just put a try and except in there. Well, the right thing to do is to say to yourself, oh, wait a second. If I don't have enough words, if the length of the words is less than 1, continue. So basically it's going to come through here, it's going to split it, and if we don't have any words, meaning it's a blank line, then we're going to skip it. So let's run that. So now this ran all the way to the end. It did a lot of stuff, and it did not blow up specifically, didn't have a traceback. Another way to protect this would be to, we'll take this part out. This is called a guardian pattern. Right? Guardian pattern, because this is dangerous. This could blow up, but it won't blow up if it makes it past here, and it won't come through there under the conditions that are causing it to blow up. Another way to do this might be to protect it as follows. To say, oh, wait a sec. If the line is a blank line, no, continue. So now what we're going to do is we're going to skip blank lines. I even say this. Print skip blank. So if it's a blank, we're going to skip blank and keep going. This will skip blank lines. It'll come through here, and this will skip lines that don't have from, but because we're not processing blank lines, word sub 0 always works. So I can run this code, and it works again. So here we have a blank line, we skipped it. Here we have a blank line, we skipped it. Now here we had a non-blank line, so we parsed it, but then we ignored it. And then up here we'll find a from somewhere. Doo-doo-doo-doo-doo. Let's find a from. Here it comes. Oh, no, there's ignore, ignore. I got too much debug print. I can't find it. Here, I'll just hunt for from with find. Okay, so there we go. There's from, and we print the thing out. So we're getting a lot of extra stuff. So I'm gonna comment out some of these debugs. And I'm actually just going to get rid of this whole skipping of the blank line. I'm going to do it with the words. I'm going to go back to the guardian we had before. If the number of words that we got, len of words, is less than 1, continue. Okay, so now this is going to be a working program. Oops, I gotta take another print statement out. Gotta take another print statement out. We sort of know what we're doing here. Okay, so this looks like a pretty safe thing. This guardian is protecting this dangerous. I'll get rid of that one too. This is the words that are traced back, and nothing else in this thing changed from when we started except we've added this little guardian. Now the interesting thing is if it comes through here and prints word sub 2, what happens if somehow we find a line that has from as its first word and there's only one word on, this is going to blow up. So we can make our guardian a little stronger. And we can say, you know what, we're gonna skip this line if it doesn't have 3 words in it. So it has to have at least 3 words. And if we see less than 3 words, we're going to skip it. And that just makes the guardian a bit stronger. And so the program works safely, and And you see these things where sometimes you want to check to see that your assumptions about the data are reasonable, and skip things where the data is not reasonable. Now, so that's one Guardian pattern. Let me show you a slightly different way to do this, and this is with an OR statement. So I'm going to take this code, copy that, and put it here with OR. Get rid of all this stuff. Well, this is the Guardian in a compound statement. So what we're saying is if there are less than 3 words on the line, or if the first word is not from. Continue. Now, we're doing this in order, because the way it works is OR is true if either that's true or this is true, but if it knows that this is true, then it doesn't bother checking this. And the checking of this is what blows up, what causes the traceback. So if we flip this order, it would fail. If we do it in this order, it will work. So let's do this one right. It works. But if I get this backwards, it's going to check this before it checks this. And we're going to go back to failing again. So you got to get the order of these things right. The Guardian comes before, in the OR, the Guardian comes before. And if this is true, then it doesn't check this. This is called short circuit evaluation, where it knows that as long as this part's true, it doesn't evaluate this second part. And so now we have a Guardian in a compound statement. You'll see this a lot. Sometimes if it's more complex, you do it in multiple statements, or you fall through, check for sanity, and only run the code. So I hope that was useful to you, looking a little bit about how to debug, where you don't just start chopping on the line that had the problem. It's not always that line, because we never did change that line. Although we did change it a little bit at the end. We added this Guardian here, but we also fixed it without it. Sometimes you add some print statements to figure out what's going on before you just start chopping on that line. So again, I hope this helps. Thanks.
Hello and welcome to Chapter 9. Now we're going to talk about Python dictionaries. Python dictionaries are probably the thing that most programmers love the most about Python because they're very powerful. They're like a little in-memory database. It's the second of our kinds of collections, and probably the best collection. To review what a collection is, it is a situation where we are going to have a variable, like a list or a dictionary, that we can put multiple pieces of information in rather than a single piece of information. And of course, prior to collections, we would put something into X, and then we would put something else into X, and it would be overwritten. And now with lists, we can append things onto the end. And so if we compare lists and dictionaries, the list is sort of the organized version of the collections. Everything stays in order. You add something, it always adds to the end. You take something, it sort of compacts itself. It's 0 through the n-1, where n is the number of items. And so it's very organized, kind of like a Pringles, where the potato chips are nicely stacked. Dictionaries are messier. You can put things into dictionaries. There's no real sense of order in dictionaries. Everything has a key, so you sort of throw things in and they kind of mix around in there somehow, and you pull things out based on the key. It's like you sort of stick a label on it, where you say, okay, I'm going to take this thing and I'm going to put Chuck on it, and I'm going to take these sunglasses with the Chuck label, and I'm going to throw it into the dictionary, and I'm like, hey, give me back Chuck. I'm like, oh, here's your sunglasses, because you mark everything. This is like the key. This is the value. I took a pair of sunglasses and I threw it in. So it's kind of like a purse, or it's a sort of like a mess. And so the idea is you have these labels that you put on everything that you're going to throw in. Like, I'm going to put, hope it won't stick to my keys. I don't know, what else do I got here? I'm going to stick a label on my pen, a Chuck label, and I'm going to store a pen in my dictionary with the Chuck label. And so it's like having a purse or a bag or a backpack where you have things labeled, and you can throw things in and label them, and you can shout into your bag and say, give me the calculator, or give me the candy, or whatever it is that you have labeled them. You have to come up with the labels, and then you can use the labels to get things back out. And like I said, they're probably the most powerful thing, and they're basically this concept that's generally referred to as associative arrays, which means they're like lists, but they have these keys. And so the associative means the association between a key and a value. Whereas in a list, there's a position in a value, and the position is less powerful and less flexible. Most modern programming languages have this notion of associative arrays. If they don't, they're sort of unpopular, because once you get using them, you're like, whoa, they're so powerful. If you ever find yourself in a language that doesn't have them, you'll freak out. They have different names like property maps or hash maps or property bags, depending on the language you're using, but they all are the same thing. They're key value pairs. So the idea of a dictionary is that, or the idea of any collection is putting more than one thing in, and then the difference is that you have ways of indexing it. So this basically line says, let's make ourselves a dictionary, just like we constructed an empty list, and I want to store 12 into this dictionary, and I want to label it money. And so on the left-hand side, when we use this money, that's the label that we're going to give it. And so 12 is being placed in the dictionary. That's like taking the 12, throwing it in the dictionary with a label of money. 3 is going in with a label of candy, and 75 is going in with tissues. And we say, what's in there? And there's no order to it. And sometimes the order can even change inside of a dictionary, although there are more advanced versions of dictionaries that maintain some kind of order. But for now, let's just not worry about the ordering of them. If we say what's in there, you say, oh, there's 3 things in there. There is 12, 75, and 3, and stored under the keys money, tissues, and candy, respectively. We can ask, using the index operator, what is per sub candy? That's like saying, hey, give me back candy, and out comes the number 3, which is that. And we can update stuff. So we can say, go grab the candy version, add 2 to it, make 5, and then store that back into candy. And so now we see that candy has been set up to be 5. And and so if you look at the difference between lists and dictionaries, they both can have new items added to them. We haven't talked a lot about deleting, but items can be deleted from them. The difference is the indexing mechanism, how we look things up, how we store things, and how we look things up. So we make an empty list, we make an empty dictionary. We add 21 to the end, and we add 183 to the end, and we ask it, and it says, oh, position 0 is 21, and position 1 is 183. We don't see the positions when we print it out because it's sort of implicit. Here we're going to mark 21 with age and stick it in, and mark 182 with course and stick it in, and then we're going to print it out, and there we got course and age mapped. And we can add a 23 and stick it back in age, and that overwrites. So the 21 becomes the 23. We can do the same thing in a list, except we say lists of 0, because in lists the indexing is position, and so this 21 becomes 23. And again, you just look at them and you can think of each of these as pretty much doing roughly the same thing, except the indexing mechanism. The values are the same, but the keys are different. So in lists, the keys are always the position, and you don't get to assign those other than the fact that the order in which you put them in implicitly assigns a position. And in dictionaries, the key is a string. You can actually use other things. I use strings a lot in this lecture, but that's just to kind of keep things simple until you get good at it. You can actually use numbers as the dictionary index, the dictionary keys if you want. But the values are things you put in and manage in those dictionaries. So we can, just like lists, we have dictionary literals. And what's nice about dictionary literals is that they use the exact same syntax as the printout. And so it starts with a curly brace, ends with a curly brace, and then has a series of key colon value, key colon value, key colon value. And this is sort of the associative array bit. We are associating 1 with the key Chuck. We are associating 42 with the key Fred. We're associating Jan and 100. Then we print it out, it kind of looks exactly the same. And so the print statements in Python are nice in that you ask what's in a thing, you show the stuff, and it shows you in the syntax that if you type that into Python, that would be how you do a constant. And if you just say empty array, you see me also do DICT. this is constructor where you say make a new empty dictionary. This is an empty dictionary constant. These two things are pretty much the exact same thing. This is a shortcut to doing this. The empty curly braces is a shortcut to do the construction. So up next we're going to talk about sort of one of the really common applications of dictionaries, and that is counting. So now we're going to talk to you about one of the common applications of dictionaries, and that is making histograms. It's counting the frequency of things. And so if you think of a histogram as, it's a little graph, and there is, how many A's, how many B's, and how many C's, and there's a histogram that says, oh, there's this many of that, and this many of that, and these are like buckets, these are frequencies, and this is how many times it happens. So a histogram. But we're going to do this thing where we're going to count people's names, and we're going to kind of count how many that we see. But the interesting thing that we're going to solve, just like many of the things in the computer, is we can't just sort of look at the data. We got to look at the data iteratively, one piece of data at a time. So I'm going to give you a little problem. Okay, I'm going to show you a series of names one at a time, and I want you to count for each name, make a little bucket, and then keep counting how many things for each of the different names. Okay, you'll notice that you have to start with one and then you move across. So just watch this and tell me what's the most common name of the set of names I'm about to show you, and how many do we see? So what was the most common name and how many times did you see it? That's the question. Now, here comes the reveal. So for humans, it's so much easier for you to just look at this and you think, how did my brain look at that? And you're like, okay, what is pretty common? Oh, maybe Chen is common. Oh, Chen, no. Maybe Zhen is common. 1, 2, 3, 4. Yeah, anybody else have? Marquard's got 3, C7. And so you'll notice how our minds, without computers, we just sort of like bounce, branch and bound. We have hypotheses, and then we decide, yeah, it's Zhen. That's it, and there's 4 of them. Now, how did your brain think about this as we were going through them one at a time? Well, my guess is if you really had to do this a lot, you would make a little picture like this. And then what you would do is if you saw a new name, XYZ, you'd add it to the list and give it a tick mark of 1. And then if you saw like C7 again, you'd give that a tick mark. And if you saw XYZ again, you'd make a tick mark. And then you'd keep adding to these tick marks, right? And that's how you would do it. And you wouldn't, like many of the things we do in a loop, you wouldn't really know what the most common was until the end. And then you'd sort of take a look at these numbers and you say, okay, that's the most common number, and then you'd be done. But you have to watch them one at a time. You can't just bounce around. And so that's how we're going to use dictionaries to achieve that. Again, instinctively as humans, we just look at the stuff. But if you had a million things, you probably want to write a Python program and use dictionaries. And so this is the idea, and there's 2 basic things that happen. One is the first time you see a name, you got to say, is this name there already? If it's there already, you really just want to add 1 to it, right? That's the adding of a tick. Or you want to see for the first time, blah, 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 and give it a 1. And so you can use the name as the key. And then 1 is the value. And then first time you see Chen, you stick 1 in there. And so at this point, inside the dictionary, sort of dynamically adding, as soon as it sees a new name, it adds another slot in here. But then if you see the same name again, like Chen again, then you end up with a 1, add 1 to it, and so it's 2. And so at that point, Chen is 2. And so you can see how you can both extend the dictionary by encountering a new name, or adding when you see a name that you've already seen before. The problem with dictionaries is, like everything in Python, there are rules about what you can and can't do. And one of the, I think, kind of frustrating things about dictionaries is that you can't just look for a key that doesn't exist. So this is a fresh brand new dictionary. We do a constructor there and we print out sub csev and boom, it blows up, and that's bad. But we can solve this by the in operator. The in operator we've used in the for loops, we've used it in lists, we've used it in strings. So that is a question. It's saying, is csev in ccc? Well, this is this empty one, and so it is, no, it is not. Csev is not in ccc. And so using this in operator, we can avoid the traceback. We can say, if it's not there, put it in. If it is there, add 1 to it. And that leads us to this bit of code. Okay, and that is the kind of code that we're going to build a histogram. This is going to histogram code, okay? And so this is going to have name as our iterator, names. Sorry, I made them singular and plural. That's nice, but so name is going to be csev, chen, csev, gen. Now normally we'll be reading this from a file, but for now we'll keep it easy. We're going to go through this. And we're going to have counts as our dictionary. So that starts out empty, and we're going to do a simple if then else every time through the loop. If the name we're looking at is not in the dictionary already, is the key, then set it to be 1. If it's not, go get the old value, count subname, and then add 1 to it and stick it back in. So this line right here is new, adding a new thing, and this line right here is adding some things to existing things. And you do this long enough, you start with an empty one, and you do this long enough, at the very end, it will print out the histogram that you're looking for, the histogram you're looking for. And so you say, oh, we've seen csev twice, gen once, and chen twice. And so that's the idea. And so this can run 1,000,000 times if you want. Now, this notion of checking to see if a key exists and doing one thing if it doesn't exist and doing another thing if it does exist is such a common practice that the dictionary object has this method called get that collapses these 4 lines into 1 line. And so the idea is you're going to do one thing if it's in there and you're going to retrieve the current thing. Otherwise, you're going to pick a default value. In this case, we'll pick 1. I mean, pick 0. This is like the default, right? Meaning what is not there. And if you say counts, now counts is a dictionary, .get, that's like string.upper, that's a method. You give it a key and then a default. And if the key exists, you get back what's in the key. If the key doesn't exist, you get the default. Okay, so, and with no traceback, this works. So the best way to think about this is those 4 lines are equal to that 1 line, because X is either going to be whatever was in there before if it exists, or it's going to be 0. Now, the nice thing about 0 is the next thing we're going to do is we're going to add 1 to it, so that's going to get us to 1. So collapsing that loop that we saw before, we can make it just a 1-line loop, and this will become an idiom. This will become something that you will get used to and you will use over and over and over again, and after a while, right now you're looking at it, boy, that's a lot of syntax and semicolons and whatever. After a while, you just type this and not even think about it. It's an idiom. It's basically included in this idiom is how to both create new entries in dictionaries and update existing entries by adding 1 to them. So everything else in this is the same. Name is going to go through these 5 values, and we're going to say count subname equals counts.get name, comma 0 plus 1. And so if, for example, this already has a 1 in it, then this is going to be 1 plus 1 becomes 2. If it's not, it's going to be 0 plus 1 equals 2. And so this is the idea of if new, set it to 1, not 0, set it to 1. Because the first time you see something, the count should be 1, not 0. So that's why we make this default. Now the get can be used for anything. It just so happens that 0 is a common default because it's really common that we're using this to basically make a histogram, right? Little histogram of A, B, C, right? And so we need to make a D, but then the histogram has to start at 1. So that's basically the simplified counting with get. And you know, there's a lot of things that we're going to do inside of Python that do have to do with frequencies and how many times certain things happened, and this pattern is a really good pattern to absolutely know. So now what we're going to do is we're going to switch from just looping through strings, but instead loop through files. And it's going to take a little bit of work because we have to open the file, and we'll bring a lot of things together at this point. So here would be another task, and that is here's a bunch of text from the book, And you can just split this into words and count and find out what the most common word is and how many times it occurs. So go ahead and try to do this for a second. Feel free to pause. Actually, don't bother pausing. This is too hard. We should write a program for this. It's not easy. Humans don't like this. It makes you concentrate. And so here is a counting pattern where we're going to take a line, and then later we'll read this in a file. And so this is just an adaptation, improvement of the previous thing. So we're going to start with an empty dictionary. We're going to ask for a line of text and read it in. And then we're going to use split. So remember the list of words? Well, what we're going to get here is a list of words. We'll print it out, and we'll run this counting. This is the little loop. For every word in whatever this was, we're going to do this idiom of either adding a new entry or adding one to an existing entry, and then printing that out. So let's take a look at what we get there. So if we run this, we can give it some text, and I've got this will be all one line, and then it splits it into words, and you see that these words here are split, 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 split. I mean, that's strings and splits. Remember, strings and lists and split. And so now the counting is going to go through this list. The clown ran after the, and it's going to build a histogram. The clown, one clown, the up, these things are going to go up, right? That's this histogram. And then when it's all said and done, we end up with the histogram. And so counts is the dictionary that ends up with a histogram. And we can, by inspection, see, oh, the is the most common word. And there are 7 of those, right? So if we sort of take a look at this, we start out, we make a dictionary, we read in a line of text, the text goes in, and then we split that, and we print the words out. So these are the words, right? Then we have a for loop that's going to loop through all those things and then produce a dictionary. And when we print the dictionary out, that's what we're going to get. And the is 7, okay? So that's one line of text. That's how you walk across the words in a line of text after you've split the line into separate words. So now we're going to look at ways that you can loop through dictionaries. We just produced a loop that can build a dictionary, but now we're going to look at a dictionary. And so we'll start with a very, very simple example, and then we'll work to a slightly more complex example. So here's a dictionary, just the constant. Chuck is 1, Fred's 42, and Jan's 100. And so we're going to use a definite loop with the for key and counts. Now it doesn't have to mean key, but key is a good name because these are keys and values. K, V, keys and values. I just mentally think of this as keys and values and keys and values. So this iteration variable is going to walk the keys. It's not going to walk the values. It's going to walk the keys. Chuck, Fred, Jan. Not necessarily in that particular order. As you see, it goes Jan, Chuck, Fred, because just because I typed it in this order, it's not like a list. It doesn't stay in that order. It might move around a little bit as we add data to it or as we set the data up. And so you can, in the loop, you can get the key, and so that's what prints out the Chuck, Jan, Chuck, Fred, but then you can also get the corresponding count for each one of these by just pulling it out of the array. Pulling it out of the dictionary, right? And so we can pull out the corresponding value, and so we print out Jan 100, Chuck 1, Fred 2, and that runs this loop 3 times. So if you just use the in and you give a dictionary here, remember all the different things we've been able to put there on the end of a for loop. And dictionary is another thing we can put on, and we get a list of keys. Now there's a couple of methods that allow us to get the keys, and so we have, we can say turn this into a list, and we get a list of the keys. So this is a dictionary, the same dictionary. We get a list of the keys. You can also get a list of the keys by using the keys method. So that's take this dictionary JJJ and give me all the keys, which gives me a list, which is kind of the same thing. And then we can ask for the values, and they give me just then the values extracted out of this dictionary. So that's nice. Now the one thing is that while I said you can't predict the order, if in 2 statements you ask for the keys and then the values, they at least come out in the same order, even though you can't necessarily predict the order that they come out. They come out in the same order. And then there is a third thing that we can do, and that is ask for the items. And we can say, give me the items. And that gives us a list. This is our first really kind of composite combined data structure where it is a list, a 3-item list, 0, 1, 2, and inside that there is what are called 2 tuples. Jan maps to 100, Chuck maps to 1, Fred maps to 42. Coming up next, we're going to have a whole chapter on that, and so just take a look at that for the moment, and we will come back to that in some detail later. This whole items idea that gives us back a list of key value pairs, because it's not just a list of keys or a list of values, it's actually a list of key value pairs, allows us to write in Python a very clever and elegant loop. What we can do is actually, this items gives us back, each item in the list has a key and a value, and we can actually take two iteration variables. For AA, comma BBB, this is two iteration variables, and if you're coming from another programming language, this is super cool, and it's a Python only feature. I never have seen another language that's capable of doing something this simple and that elegantly. So what this basically does is says we're going to simultaneously advance these two iteration variables. So this is going to be the key and the value, the K and the V. Key and the value is going to be Chuck 1, then they're both going to advance. Fred 42, Jan 100. And so that means in this simple loop, if we just print them out, we're going to get the key value pairs, of course in the order. And so it's sort of AAA and BBB simultaneously walk down these key value pairs. And so that's really pretty, and it makes for a very succinct loop. The syntax is a little sort of disquieting when you first see it, but it's a super elegant thing, and you just have to say items. If you don't say items, you just get the keys. If you say items, you get the key value pairs, and you have to have two iteration variables. If you don't have two iteration variables and use items, it'll complain and say, what are you doing? I'm giving you two things, and you don't have two variables to receive them. So two iteration variables and items are basically related. Now, we're going to take a look, and this is code that I showed you perhaps many weeks ago about, I said this is a little story about how to read a file and count all the words in the file. And now we're back to it. And at this point, you should understand every single character of this program, every single concept of the program. You should literally stare at this and look at it, code it, play with it until you absolutely understand it. So let's take a look. Again, I showed you this weeks ago. So we're going to ask for a file name. Then we're going to open the file name. Then we're going to make an empty dictionary. Again, this is all stuff you've done before. And then we're going to have an iteration variable that's going to go through the lines in the file. Right? So line is going to go line, line, line. Then we are going to split that line, each line into words. Chop, 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 chop. So that's words is the list of the words in one line. We're inside of a loop that's going to go through all the lines. And then what we're going to do is we're going to have the word iteration iterate through each word in the line. And then what we're going to do is take each word in the line, and we're going to do this histogram. Right? So we're going to, this is going to run not only just for every line, but for every word in every line. So we have a nested loop for every line, then we split it, and then we go across the line. So it's almost like a typewriter where we go ding, ding, and that's what we're doing. Ding, ding, ding. So it's like the outer loop is going down, down, down the lines, and the inner loop is going across, across, across the words. And eventually we are going to see in this last line, every single word in the file. And we're going to do the counts get word plus one, which is our magic histogram making line that if you don't remember what that is, go back a couple of slides. I just talked about it. At this point in the code, and it's important to be able to draw these lines, at this point in the code, you have the histogram, and it's in the variable counts. Now, we want to find the largest one. Now, we have written loops that can find the largest in a list, but now we want to find the largest value in the key value pairs of a dictionary. So we're going to start with we're going to know what the largest count is, and the largest word has that count, and we're going to set them both to none, because we're going to prime our loop. We have to prime our loop, and we're going to say to none. And so then we're going to write one of these cool things that says for word, comma, count. So word and count are going to go through the key value pairs, because we've got items here. So it's going to go through the key value pairs, loop through each key value, whatever it was. There could be a million words in here. We're going to go through every one. And what we're going to do is we're going to make sure that big count is the current largest count we've seen so far. And if it's none, well, then we haven't seen anything. Or the count we just read is greater than the big count so far, we are going to jump in. And this is sort of like, oh, this is a new personal best count for this particular data set. And so we're going to remember the word in big word, and we're going to remember the count in big count. So this is just a max loop. It's a maximum loop with the extra thing that we're recording, in addition to what count is the largest, what the word that was associated with that count, recording it. So again, this is a starting part of the loop. We're going to do some work, and then when we exit the bottom of this, big word is going to be the word that is the most common, and big count is the number of times. And so if we run a file, we say, oh, in that file, 2 is the most common word, and it's 16 times. If we run the clown file, well, the is the most common word in 7. And so this now is, and this could have a very large file and give you the most common word. And so that is sort of a really good application of dictionaries. So dictionaries are the most powerful, well, they're the most powerful collection we've seen so far. It is good to see both lists and dictionaries to understand what collections are. They are things inside of Python that can handle more than one item inside of it, and we'll learn about another collection about tuples in a second. Just understand the get method, because that leads to very compact code. Understanding there are various ways to iterate through dictionaries, and so we've learned a lot. But in the next section, we will learn even more and put these together and do some sorting and do some other stuff, and really start to see the real power of dictionaries.
I'm going to do some coding. It's related to the dictionaries chapter, chapter 9. And we're going to do some word counting. That's basically right out of the slides but I'm going to just write the code in front of you rather than have you look at it in the book. So what we're going to do is I've got my text editor up here, and let me start by making a new folder. For my chapter 9 exercise, and then I'm going to go and make an untitled file. That was from the previous one, and I'll do what I always do, print hello, and save it. And save it here into exercise 09 and ex09.py. So now I have a folder that's in my py4e folder, and that happens to be in my desktop. py4e is my folder on my desktop, and now I have all of these subfolders: cd, ex08, ls is dir on Windows, ls, oops, I got to go up one, ex09, ls. So I've got that file right there. Now I'm going to want to read some files, and so I'm going to bring some files down. A couple of files, Python for Everybody Code 3 intro.txt. So I've got this URL, and I'm going to save it, save page as, and it's really important that I save it in the same folder as I'm going to write my code, just so that when I open this file it knows where it's at. So I've saved that one, and I'm going to also take this clown text. I'll use this to make my life simple, so I have a real short thing that I can show you how it works. And so now if I go back to my terminal, I see I've got exercise 09 Python, intro.txt, and clown.txt. Okay? So let's go back to my text editor and get started. I will prompt for the file name, input, enter file, :space. Now I'm going to do something. If the length of the f name that I just read is less than 1, I'm going to say fname equals clown txt. I do this so that I can just hit enter and it defaults to clown.txt. If I want to give it a different name, I can. So this, if I just hit enter at this prompt, then this will give me a string that's 0 length. So if it's less than 1, I'll just assume that. So let me open that. Handle equals open fname. And let's read through it. For line in handle, we'll strip it. Line equals line.rstrip to take the white space off the right hand side, and then we're going to say print line. Again, I'm not just doing this. I really, when I write code, I just saved it. When I write code, I do these kind of stuff all the time just for my own sanity checking. And so now I'm going to run Python 3 ex09.py just to test that. I'm going to hit enter now, and it's going to assume hopefully clown.txt if it all goes well. And yep, it read one line. Okay, so that part's working. I'll just leave that print statement in. The next thing I want to do is kind of a classic thing where we're going to go read a bunch of lines and then go horizontally across those lines in words. So I'm going to split that. WDS equals line dot split, and print WDS. So I'll print that, and I'm going to save it and test it. I really love to test things over and over. There's the actual line. This file, clown.txt, only has one line, and it breaks it into words, and so I have those words. Let's just run it again with intro.txt. So this will have a lot of lines, line, lots of lines. Every line prints out the line and then prints out the words that we split it into. Okay, so now one of the things that I do here is I want to believe, now I sort of can believe everything from here up. Like, oh, it's going to open the file, it's going to read through the lines and going to split them into words. And so then I'll just kind of behind it, I'll just say, okay, I'll just comment that out. Now I need another for loop for W in WDS. Now words is a Python list and has some number of words in it, 0 or 12 or whatever was on the line. And now I'm going to print out the word. Okay, and so now it will go through that horizontally. Now I'll just do clown.txt so that you see I'm not printing the line out. That's the words that have been parsed split from the line, and now we got this loop. Now, one of the things that's interesting is just to make sure that you're going through all the words, and I like a print statement here to know that W is going to successively take on literally all the words of this file. So if I comment this print statement out and I run it again, clown.txt, that for loop starting from here is every word in that file, which happens to only be one line. But now if I do the same thing for intro.txt, it's just going to go through the words. And in a sense, by nesting these two loops, we're going to hit all the lines. And that's a lot of stuff, but it hit all of the lines, all the words, and away we go. Okay, so here's where a dictionary comes in. I'm going to make a variable called di for dictionary, and I'm going to say give me a dictionary. Now dict is not something you can choose. That's saying that's defining the type of dictionary. Di is a variable that I chose. Okay, so the key thing to this dictionary is we're going to make a counter, and we're going to use W, the word, absorb, elegant, whatever, and we're going to use that as the index. So the simple thing to do is to say if W is in di, then we can say the dictionary sub the word, which is our key and the key value store of the dictionary, is equal to the value that we had before in that area, d sub W plus 1. And if it's not in there, else di sub W equals 1. And I'm going to print print new. So every time we see a new word, it's going to say new. And I'm going to also then print W and the current value of the counter for W as it's going through. Now notice how far in I'm indented. This is all part of this inner loop. So this is the loop that's going to run every single word. Okay? And I'm going to run this first with clown, so it runs slowly. Okay, so we saw the was new, and the count is 1. Clown is new, count is 1. Ran is new, the count is 1. After is new, the count is 1. Now we saw the again, but now we made the count be 2. let's print here. I'll say existing. So you can kind of see it. Now in the print, I'm printing this. Let's make it even a little more verbose. Print W. And then I will make it so it prints the word before and the count after, and then whether it's existing or new. So we're put a lot of print statements in. Print statements are cheap. Okay, so now we see the word the. It's the first time we see it, and we set it to 1. We see the clown. It's the first time we see it, we set it to 1. We see ran, new, 1. Later on, we see the. It's already in. So existing means it was already in the dictionary. W as a key was already in the dictionary. Okay, and so that's why we added 1 to it. So the old value was 1, and then we added di sub the equals di sub the equals di sub the plus 1. W is the string the, T-H-E. That's what that string is. Okay, and so we've made it all the way through, and you see the in this one line occurred ultimately 7 times. So now I want to print out the contents of this dictionary at the very end of both loops. So I got to de-indent twice, and so that will give us the counts. And so this is what we get when it's all said and done. You know, the happened 7 times, but it just worked through its way through. Okay? So you got that. Now, this is a pretty verbose way of doing this, but I did it sort of the slow way to show that there are 2 situations. If it's already there, you increment it, and if it's not there, you set it to 1, effectively inserting it, right? So you insert it and set it to 1 with this di sub the equals 1. Okay? But let's get a little less verbose here, get rid of some of these print statements because we kind of covered all that. Get rid of this line and go back to printing W and DIW at the end. We'll leave that one in. So what I want to do is I want to look at this bit of code right here, this if W in DI else. We do this so much with dictionaries that there is an easy mechanism to do this that combines these 4 lines into a single kind of contraction. And so I'm going to do this. I'm going to print, let's put 2 stars out, then the word and di.get of the word, comma, negative 99. Okay, and so this di.get of the word is the important part. The way it is this is a dictionary. .get says in its first parameter is the key to look up, which is word like the or fell or clown or whatever, and 99 is the default value that we get if the key doesn't exist. So this is in effect an if then else, right? This little di.get w99 negative 99 is, you know, if it's in there, do one thing. If it's not in there, do something else. Okay, so let me show you how this works, and you'll see that the 99 will happen when okay, so the first time we see the, get returns 99. Right, so let's move it over here. The first time we see the is not in the dictionary. So this di.get of the word the in the dictionary gives us back the negative 99. Okay, and this still is working, and so the is 1, clown is whatever, but away we go. Okay, let's do it this way. Let me comment this out. Let me comment this one out and run it again so it's a little clearer what's going on. Okay, so the first time we see the is not in the dictionary. The first time we see clown, and we know it's negative 99. But here we asked for it, and the is 1 because we've seen it before. And so that's just this get mechanism allows us to get the new value, or get a value out if the key exists and specify a default if it's not there. So I'm going to go old count equals di.get w comma 90 comma 0. So instead of using 99 here, I'm going to just get rid of all this. Is what I'm saying is look up in this dictionary. Get is a function that's part of all dictionaries. Look up using the key W, which is the, and if I don't get it, give me back 0. And so I'm going to say print word, comma, old, comma, old count. And now what I can say, whatever the old count is, it's either the value that was in there or 0. And now I can say new count equals old count and now let's see, new count, and I can say dictionary sub word is equal to new count. So instead I'm going to get rid of this if then else then. This is basically saying look up the old count that we have. If you don't find one, use a 0. We'll print that out. And then I'm going to say afterwards I'll print the new count. Now, and so we'll print the old count. Here are some of these blanks. Print the old count. And you can see the old count with the, because the doesn't exist, was 0. The new one's 1. Clown's old is 0. New is 1. Clown's old ran, old 0. But now we get to the, its old count was 1, and now its new count is 2. Okay? So by using this get and saying if we don't find it, we'll assume the count is 0. That makes a lot of sense, right? You know, if not there, the count is 0. If the key is not there, the count is 0. Okay? So that's what this line does. If get the value from under the key associated with the key, or give me 0 back. And then I can take that old number and just add 1 to it and then stick it back in. Now this is ultimately not how we tend to do it. Okay? We tend to blend this all into one big long statement. di sub w equals this part plus 1. Okay, so that says get the old value from this key or 0 and then add 1 to it, because that really combines all of these lines into a single line. Okay, so I'm going to delete them now. And now we've combined this all into one, what effectively is an idiom. Retrieve, create, update, counter, all in one line. I'll still print out, in this case I'll just say di sub w, and then we'll see the counter. Okay? And so now I'll run this. We have a new, but now we see it the second time it's 2, and so we see car the first time, we see that the second time, we see car, the third time, we see car the second time, and away we go. Okay? And so that's pretty straightforward. And so it really kind of, a typo there. So let's just get rid of that and run it with the clown stuff, and we get the right data there. And let's run it with intro.txt. And there we go. Okay? And so it's tearing out a bunch of words and giving us a dictionary. So that was a lot of work to get to this line 16 that has the dictionary in it. Now we want to find the the most common word. And so we're going to loop through this dictionary, and part of it is like, once we printed this dictionary out and we verified that it's right, don't worry too much about the code up here, right? Matter of fact, I can take out some of these print statements, and we can kind of trust all this. And so now we're going to work on this. Okay, now we want to find the most common word. Now this is like a maximum loop. So if you recall, we have a whole set of key value pairs. Communicate goes to 2, is to 2. Skills is 3. So we have these key value pairs, and we're going to loop through and look for the maximum. Now, in a dictionary, we can loop through the key value pairs with the following syntax. For, you know, I would call these variables k and v for key and value, but yeah, in the dictionary's name dot items. And items is a method inside of all dictionaries that says give me the key value pairs, and we need 2 iteration variables. So this is like an assignment statement for k and v. K and v take on the successive values for the keys, the key and the value. Okay? So if I just now print k comma v, and I'll take this print statement out and then run the code on, oops, what I forgot to, oh, I fell back into my Python 2 days. Need parentheses for my print. So there's clown, and it just prints it out. And it's kind of the same thing, except it's pretty, where we're putting each one on a line. Okay, so the v is the value. So we're looking for the largest value. Oops. So the thing is, we know that the values are always numbers that are greater than 1. So I'm gonna do kind of a quickie maximum loop. Largest equals -1. Now in previous times we've seen that this is a bad assumption, but because we know these are counters that are always positive, it turns out this is not a bad idea. And so I can say if the value is greater than the largest we've seen so far, largest equals the value. Okay, and when that loop is all done, we can print the largest. Okay, and so this is just a max loop, and we're using this value. That's the number. The value is the second thing. Oops. Can't type Python. Oh, it's a typo. Yeah, I'm not using value, I'm using v. So largest equals v. Let's try it again. Okay, so we're all done with 7. So these were the things that we were looking for, and it was looking for the maximum, and it just dutifully found 7 was the largest. But we also want to know what the word is. And so what we can say here is we can say the word is none, meaning it's just like we don't know what the word is. And then whenever we catch this new largest number, we say the word equals W. So I like to think of this as capture, remember the word that was largest. Right? That's what I'm doing. Remem, remember. Right? That's tough. R-E-M-E-M-B-E-R. There we go. So we're gonna this trick here is not only knowing what the largest number was, but the word that was associated with the largest number. So now I can print out at the end the word and the largest, and that's the count. Okay, and so now we know that. Oops, did we make a mistake here? Okay, that does not look good because it says car and 7. If v is greater than the largest, oh, It's not W. I used a really bad variable. See, that's the old value there. There we go. It's K, which is the key. Key. I was going to say, that was quite the bug. See what happened there? I had this as W, and it just happened to be, it was the last word on the file. Car, the last word in the file, because I used a wrong variable. Right? No, little mistakes, little mistakes. The and 7. Okay, so let's get rid of this print statement because we kind of know what's going on here. And away we go, and this should now work if we run it. We can even get rid of the word done here. There we go, the 7. Now, the cool thing about this is this code runs just as easily with one line of code or the intro of the book, intro.txt, and not surprisingly, the is still the most common word in the introduction.txt. I seem to like that word, and it's 226 times. Okay, and so that is the basic pattern of reading some. This is just a word loop. Now, sometimes there would be some, checking to see if the line is the one you're interested in, maybe tearing apart the line, but it's at the end of the day, this idiom of starting a dictionary. Now, it's a common problem to know where to start the dictionary. You want to accumulate the numbers for the whole file, so you don't want to put it in between line 6 and line 7. Okay? So I hope that particular thing helps a little bit, helps you understand dictionaries.
Hello and welcome to Chapter 10. Now we're going to talk about our third kind of collection called tuples. But tuples are really a lot like lists. There's not too much to them. They're really kind of reductionist version of lists. They're so they function very much like lists in that they have things, and the difference is there are no square braces. There is a parenthesis, round brace or whatever, and they have positions 0, 1, and 2, just like a list. And you can look things up, x sub 2. So x sub 2 is actually the third element here, and so that prints out Joseph. You can assign, make a tuple here. This is the constant syntax for a tuple, and print that out. And the print statement shows you that this is a tuple, not a list, by showing you round parentheses. And a whole bunch of functions that work with lists work the same way with tuples. You can put a tuple at the end of an in statement into for, as you might expect, and then it iterates through the tuples. Tuples maintain order, so it prints out 1, 9, and 2. So literally, this bit of code here could be identical whether it was a list or a tuple. It really would do the exact same thing. The difference between tuples are that they are immutable. Once you create the tuple, you can only sort of assign a tuple, but you can't modify it. You can modify a list. So if we take a look at a list here, we make a list that's 987, and we say x sub 2 equals 6, well, that just means this 7 becomes a 6, and that's just natural, meaning we can reassign slots. We can delete things, we can insert things, we can mutate them, we can change them, so they're changeable, right? They're changeable. But if we try to do that same thing with a string, so we say y equals ABC, and we know that this is position 0, 1, and 2, but if we try to say, let's change the C to a D by saying y sub 2 equals D, that is not allowed. And it says it doesn't support item assignment, and this little bracket, x sub 2 is what they call item assignment inside of Python. And so if we do the same thing then with a 3-element tuple, put that in Z, and we try to change this slot to be a 0, it's going to blow up because it's the exact same thing. And that has to do with the fact that once this assignment is made, this is not modifiable. Now, it turns out that the reason it's not modifiable is for efficiency. They take up less storage, they are quicker to access, and they're really designed internally behind the scenes in ways we don't really need to understand. They're just more efficient than lists. If all you want to do is store a list and look at it and then throw it away, you probably should use a tuple instead. So there's a lot of things that you can do with lists that you also can't do with tuples, but they're really just a corollary of this notion of non-mutability. And so, like, you can sort a list, but you can't sort tuples. You can add a 5 to the end of 3, 2, 1. can't do that in a tuple, but you can in a list. And flip the order. Dot, 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 dot. So anything that you can do to a list that modifies the list, not allowed for tuples. And so you can take a look at the kinds of things that are inside, the methods that are part of each list: append, count, extend, index, insert, pop. Many of these are modifying, and then count and index are the only ones that work for tuples. And so tuples are limited lists. Now, at some point, there's going to be a but here to say, why do we like them? And the reason that we like them is that they're just more efficient. They don't have to build Python in its own internal organization of these objects. It knows that they'll never be modified, because when you make a tuple, you as the programmer are saying, I'm never going to modify this, and Python won't let you do it. So it's higher performance, better memory use, and to a beginning programmer that doesn't really matter, but that's the reason. And so we tend to use tuples when in situations where we're going to make a temporary variable and then temporarily use it just a little bit and then throw it away without really messing with it. And we tend to use lists to build things up, etc., etc., etc. So the other thing that's interesting about tuples, and we've actually sort of seen this, is that you can put a tuple that includes variables on the left side of the assignment. And this takes a little getting used to, but it's really cool, and no other language that I know of does this. So if we say x comma y, that's a two-tuple. Both have to be variables. You can't put constants on this side. It's like saying x equals 4, y equals Fred. Right? So what happens is you can put a tuple on the far side of an assignment statement, and the 4 goes to x, and the Fred goes to y. And you say, what's in y? Well, y is indeed Fred. And so this is like two assignment statements. Now, the way I've got this syntax, I would probably do, two separate statements, just not to show off that I know how to do tuples. And so here's another one, and they just move correspondingly. If you don't have 2 here, and you do have 2 here, well, if you have 3 here, or 2 here and 3 here, and you don't match the number there, you get in some trouble. Now, if you just say x equals tuple, then that is the tuple in the list. But this is just a simple straight 99 value going into A. So you can put tuples as the left-hand side, and you can even do things like return a tuple from functions. That's a real nice Python feature that I like a lot. Tuples are also related to dictionaries, as we've seen in the previous chapter. So here we make a little dictionary. We make an empty dictionary by constructing an empty dictionary, stick it in D. So D is sort of like this place that can hold key value pairs. And we put csev, and there's a 2 in there, and chen-wen, and there's a 4 in there. So we have this, associative mapping between csev and 2 and chen-wen and 4, all stuff we know. And now we say, hey, we're going to loop through the key value pairs here, and we've seen this syntax before, k comma v. So this is a tuple. So you can think of this as each one of these things is going to get assigned into this tuple, which means the key ends up and the first one's the key and the second one's the value. I use the variable key kv all the time in code that I write, just for my own sanity. So kv are going to iterate successively through the successive keys and values in that. So this is going to run twice, and k is going to be csev 2 and chen-wen 4. The order just happened to stay the same. And so if you say what is in one of these things, you can actually take d items, the items method within that dictionary, and say, hey, give that to me back, and then print tups. And it's a special kind of a class, but really ultimately it is a list of tuples. This is 2, this is the 0, and this is the 2, the 1, the first and the second. And then within each thing you get, you have a 2-tuple. And so, in a sense, this k and v are iterating through those things when we're putting d items here and d items there. One nice thing about tuples is that they're comparable. They're comparable in the same way that strings are comparable, meaning that they're compared from left to right, with the leftmost or 0 tuple being the most significant. And it doesn't compare any further than it has to if it's asking less than. So if it's looking at, say, this first tuple, it starts at the left and says, okay, ask the question, tell me true or false. Is 0 less than 5? The answer is true. And so the answer to this overall expression is true, and it doesn't even compare those two numbers, those second and third number. They don't compare them. If, on the other hand, we're asking, is this less than that, it only looks at the first one and asks if it can answer the question. And the answer is, well, they're both 0. And so I can't answer the question, so I have to go to the second one, second pair, and 1 is less than 3, and so that means this is true. And it does not check this, even though 20 million is bigger than 4. It doesn't matter, because these are the numbers that cause the true to happen. And the same is true if you do this with strings. Again, we start the first one, so Jones, Sally, well, that's the same, so we don't know the answer yet. And so Sally, Sam, well, okay, S, oh, they're the same. A, they're the same. O, L, and M. L is less than M, so, so the actual letter that makes the difference here is the L and the M, and leads to us being true. And so it goes left to right, but then even when it's doing strings, it's going left to right. That's just how string comparison works. And if we say is Jones Sally greater than Adam Sam, well, we check the first one and we check the J and the A. Well, J is greater than A, and so we don't have to look at anything else. We don't have to look at any more of these characters. We don't have to look at the second thing in the tuple. We have to look at that is enough to be true. So it only scans until it has a definitive answer. It doesn't scan any further. So now what we're going to do is use this comparable capability to sort these lists of tuples and then bring this all back and connect it more to dictionaries. So now we can take advantage of the notion of comparing tuples and use sorting. And so what we're going to produce is a list of tuples, and then we're going to sort them, right? And so we can get a list of tuples from a dictionary, and then we can sort that list of tuples, and then we can end up sorting dictionary items by taking this two-step process. Convert dictionary to a list, sort the list, and then we can have assorted dictionary values. Okay? And so we'll do this a couple of different times. So if we take a look at this code right here, we have our happy little dictionary, A, B, C, A maps to 10, B maps to 1, C maps to 20. Like, what are we going to get here? Well, it comes out, the mapping is the right way, but the order is whatever. And now we say this function called sorted, which takes inside a sequence and then returns us a sorted version of that, a list that's sorted. And so it says sort D items. So it's basically going to take this list and compare the A's and the C's and the B's, and because it's a dictionary and all the keys are unique, there's never going to be equality, so it really is going to just sort this by keys and never get to looking at the values. You could construct a list that had duplicate, you could make a list of tuples that had duplicates in the first, like we did before, but given that this coming from a dictionary, the first thing is going to always be unique and distinct. And so if we say sorted D of items, that we're passing this stuff into sorted. Sorted is going to go around, move stuff around, and then give us back a sorted version, sorted in ascending order based on key, without looking at the value. And so that's a way to see dictionaries sorted by key, is just say sorted of D sub items, and sorted is a function, and so it just fixed stuff. And so this is the kind of loop that you're going to write to do that. You know, we did this before. We took sorted and we got these sorted by keys, and so you can just make this nice and simple for key value. By the way, you can eliminate the parentheses here, and I think it's prettier if you eliminate the parentheses, but you could put parentheses. This is still a tuple without the parentheses for key and value in sorted. So that says go through D items, but before I go through them, please sort them. So that means K is going to go through A, B, and C deterministically every single time it's going to go. And of course, value is going to go through the corresponding values. So now we can print this out nicely, sorted by key. And that's a real nice, succinct little way to say that. I mean, again, these are one of the kind of things that people really like about Python, is that you can do pretty powerful things with easy to understand. I mean, you might have seen this for the first time, but ultimately you look at that eventually and you'll be like, oh yeah, I see exactly what that's doing. Easy, not hard at all. So, but let's say we're looking for the most common word, which we have been for weeks and weeks and weeks now. And so we want to sort by values, not key. So this is an example of where we're going to construct a data structure. We're going to imagine a data structure, and then we're going to write code to construct the data structure, and then that's going to make our problem easy. So this is an example of using cleverly constructed data structures to do this. And the data structure that we're going to create is a list of tuples where the value is first and the key is second. So you can just with items get key value. I want value key. So Let's take a look at this code. Take your time and get it right. So KV goes in C items. Well, that is unsorted and going to go through whatever A, B, and C in whatever order, and we're going to make a new list. So this is a data structure that we're creating temporarily. And what we're going to do is, this is a list, and we are going to append to that list a tuple. So this is going to be a list of tuples. Except we're not going to append them in key value order. We're going to flip them and append the first part of the tuple is going to be the value and the second part is going to be the key. So we end up with this. This is sort of our temporary data structure that we have constructed to make our job really easy. So this ends up being 10A, 22C, 1B. Now we just kind of flipped them. We took this order and then we flipped them around. And so now we have this nice little list sitting in memory in a variable. And that's really simple. We can say, oh, look, we can use sorted, and we can sort by now the values because they're the first thing. I mean, the sorted doesn't know that they're how we produce this list. It just looks at that and says, oh, that's a list of tuples. I'm going to always sort by looking at the first item in any tuple, and I'm going to add reverse equals true so I get a descending sort. So I see that the value that is highest ends up being first. And so that changes this, and I'm just sort it and then reassign it back into temp. And I'll print this out, and so now you see it's sorted in descending order of key. So it's value, key, value, key, value, key, but it's sorted in descending order, okay? And so that's an example sort of just like, you know, if I just made a data structure and I flipped those things around, I could use sorted to sort these things. There's many other ways you could do it, but there's sort of like the more elegant way of doing it. And the clever bit here is like, make a new list and make it be a little bit different. Okay? So here we're going to print out the top 10 most common words in a file. And most of this code is review, so if we take a look at it, we're going to open a file. We're going to start a dictionary for our counting. We're going to, you know, there's going to be words and lines, right? And so we're going to have a for loop. This for loop is going to go through each line. And then, of course, we're going to split them, which is busting them into pieces. And then we have a for loop within that, and this for loop is going to go through each word. And so that means that by nesting these loops, we're going through each line, and then within the line we're going through a word. Then we go to the next line and go through the words. And eventually this line of code, count subword equals counts.getWord 0 plus 1, our idiom for making a histogram, right? This line right here is an idiom. If you don't know already what that is, go back to the previous dictionary lecture and understand it, because you're just going to use it over and over again. So now at this point, and I always like drawing horizontal lines in code when we write it, at this point, coming through at this point, counts is right. Counts is the histogram. It's not sorted. So now we want to sort it. So we're going to make a new list. We're going to loop through key value, and then we're going to make a tuple. I'm making this be 2 lines to make it a little easier. Value key, so I'm flipping it, right? So I'm flipping the order of these things. That's making a tuple, and then I'm appending that tuple to the list. Okay? So at the end of this, we have a list of tuples in value key order, VK, VK, right? So at this point, coming through here, I've got in my LST variable, I've got this really useful bit of code or useful bit of data that I produced. And then I'm like, oh, now it's ready to be sorted. Poof, sort. So take list, sort it back, and sort it in descending order, and then stick that back in list. Now we want to print it out, but we don't want to print it out. So we got a nice sorted list coming down here. We don't want to print it out in value key, because that's what it is. It's in parentheses V comma K order, but it's sorted. And we know that the highest value is here on down. And so we're going to say, you know, we're going to run through, and now we're going to go through this new list, only the first 10, start at the beginning up to but not including number 10, which is the first 10. For value key in, and so value is good. So this is the iteration variable that's going to go through each of these things on and down, and then we're just going to print it out flipping it. So we re-flip it, flip, flip. We print it out key value, and it's going to work. Okay, so that is one way of doing this, and this slide right here you absolutely do not need to figure out. But some of you will look at this slide and you're like, why didn't you show us that in the beginning? And others of you will be like, no, 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 keep telling me this stuff here. So I don't know exactly the term for this, but this is a very procedural. This is a classic algorithms and data structures approach to solving this problem. This next thing uses what are called lambdas, and they kind of create what's called what I call a closed form, where you kind of do it in all one statement, and there's all this implicit stuff going on. So if you don't get this right away, don't worry too much about that. But roughly, this single line does everything that bottom half of that program does. I mean, if we go back to here, it's pretty much this line does everything, does that in one line. Okay, it doesn't create the counts and it doesn't print out the top 10, but it does everything in that middle bit. So let's take a look at this. So we all are going to collapse this down. So we have a print, that parentheses the end of the print. And then we have sorted, and remember that sorted takes as input a list. And so that's not too bad, and returns us a list. And so we'll print the return from sorted. And then this is the funny part. The fun part, funny part. This is called list comprehension. And we have square brackets, and we say to Python, this is a list. But instead of listing the things or having a constant of 1, 2, 3 or append, 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 we are going to create an expression that will act as a generator for all the elements. And so this basically says, this is a list of two tuples, v and k, and then this is sort of implied. For all kv in c.items. And so this is like a for loop that is sort of driving this. Think of this as like stamp, 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 stamp. However many times it has to make a stamp. And so that's producing a list, right? It just manufactures this list. And then that list is sort of manufactured in the moment. There's no stock, it's not put in a variable. Python makes that list according to the stamping pattern that you've told it to stamp out this list, and then it passes that stamped out list without even storing it in a variable into sorted. Sorted moves the list around because it is just a list of tuples, and then gives us back the sorted list. And so I didn't put reverse equals true on here, but you see that this is sorted in ascending order now by key. And I did that all in one little statement. So look at this. This is also one of the beautiful things about Python, that you can build these things, and you can build more complex versions of this, and there's a lot of real elegant things that you can do in Python that are really succinct. You should be careful, because in the beginning I think this is easier to understand, even though after a while you're like, wait a sec, why am I putting all these extra lines in? Because this is not so hard to understand, but at some point you will want to master this more powerful and more succinct version of Python that expresses it in terms of what the data you want to see rather than the steps you want to take. So this sort of finishes up tuples. We've done a bunch of stuff. I mean, really, they're simple and elegant. Tuples, lists, and dictionaries are all related. They're really three different, three foundational data structures, three foundational collections of Python. And we combine those in a lot of different ways.
And now in this little bit of lesson, we're going to talk about some tuples, and we're going to create a list of the most common words and find out how to sort a dictionary by the values instead of by the key. We're going to use the clown.txt file and the intro.txt file. And I'm going to start with the code from exercise 9 that I just did from chapter 9. It's not exactly one of the exercises, but it's very similar to them. And I'm going to make a copy, and I'm going to keep it in the same folder. I'm going to keep it in the EX09 folder and just call it EX10, because this code is going to do much of the same stuff, and it's going to read these same files. And so I've got myself exercise 10. Exercise 9 is still here. Exercise 10 is now what I'm editing, exercise 10. But I'm in the exercise 9 folder. So in exercise 9, we look for the most common word, but we want to find the 5 most common words, which is going to require us to sort. So I'm going to get rid of that code, because it's not really how we're going to do it. There we manually looped through it and found the maximum. And so I'm going to just run this. cd desktop python for everybody ex09. And if I do an ls, you see that I've got ex09.py, intro.txt. So I'll run python 3 ex10.py and run the clown data, and we see the dictionary and it's properly making it in this code right here. That doesn't change. It reads the file, reads all the lines, goes through and splits it into words, and then goes through the words and does the idiom of using dictionary get to maintain the counters, and we print it out at the very end. So the new code we're going to write is down here. Okay? So let's first do a few things. If I can say x is equal to the dictionary dot items, and this gives us basically a list, print x. This gives us a list of the key value pairs. This prints out the dictionary, but if we do it this way and use items, it gives us the key value pairs. Okay, and so that's what we got. Key value pairs. Now, we can sort this based on the value, because tuples can be compared. This can be compared with this, and because D is lower than R, then this one is lower. This ran tuple comes after the down tuple. So we can sort this whole thing. And I'll do this by just putting the word sorted here and say, give me a sorted version of that. Now it's going to do it based on the order of the tuples. This is going to be higher precedence than this. So if I print it this way, run it again, you'll see that it's sorted. And now is after and car, it's in alphabetical order by key. And so we could actually print the first 5 up to but not including 5 by adding a list on the slice, a list slice here. And so that will show you only the first 5, right? Except that that's not what we're trying to do. We really want to sort by this. Okay? So, we have this mechanism that can take a list and sort it based on the tuple values. If we could create a list where it was 1 comma after instead of after comma 1 and make it the exact same thing, then we could actually then sort it and it would be fine. Okay? So let me show you a couple of ways, at least one way to do that. Okay? Get rid of this. We're going to hand construct a list. And just call it temp equals, give me a new list, temp equals new list, and then for k comma v in the dictionary.items, and I'll just start by printing k comma v, so we see, and this is where it's really nice to do these with the clown code first and then only do your test on the bigger file later. And so it's pretty much the same thing. We are going through in key value order, which is dictionary order, which is not sorted at all. Okay. Now, instead of printing this out, we are going to, let me do this in a couple of steps. Make a new tuple, and we'll just call it newt equals parenthesis v comma k. Okay, so this is, I'm saying make a new tuple. This is like a new tuple with 2 items in it, and I'm going to make the value and the key. Okay, so then I'm going to say temp.append newt, new tuple. So I'm going to end up with a list of tuples. Let me comment this one out, and I'm going to then, when I'm done here, I'm going to print temp. So if I run clown.txt, you see what happens in temp. It's still, well, let's print temp twice. I mean, it's not sorted, it's flipped. Let's print it. Well, that's okay. We'll just, that's the flipped one. Okay, so it's flipped. And all we did is we made it, instead of car comma 3, it's 3 comma car. But now we have a list. Okay? So now it's flipped, and now we can sort that. We can say temp equals sorted temp. So it says takes temp and sort it and give it back to me. And now I'm going to say print sorted, comma temp. Okay, so here's the first print. When we flipped it, we've got 210, but it's not sorted at all. But after we sorted it, it's sorted by tuple, and the lowest is 1 after, so you'll notice that 1 is the same as 1, so it checked the second item in the tuple, so down comes before after. Fell becomes after down. Intro, on, alphabetical order, but now we get the 2's, so that all the 1's sort there, and then the 2's come here, but then within the 2's it's sort in alphabetical order, because like a string, if the first character matches, then it looks to the second character, and then we see, oh, here we go, the 3's, and then the one we actually wanted, the highest one, is the 7. And so one of the things we can do is we can say, you'll notice that we want the highest one, not the lowest one. So we can just tell this with this parameter, reverse equals true. And we just say, hey, sorted, do this backwards. Do it from highest to lowest rather than lowest to highest. And now our sorted one says 7, the, etc. Okay? And so if we want the first 5, we can say up to, but not including 5. So this is now the top 5. So the sorted one is, that's the top 5. If it's a tie, we're going to go in reverse alphabetical order, but let's not worry about that too much for now. So it makes a flipped list, then it sorts the flipped list. Now, if I just wanted to print it out nicer, I could loop through this new list. I could say for v comma k. Remember, this is a flipped list, so the sensible thing is what's coming out of this list. Each tuple is value comma key in temp, and I'm only going to go up through, but not including 5. So the first 5, and so I'm pulling them back out as value key because that's what they are. They're value key. See, value key, value key, value key. So v is going to go through these, and k is going to go through these, and then I'm just going to print k comma v. So this is kind of my flipping backwards because I want to see them this way. And thus the most common one, car 3. And so it's just going through this up through the 5th one and then printing them out. Okay? So let me comment this out. Let me comment that out. Let me just delete this. So we have a dictionary. Let me comment out the dictionary. We have a dictionary, we make a list, and we make these reversed tuples where we have the value first and the key second. We're setting it up so the sort's going to work. And then once it's sorted, we have to flip them back. So we flip them for sorting from key value to value key for sorting. We do the sort, then we flip them back with key value and print them out. And it works fine. So let's try our big file, intro.txt, and there you go. Those are the 5 most common words in intro.txt. So you might ask yourself, why did we use tuples? We could have really used lists for this, but tuples are more efficient than lists, and you notice that we weren't going to modify. We did modify the temp list. It's a list of tuples, but the tuples within the list we weren't going to modify. And so we tend not to make lists if we can get away with using tuples. And so that's why we made this this flipped tuple thing. Okay? So I hope that was useful to you. Hope to see you on the net.
Hello and welcome to Chapter 11, Regular Expressions. The fun thing about this chapter is, unlike all the rest of the chapters, you sort of had to really understand every single thing in chapters 1 through 11 built on one another, 1 through 10 built on one another, but you can really get along without using chapter 11. It's not a really required topic, but it's a fun topic and an interesting topic. So you can relax a little bit and realize that you may or may not like regular expressions, and if you don't like them, that's okay. You don't have to use them. You can go for your whole life without using regular expressions. The idea of a regular expression is that you come up with a language. It's a little character-based programming language where you can do smart searching, basically. Smart searching, and as you'll see in a bit, will smart extraction, and it's really almost programmable wildcard expressions. There's no looping, but there is looping, and there's all this implicit thing, and you say, look for patterns that look like this, and then you get back things that match those patterns. We do searching for everything. We're looking through large blocks of text, say, go find me everything that has the word Python in it, or something like that. So that's just such a common thing to do, and regular expressions are a very structured way to go about searching for information. They're very powerful, but they're also very cryptic, and you may not like them, but they're a lot of fun, actually, once you understand them. Learning how to program them takes a while. Writing good regular expression programs requires some try it, play with it, check it, try it, check it, try it, check it. But once you get them, they're really quite cool. It's a very old programming language. It comes almost from the 1960s. The concept of, it's the theory of computing, where they were trying to come up with theory of languages, and regular expressions was one form of languages that computers could understand. And so it has some fun old words. And one of the advantages of knowing regular expressions is that you're kind of a cool person. You can take a quick look at this XKCD that sort of captures the devil may care awesome power that regular expressions do. And while we're at it, while we're talking about awesome, I do want to take this moment and show you my awesome tattoos. And so you may not know this, but I got a couple tattoos here. Here's the first tattoo. This is where I got my PhD, and this is my University of Michigan faculty member position. I got PhD in engineering, and I teach in a school of information and library science. And then I have this other tattoo, and this tattoo is what I call the Ring of Compliance. I work on learning management systems and educational technology and standards, and there's this standard called Learning Tools Interoperability, which if you're using this course and doing the AutoGrader, it uses Learning Tools Interoperability to integrate into whatever learning management system you happen to be using. And one of those learning management systems is the open source learning management system that I helped write called Sakai. And these are the rest of the major vendors. And the idea of that tattoo was that I would put the tattoo of every vendor that would comply with Learning Tools Interoperability. And so you'll notice Coursera. I helped Coursera put Learning Tools Interoperability in, and so the AutoGraders integrate into Coursera or Blackboard or Canvas or Sakai or Moodle or half a dozen other things. So it's just like a cool techno thing, just like regular expressions. So I've got a URL here for regular expression quick guide. You might want to print this out so that you can look at it even while you're watching this lecture, because it's a little programming language, except that it's character-based, not line-based, and not keyword-based. It has certain active characters that the character means something versus the character represents the character itself. And so the regular expressions is not part of the base Python, but it's distributed with Python. So you have to put an import RE at the top to say that's really saying pull in the regular expression library. And there is a couple of functions inside that, re.search, which is kind of like a really smart version of the find method inside of strings, and re.findAll, which is kind of like taking and stamping your way through a loop, through a string, and finding all of the things that match a particular pattern and then extracting those. And we'll talk about both of these in this lecture. So here's a really simple piece of code where I'm just going to sort of show you sort of before and after. So here's a thing where we're looking for lines that begin with from : and so we open a file, we loop through the whole file, we strip off the lines text, and then we say if line.find from is greater than or equal to 0, then we print it. It gives you -1 if it's not found, and so reads all the lines, and once in a while it'll print it out, reads all the lines, once in a while print it out. So that's kind of like a needle in a haystack. To use regular expressions to do that, we have to import the regular expression library. These lines are the same. We're going to loop through, we're going to strip. And now we're going to say if re.search. The way to say this is within the library regular expressions, go find the search function and search for the string from in the string line. Okay, so this is the line to search, whereas here it was more object-oriented where we say line.find. Here we say re.search and we pass in line as parameter. These two things are equivalent, which means most of the time it's going to run, and once in a while it'll hit a line and it'll print that out, and then it'll finish the whole thing. So that is taking and doing what we would do with the find operation with regular expressions. Now, Searching with regular expressions has these special characters. And so here we have the same basic code, except now we're saying if line starts with from. So we're not using find anymore. And that way we're only going to get that thing in the first position, not like blah, 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 from, colon. We don't want that to match. We only want it to match here at the beginning of the line. And so that's what we use line starts with. So it's going to do the same thing and find lines that have the prefix and print those out and then be done. Now in regular expression search, we don't, in a sense, change the method. We have a certain number of things we can do with strings based on what they've built in. But in regular expression, we actually can turn this first parameter into code. And so what's happening here is the caret, if you go back to the little cheat sheet, caret means this is the beginning of line. It's a virtual character that matches the beginning of line. It's like from that starts at the beginning. So from at the beginning does match, and from in the middle does not match by putting that little caret there. Same thing, line is what we're searching, and then from is what we're, caret from, line at the, from at the beginning is what we're looking for. And so again, it does the exact same thing. It only prints lines that have from colon as the first character in the line. So the difference is we look for a method, and the other one is we program the regular expression. So we're going to run out of methods in the string class long before we run out of things that we can do with regular expressions. And so a couple other special characters, that caret matches the beginning of the line, so caret matches the beginning of the line. This capital X matches itself. Dot is a wildcard that matches any character, and then some of the characters in regular expressions modify the immediately preceding character. And so that says look for a line that starts with X and then has many characters, that's with these two things, 0 or more characters followed by a colon. And so you can see that it's this sort of like expanding stamp. It's like, oh, there's an X at the beginning of the line, that line, it looks good. I got some characters here and then I got a colon, that's good. So this is an X, some characters, and a colon, check. X, some characters, and a colon, check. X, and these things, you know, away we go. And so you can, that's what's going to match. And so you can see how some of these characters are special. Again, go back to your cheat sheet. Some of them are special and some of them are actual characters. And this colon and X are just, they're not special, they're just the characters. Okay? Now, sometimes you want to be a little more clear on your match. So let's take a look at these lines that match that particular thing that we just did. So we have these two, x-civ colon, x-d stam dash result, like these are from mail messages. And then one of the mail messages has a line in it that says x-plain is behind schedule. And this matches. Is that what you really wanted? And so what we can basically say is, because this is an X, this is some number of characters, and that's a colon, it matches. It has to match. That's this rule applied to this line results in a yes. It does. And so how can you be a little more clear as to what you want to match and what you don't want to match? So we can write code. So now what we're going to say is we want to match the beginning of the line, and we want to capital X, and we want a dash. So now we're going to match those first two characters, X dash, at the beginning of the line. Caret X dash says first two characters of the line must be X dash. Now we have another special character. Again, refer to your cheat sheet. Backslash capital S means a non-white space character, right? Any character other than white space. And then plus means one or more times, one or more non-white space characters. That's what this whole thing says. One or more non-white space characters, and followed by a colon, which is just a character. So now we have X dash followed by one or more non-white space characters followed by a colon. X dash followed by one or more non-white space characters followed by a colon. Here we have X dash followed by one or more, whoops, there's a space there. And so this doesn't match. Even though there's a colon there, it means that between the dash and the colon, you can only have some number of non-white space characters. So this is a no, it does not match. And so you just can, if you didn't want to match this, you then sort of create a more precise, you know, we could even have a thing that said, I want X dash with an uppercase character, uppercase letter, if you wanted to. And so there's all kind of fine-tuning if you sort of learn the structure that you've got to do. And so that's kind of the matching, where you're taking a whole line and taking this template and deciding if the template anywhere in that line matches. And now what we're going to do is use this to actually pull data out of strings using the regular expression library. So now we're going to move from merely matching to matching and extracting. So we're going to say, hey, I would like to not only have you take this template, this little pattern, the string pattern, regular expression pattern, run it across the line. I want you to give me all the ones that match, and I want a list of those. And that's what we're going to use the find all. So search gives a true false. Find all gives a list of all the strings that match. So if there's 4 of them, you'll get 4 things in the list. If there's nothing that matches, you'll get an empty list. So let's take a look at what we got going here. So instead of calling search, we call find all. We still pass in the string that we're looking through, and then we have our little template pattern. And this is a new bit of regular expression. Any little bracket operation, square bracket, is one character. That's just a character, but then there in between here is a set of allowed characters. So 0-9 means a single digit, 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. But that's really one character. And then we have, so that's one character. And then when the plus applies to that, which means if we look at this whole thing says 1 or more digits. That's the code we write in a regular expression that says 1 or more digits. And we're just going to use that in our regular expression by itself. So we're going to look for any string that's 1 or more digits and pull it out and give it back to me. So it's going to look. So that's my little template. Stamp, 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 stamp. Oh, got it. Stamp, 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 stamp. Oh, got it. Stamp, 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 stamp. Got it. So what we get back after we ask find all to find all of the 1 or more digit strings is 2, 9, and 42. So it actually parsed it, it split it, it found all these things and said, I found them all for you, and here they are, 2, 19, and 42. So it's a list of 3 strings because that's how many it found. Now it might have found none, and we would have got an empty list at that point, but it found some. Okay, so just as an example, you know, we did this thing, we get 2, 19, and 42, but if I said this, that basically is an uppercase vowel, A, E, I, O, or U, so that's one letter, and that's 1 or more. So it's saying, you know, something like A would match, E, I would match, O would match. But if you look now, it's saying, okay, I'm looking for 1 or more, minimum 1 or more uppercase. A, E, I, O, U is a set of characters, 1 or more uppercase letters. And so it says, like, look, do you find, oh, there's an uppercase, but it's an M. No, 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 no uppercase, no uppercase, no uppercase, no uppercase. Found nothing. Did not find anything. And so it gives us back an empty list. And so it's like, find all the things that match this. And the answer is none matched. Here's your list of nothing. Okay, and so you have to check. That's how you have to check even if you got something, because it's not going to return you false. It returns you a list with no items in it. Now, the way it works, like I said, it sort of is taking this template and stamping it across the line, stamping across the characters. Now, there's a behavior that might not be intuitive you at the very beginning, but the notion of what we call greedy matching, and that is when it can match more than one possible string, overlapping string, it chooses the largest overlap of the overlapping strings. And so the easiest way is to show this with an example. And we're saying, I want something that starts with an F with 1 or more characters and ends with a colon. So that's my little stamp, that's my template. So starts with an F, good, that's good. 1 or more characters, da-da-da-da-da, have a colon. So that could be from colon. That would match. But look, I've got another colon here, and this is just continuing on with 1 or more characters and this. So the question is, do we get this or do we get this part, right? And the answer is, with greedy matching, is we get the larger of the two. Okay? And so what you get back is somewhat counterintuitive. You get the whole thing as the match, from colon using the. We could have got from colon, but the reason it picks this is this one's longer. So anytime it has a choice, it picks the longer one. And that's what greedy is, meaning it'd probably be better described as larger or tending toward the longest string or something like that. So you can, of course, suppress this behavior. Like everything in programming regular expressions, you simply add another character. And so now it's going to say, I would like to start with letter F, any character, 1 or more times, and then this question mark, this is still one little thing, non-greedy. Okay? And so that just says do it not greedy. which just means that it prefers the shorter of the strings. And so now it could still match this string or this string, but because it's been told to not be greedy, it chooses this string instead, and that's the string that we get. And so that's the not greedy, and you just add the question mark after the asterisk. So it's usually an asterisk question mark or a plus question mark, though that's a two thing. That's 0 or more characters non-greedy, and that's 1 or more characters non-greedy. Actually, most of the time, it seems to me that the non-greedy would be the more reasonable default, but that's not how it is. Greedy is the default and non-greedy is optional. Now, we can play some more with this stuff, okay? And so let's take a look at this little example where we have a non-blank characters, \S, 1 or more of those non-blank characters, followed by an @ sign, and then again 1 or more non-blank characters. So this is looking for strings that have an @ sign with non-blank characters on both sides. This is an example of where it sort of comes to this @ and it goes this way, and it does it in a greedy manner. If you told it to not be greedy, it would give you these 3 characters. But we're telling it to go greedy, so it goes all the way to here and stops at this blank, and then stops at this blank. And so that's a nice little thing. Find the @ signs, go to the first blank, and pull that stuff out. And so that, with one little match, you've pulled this thing out. Now, of course, we've done that before with other techniques. So that's just another way to pull stuff out. Now, if we get this whole thing, but what if that's not exactly what we wanted? We can tell, we can give it a matching string that's different than the extracting string by adding parentheses. And so here's another example where we basically say, this is our string. We want to match from at the beginning, followed by a space, followed by, ignore the parentheses for the minute, 1 or more non-blank characters, followed by an @ sign, followed by 1 or more non-blank characters. So this is also going to, if there's no from, it's not going to be looking for that, right? So it demands the from is here, so it matches that, and the space is demanded as well. And then it says, oh, non-blank characters, great. I got an @ sign, great. Non-blank characters, oops, stop there. And so this is what's going to match. Now the key is that we don't actually want that back in our extraction. What we really want back in our extraction is this part right here. So what we do is we put parentheses in. Parentheses are code, they're code in the regular expression world. Parentheses say start your extraction and end your extraction. And so when you do this with a parenthesis, when you do it, without a parenthesis, you get the whole from, right? Without a parenthesis. Oh wait, no, okay, that doesn't have the from in it. So, but if you do that with the parenthesis, you match the from, but you only get this bit to come out as well. So you can add this to make the matching part more precise, but without changing what you get returned, and you specify what you want to get returned with the parentheses. So next I want to show you just a couple of different ways to use these newfound skills. So now what we want to do is use some of these newfound skills in some more practical applications of regular expressions. So let's go back to the way we first tore apart strings and look at the situation where if you recall, we just wanted the host name, right? This is an email address and we're interested in the host name. So we have this string and we go find the @ right? The find looks up and tells us the @ is at position 21. And then what we do is we say, okay, let's look beyond there to the space, and that tells us the space is in position 31. And then we're saying we can extract starting at beyond the @ sign up to but not including the space by saying @pose +1 : space position. And when we get that, now we have to have a thing that decides to only look at this on from lines, but then it can print out the host that is extracting of this information. So that was one way that we did that, right? One way we did it. The next way we did this was the double split pattern, right? So we said, okay, let's take this line, let's break it into words based on spaces. That's what words is. So that's 0, 1, 2, 3, 4, 5, 6. And then we know that the email address on lines that start with from, space, is the second one. So we pull out email address, which pulls this bit out into email. And then we're going to split that again based on the @ sign. So we're going to split this part again based on the @ sign. So it splits right there, and then this becomes the 0 and 1 in pieces. And then pieces sub 1 is that host. And if we print that out, we get the host. So that's the double split pattern. Nice thing about that is you don't have to keep track. The little +1 is kind of annoying to use the space position. That previous one, that's just hard to remember. It's just, I've written this code way too many times in my career, and I've made mistakes, and I have to debug it every single time, and I print all these numbers out. I'm like, did I get it right? Oh, I did it in Python, I did it in Java, I did it in C. Wait a sec, I did it differently. And so this is a lot cleaner. I mean, I can write this every time, and I know it's going to work every time. I barely even need to test this code because it's so obvious. So double split is another way of extracting stuff. But if we look at this thing with the regular expression, we can say, oh, okay, let's use a regular expression to do this. So we'll start looking through the string. We'll start by saying, hey, let's look until we find an @ sign. Then let's start extracting with the parentheses. And then once we have found the @ sign, let's look for non-blank characters. This is a set of characters. This caret as the first one means not a blank. So that's another way to do non-blank. Not a set of characters which are everything but blank. That's what this little bit is saying. Star means 0 more times, which means it's going to run until it finds a blank, which is going to stop it. The greediness is what keeps pushing it, right? This is a greedy match. That asterisk is greedy because there's no question mark after it. And so that does go and starts at the @ sign with the parenthesis, goes to the space, and that's the end parenthesis, and that's what prints out. Now, Y is going to be a list. That's a one-item list that has the string in it that we're looking for, but you can just go sub-0 to get that guy right out of there. Okay, so that's sort of the regular expression version of it, but we can make this a more fine-tuned thing. So we can say, look, we also want to pick the line, and we want to know if we don't get that line, we want to skip it. If we do get the line, we want to extract the data, and we can do this all in a single regular expression. So again, we say start from the beginning of the line, and it's got to be a from, followed by a space, and then followed by any number of characters, dot star, followed by an @ sign. So this has to match. We see a space, then we're going to have any number of characters, and then we're going to see an @ sign, and then we're going to start extracting, and then we're going to go non-blank, 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 up, blank, and extracting, and out that comes. And this has the advantage of the previous one in that makes it much more precise. If we look at the previous one, while it works on good lines, it might actually trigger on lines that we actually don't want to see. So this allows us to refine it so it only actually does this to lines that we care about. So it's sort of both an if statement and a splitting, extracting going on all at the same time by having a bigger string that we're matching than we're extracting. It's a way to kind of clean up your data. So here is a simple program that we're going to just put all this together and actually accomplish something. And so we're going to read through and look for lines in a file that have this form. And we're going to extract this number, and then we're going to compute the maximum of this. Okay, and so we're going to extract this number and then convert it to a float and compute the maximum. So, we're going to open a file, we're going to write a for loop, we're going to strip. So we're going to do this for every line of the file, but the first thing we want to do is not get line. We want to discard all the lines except ones that have this. So our regular expression is look for lines that start with x-dspam-confidence : So that's a pretty strong match. If that's not there, we're not going to get anything. And then there's a space, and then start extracting, and then go as long, one or more digits and dots, that's a single character, and that's one or more, and then stop extracting. So that says start extracting, greedy, stop extracting. And so that's what we're going to get. Now, if the line doesn't have this, it means missing in some way, whether it's this prefix or this number. If the number's missing, it's going to fail too. We're going to get back a list, an empty list. So the first thing you have to do is check to see if you actually got a match. So you say if the number of items in the list, len of stuff, is not equal to 1, continue. And so this is the skip all the lines that don't match. skip, 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 skip. So there could be thousands of lines that don't match. But then when this match hits, it's going to come down and fall through, right? So that most of the lines will skip up, but then when we actually get one, and we know instantly that we've got one, and stuff sub-zero, because that's what we extracted, is this number. And we can take the floating point of it, we append it to our list, we made a list to store them, that runs, the list grows, and then we just say what was the largest one. And so you can run this and see that. We have an escape character, and the whole idea is sometimes all these little special characters that make a lot of sense to us, we actually want to search for it. So what if we want to search for a $? Well, we just prefix it with the backslash, and that just means this is a real $. So $$ is a real $. So this says I would like a $, followed by one or more digits or dots, and so that's going to match a $, followed by one or more digits. Dots are okay. This is a set, remember. 0-9 or dot, that's a set of the list of legit characters. This is a range of characters that's a shortcut to how to make the set. You could make it be 0, 1, 2, 3, 4, 5, 7, 8, 9 dot, or 0-9, and it assumes that. And that's one or more. So then it stops because this is a space. It's greedy matching. Then it pulls this out. So that's kind of why greedy has to be the default, because otherwise if it wasn't doing greedy matching, oops, come back. If it wasn't doing greedy matching, it would, if it wasn't doing greedy matching, it would stop here, because it would find a $, non-greedy would find a $, and one character, and then it would give us $1 rather than $10. So, in summary, regular expressions are a cryptic but powerful language, and they're an acquired taste. I bet eventually you'll find them fun, even though on your first impression you might not think that they're so fun. Welcome to Networked Programs. This is Chapter 12. Now we're going to learn a little bit about how we talk to resources on the network using Python. Now, this is a really quick introduction to how the network really works. I have a whole book that I wrote. It's also translated into Spanish on how the network works, starting at the very lowest layer, packets and everything, right on up. And it's actually really easy to read. I wrote it for a high school audience. It's a short book and pretty easy to read. So if you read that book, you will understand that there is this layered architecture, the TCP architecture that sort of runs our network. At the lowest layer, that on one side here, this is your computer and this is a server computer. And if you sort of want a web page, it goes across the network, does this like 15 or 20 times, then it goes up into the server, reads the data, and then the data comes back, 15, 20 hops for the packets, and then it's shown to you as what you see. And so that's how it works, and there's these layers that we're not going to talk about in this section, but I talk about in that book. The layers of the link layer, which talk about how to get over one hop, the internet layer, which talks about how to construct, say, 15 or so hops to get packets back and forth. That's the sort of lower level bits. We're going to start at what we call the transport layer, and that's the layer where your computer sort of assumes that it can make a phone call to another computer, another process running on a program on this computer, talks to a program on this computer, and then it kind of comes back. Okay, and so we're gonna leave this alone. We're going to ignore it. We're going to assume that there's this nice reliable pipe that's going from point A to point B, and what are we going to do with the pipe? But if you're interested, take a look at the book. So we're going to start with a pipe, some kind of a connection. We have two processes, process, and we have some kind of a connection between them. And it is a connection that we can both use to talk and to listen. In nerd terms, we call these things sockets, and that is one process running on one computer, another process running on one computer, another second computer connected through the internet somehow, and one computer speaks into that socket and it comes out, and the other computer returns something and it comes. And so this is a bidirectional protocol of data, which is a series of, in effect, data phone calls between applications. So the application might be on your side, this might be your browser.